All right, I think we're ready to make it official. So hello, good morning and welcome. My name is Rafał Motriuk, I'm a broadcaster. Thank you. I'll be your host today, so thank you very much for having me again. This is Code Dive, and it is now officially open. I'd like to welcome everybody gathered here in the New Horizons cinema today, as well as our friends who are watching online. We have grown so much over those years, and let me say we are people of all possible nations, creeds and ages. And today I'd like to have a special welcome from everybody to our youngest participant ever. She is 10 and her name is Rebecca. A big hand for Rebecca, please. Thank you. It's the 11th time that Nokia has organized Code Dive for us, and to mark the start of its pre-teen years, Code Dive is going back to the roots. Catch my drift? We're going back to the roots. A dad joke number one this morning, thank you. And we are going back to the roots in a figurative meaning as well, because we will be focusing on C++. It was this language, C++, that was the inspiration for this conference 11 years ago. And so our special feature today is this magnificent recycled cardboard tree. Initially, we thought we'd get a real tree with real roots to really hone in on this year's theme, but then we decided we are too eco-friendly, so we got this beauty. And as you can see, it is decorated with carrots, which are also roots. That joke number two. So here at Code Dive, we believe in supportive working environment, and we are not great fans of sticks, and so the carrots are our encouragement for the speakers to perform, and you, the audience, to show extra enthusiasm. On a more serious note, a Globi ISO C++ standard committee, also organized by Nokia, has just ended, which is why we managed to bring to Code Dive this year the brightest C++ minds. Although C++ will dominate our conference, one of the rooms will explore other state-of-the-art technologies such as cybersecurity, no-code tools, communication and productivity. Now, Code Dive, as you know, is an excellent opportunity to network and exchange experiences, and this conference, of course, is mainly for the professionals, but there will be also talks for beginner programmers. Recordings of all the talks, current and past, are and will be available on our YouTube channel. And this year we have 3 conference rooms, 28 speakers, 24 lectures, 6 lighting talks, and 1 much-loved lunch break. After the conference, there will be an after party at Szklarnia Cocktail Bar. You can walk there, it's literally 7 minutes away. When it comes to snacks and food stations, there's a Pan Pretzel on the 2nd floor. Downstairs, there's a cinema cafe and also a bike cafe and a bakery, Gorąco Polecam. And now, in line with our tradition, we are starting our first networking event. So on my count, I'd like to shout out your name, then your job, and on 3, your favorite programming language other than C++. So just to give you an example, I know, what is there to say? But you can still stay silent if you don't have one. So in my case, it will be Rafał Broadcaster Python. Ready? 1, 2. Very long titles, thank you. And 3. Okay, I heard JavaScript. I don't know about the reaction of the room, but we will check your faces later. We will analyze them on the recording. Now, a quick question for me. How much did you pay for this conference? Exactly. This conference is free, so may I ask everyone to please put your hands together and thank our organizer and sponsor, Nokia. Before we begin, just very quickly, some house rules. Please put your phones on silent. It would be great if you didn't interrupt the speakers until after the talk. There will be a Q&A session after each talk, and we are using an old school method this year, so no fancy online stuff, just regular mics in the room. And this year we have a Wheel of Fortune. You win prizes by spinning the Wheel of Fortune, and you also need to answer some questions correctly. And additionally, if you'd like, you can enter a special number, and then you can take part into a special draw later. The lucky 3 winners will be announced during the closing ceremony. And last but not least, you're going to find the forest on the first floor, where you can grab yourself a free 10-minute massage. Lunch break is at 1 p.m. There is no food provided, so everyone needs to get their own. There are several places to eat within walking distance. And now I'd like to give the floor to our panelists. So welcome. Let's welcome our keynote speakers first, and I'd like to introduce them as you can see the photographs in our slide. So let's welcome to the stage Herb Sutter. He's chair of the ISO C++ committee. Hana Dusíková. Hana is staff software engineer at Woven by Toyota. Jason Turner, he is a speaker, developer and trainer, and also the author of Jason C++ Weekly on YouTube. Bjarne Stroustrup is a member of the C++ Standards Committee. He's also a professor of computer science at Columbia University in New York City. Taras Lukaniuk, his country manager, Nokia Poland, and he's the guy who is actually paying for this conference. And the person who makes it all happen, Eva Okołotowicz, Code Dive project lead. So we are going to have a very brief panel right now, and it'll be pretty simple. One person, one question, one answer, and we need to keep it brief because, again, in line with tradition, we got delayed. So just to check your editing skills. So the first question for you, Herb. How, in your view, have ICO C++ Standards Committee meetings evolved over the years?
Probably the biggest thing is the growth in the committee compared to, say, 15 years ago. So at this meeting, we just, less than 48 hours ago, finished our 6-day meeting here in Wrocław. Actually, some groups continued until almost Saturday dinner time, but because they were doing core language wording, and that's very important. But we were able to have over 220 people, 2/3 of them physically, the rest via Zoom. Very productive meeting representing over 30 countries. So you already did this, but I want to do it for the committee. Thank you to Nokia for hosting us. It was a very productive meeting, and we really appreciate it. Thank you. But that has also caused us, as we grow, to have more subgroups to do work in parallel, and it's great to see all the people interested in C++ joining and working in different domains, and it's really helping progress the standard. C++ is very much a living language.
Wonderful, thank you so much. Hana, over to you. As a regular contributor to the C++ community, how do you view the role of those programming conferences? I mean, what does sharing knowledge mean for you?
For me, it means I learned a lot at my first conference. I met people, and it helped me grow exponentially. I went to CPBCon 2017, I think. I met people from the committee. Next year I gave a talk, and next year I gave a keynote at a conference. So it was like exponential. And I'm telling to all my friends, you should go to a conference and give a lightning talk. It will help you to meet people, start, and network.
Thank you so much. Jason, the aim of your C++ channel is officially making C++ fun and accessible.
Yes.
Tell us, how do you make C++ fun?
So when I first put that on the channel, I was working on projects that made it so that you could interact with a game and you could learn C++ better that way. And I thought, hey, I'm making C++ fun. But since then, I think it applies to everything that I try to work on. I have puzzle books where I try to make things fun. And if you've been to any of my talks or my trainings, hopefully you think those are fun as well. I try to get everyone involved and interactive and engaged. I think that's really what I'm trying to do in general.
And you try to make your characters pixelated, which is also good fun for old schoolers, I suppose.
Yeah, I have voxel characters all the time on my screens, yes.
Thank you for doing it. Bjarne, over to you. What has been the biggest surprise in C++'s development over the years, particularly from your perspective as its creator?
Two things really related. The first was the idea of using constructor-destructor pairs was there from the first week, and I have been somewhat surprised about how powerful that is and how it's at the bottom of most of the really important and powerful things in C++, and one of the things that distinguishes a language. And then secondly, not so happy, people don't seem to get exceptions, and especially they don't seem to get exceptions in connection with resource management, with constructor-destructor pairs. They try to use exceptions for everything, which is silly because it's for exceptional things, and they want to use it together with sort of pointers that are owning things, which is what you're supposed not to do because you've got constructors, destructors. The two things are closely related, and so one is great, way above what I could imagine. The other one is a bit of a disappointment, and I still hope people will get it right eventually.
Thank you. Taras, I was going through the agenda and the script and so on, and it looks like C++ is going to be mentioned today hundreds of times. I mean, literally, people are going to have fantasies/nightmares about this one later today. Why is C++ so important for Nokia?
Thanks, Rafa. To be honest, I thought you are going to ask traditionally about the budget for next year. So many people asking that. It's confirmed already. I just to let you know.
Woo! Yeah.
But
Next
talking about the importance of C++ for Nokia. So the modern telecommunication systems. These are huge systems and working in real time and close to real time environment. So there's efficiency requirement. It's actually critical for us, and here obviously C++ is meeting all the requirements. Plus we are working on embedded systems. I know many of us are not paying on the attention on the cost of hardware because actually it's got decreasing from year to year, but basically when you're working on a BTS system, those resources, you cannot assume those are unlimited. So here C++ is a perfect tool allowing you to control your environment. Second thing I would like to mention, it's basically user-friendly. I'll call it like that because, a part of being efficient, you also need, talking right now as a business owner, you need to have people on the market that are advanced and that have unnecessarily skills and knowledge. And obviously, you can these days find a language that maybe will be a bit faster, maybe will be allowing the resources yet more strict, but simply you need to have people on the market to code your systems. And with the C++, there are no any issue. And last but not least, it's future-proof. So the telecommunication systems are changing. So we are not no longer talking only about the classical deployment. So it's Cloud Run, Open Run, or any run, how we are calling it. So it's important that the language that we are using, it's also developing. So on a dinner we had with Bjarne and Herb, I have openly asked, so what's the future of C++? And you know, and the answer was from Bjarne was more than confidence. So look how intensive work there is ongoing, and the last week is proving that. How many new people are joining every month in C++. So the backlog of items, the features that is there to be implemented, it's huge. So you know, this gives us a confidence that there is still a bright future in front of C++, and this gives me a confidence that Nokia and C++ is the right way together.
Thank you. Thank you so much, and thank you for future-proofing it for us. I mean, both C++ and CodeDive. And Eva, you are the person who makes it all happen. And this year's main conference theme is Back to the Roots. Could you elaborate on that? Explain to us what this theme represents.
Last year, at this very stage, we had the pleasure of hosting real founders of the CodeDive conference. And they shared stories about its origin, deeply rooted in C++. Patricia, Dominic, Konrad, warm greetings to you. And actually, thank you, because thanks to you, I have a privilege to lead one of the biggest, but definitely one of the most exciting events in my life, this event. And as a Nokia, you've mentioned, Rafał, previously, we had a huge privilege to help to support co-organizing ISO C++ standards committee, the global committee meetings, which just have happened. And this is not a coincidence that straight after we have a CodeDive taking place. And guess what? We asked some of these brilliant minds to come over as our speakers, and they said yes. That's why they're just there. And because of that, and thanks to that, we got back to our roots, to the first and foremost topic of this conference, which is C++. And this is what stands behind Back to the Roots.
Thank you, Eva. Thank you so much. Thank you, everybody. We'll hear from each of you later. So, yeah, this was our panel. Bjarne, if I can ask you to stay, you're up next with your talk. And, yeah, let's thank everybody for this wonderful panel.
Thank you very much.
Thank you so much. And yes, we are continuing with our keynote. And let me introduce, I know you know the person, Bjarne Stroustrup. He's a designer and original founder of C++, founding and current member of the C++ Standards Committee, professor of computer science at Columbia University in New York City. So we are going to continue with our talk. Let me just add that also Bjarne is a recipient of the Charles Stark Draper Prize. He authored the C++ programming language, Programming Principles and Practice Using C++, and also a tour of C++. So the essence of C++, let's have a big hand for Bjarne Stroustrup.
Thank you very much. I have to speak very fast because I thought I had an hour. But let's see. So the essence is basically something that is fundamental, so that if you take it away, it's not real anymore, it's not that anymore. So I'm going to try and go through the things in C++ that I consider essential. Things that you really need to understand, need to use, otherwise things go bad. And there's a basic model of everything. I tried to document it back 30 years ago in a book, and basically we need a static type system. I rely a lot of static type system because that's how you could get guarantees, that's how you can get compilers and tools to find your bugs for you before you lose your nice sleep. And there's equal support for built-in types and user-defined types. A lot of languages can't figure this out, so you have some types you just use, and some types you have to stick new in front of it to use and use references. We need both value and reference semantics. I like value semantics. You can copy things. They are independent things. They behave like mathematical entities, but to build them, you need pointers. And to get them efficient, so you need both. And we need general and systematic resource management, known by the strange name RAII, which is basically the use of constructor-destructor pairs to handle resources, and this is really fundamental. Efficient object-oriented programming, and then more and more over the years, compile time programming. If you can move things to compile time, then you can get good checking, and you don't have to write error handlers. It's not just performance, it's simplicity of code. And flexible and efficient generic programming against something that was there from the beginning, but has become more and more important, better and better over the years. And then, of course, direct use of the machine and of the operating system, no indirections, no reformatting of data and things like that. Concurrency support through libraries dependent on intrinsics. That I don't have time to talk about today. I have one slide which is basically an apology for not doing it. And then eliminate the C preprocessor. I really dislike the C preprocessor. It's in between you and the compiler. What you see is not what the compiler sees, and that is trouble. This is why the IDEs are not as good as they should be. It is a source of bugs. So we'll get rid of that eventually. So I wanted it for systems programming, embedded programming, resource-constrained systems. Resource-constrained systems are things like wristwatches and huge server farms. They are both limited by the amount of resources you use, and large systems. And I would like C++ to be good for experts, expert-friendly, but it cannot be just expert-friendly. You need novices on board, you need to teach people, you need people to learn, we need to move ahead. And basically, what we're here for is the applications. I'm really not all that interested in how best to write an article for the Principles of Programming Languages conference to see how clever stuff you can get in a 2-column format. I want to see things building good stuff, useful stuff. A programming language is a tool. It's a tool we use to build good stuff. So there's some good stuff, all C++ applications, by the way. And C++ comes from 2 sources. This is from day one. There was 2 things I wanted. There's a low-level stuff there, assembler, BCPL, C to C++. This is where you focus on the machine. You want to use every last byte, every last cycle. And yeah, people tell me that efficiency doesn't matter anymore, but they've been telling me that for 40 years, and I don't believe it. There's always at the bottom of the system somewhere where this matters. Most people are not there, but some people have to be there, and that's usually us. So at the other level is the high level, the abstraction languages. Started with Fortran, where Bacchus got this bright idea that we should have a language that was fit for humans. Not looking at the machine all the time, but looking at the applications. These applications were things like engineers and physicists wanted. They were formulas, they were equations, so you got Fortran. Once that worked, everybody else wanted one. So the business people wanted something that had their stuff in it, and this was very difficult. I mean, things like x equals y plus z was too complicated, so they invented a different language for it. But anyway, soon there was about 200 of these languages that built in the domain-specific concepts of their field. And this was chaos. People couldn't talk to each other. People couldn't exchange data. People couldn't use multiple languages. And this is where Christian Nygaard there came with Simula. Said, why don't we let people build their own types? can't people implement their own abstractions? So that's how we got object-oriented programming and Simula. Great stuff. And there's Dennis there with C, and Christian Nygaard there with Simula, and I happen to know both of them, and got ideas from there. If you read my writings, you'll see I always acknowledge what I learned. This was good. We got C++, and we got a lot of things coming from there, from that merger of the two ideas. So C++ in 2 lines is basically there's a direct map to the hardware starting with C. We're doing it better these days, but started with C. Zero overhead abstraction so that we can get away from the hardware, away from the low-level stuff. That started with Simula. We can do much better today, but that's where it started. And in the future, I would like to see complete type and resource safety, and we have concept modules, concurrency, etc., etc. I came from machine architecture, operating systems, and that kind of stuff. That's where the inspiration was, and if the strengths are there, that's not accidental. So essential properties, we have to have stability over a decade. When we build something, it has to work. So the reason we can trust that things will work in 10 years was that there's things built 10 or 20 years ago that still works today. Performance, uncompromising. I wanted to have no language below C++ except assembler. That's a phrase from the Design and Evolution book. And this is for the domain C++ initially designed for. So for instance, Gilder van Rossum wanted everybody to write code. I don't. I want people, I'm trying to help engineers. I don't want everybody to program the brakes of my car. I want good engineers and giving tools for them. And this is for the many domains where C++ is used. By the way, some of you may heard of Douglas Adams and the Hitchhiker's Guide to the Galaxy. I met somebody who worked for him, and when the people in those stories sit and write code, they write C++. I have it for evidence for that. So this is also the start of some of the games industry. So the very start of C++ was resource management. I wanted constructors and destructors because, you know, if you have something, an object, whatever, you need to get it initialized, you need to establish the invariants, you need to get all the resources gathered for it to function. Otherwise, you get horrible things when you start using them before it's ready. Then you use it, and when you're finished, you have to clean up any mess you have created, basically give resources back. This was in the first week, and it's still the basis of just about everything in C++. Also, I needed to improve the type checking. I was working with C because that's a good way to get to the hardware, but C couldn't do type checking of function arguments at the time. So if you use C and you like the fact that you can say f of int, comma, pointer to double, that's my handiwork. So we wanted to improve the type checking, and we still want to improve the type checking, providing our own types, because we need to write the types that we want in our applications, matching our domain, not the ones that Dennis and I invented. They are at the bottom of things. And every system I've ever seen, large system, is multilingual. We started with C, Fortran, assembler, Unix shell. The idea of building a large system in a single language is strange. And so we started with called C-will classes, those C++ at the time. Lots of simulation projects, much simpler compatibility issues, so that's fine. And C++ was designed to evolve. It was completely obvious to me that I couldn't build the language I wanted with the resources I had in the time I had, and I couldn't do it without feedback. All good engineering relies on feedback. You do the best you can, you put it to use, you see what works and doesn't, and then you make it better. That's engineering. And that's how we have developed C++ over the years. This is how we develop it now. I hope it is mostly by feedback, not by theories. Theory is great when you know what you're going to do, but theory isn't a great guide to what you should want. And compatibility is a constraint. And you should always consider when you build something into the language, does it block something else in the future? That's a hard thing. You get feature composition, and you have to think about what in 10 years we might want and not block it. It's a very interesting exercise. I can't give you guidance about how to do it. I'll just suggest that you do it, because if you're building something that is going to last, and most of you are, think about the future, think about how you can enable the future, how you can slowly get ready for it. And you don't solve particular problems. That was one of the early things I decided. I'm not going to solve a particular problem. Not building a tool for a particular problem. I think about the problem, then I think about what kind of class of problems does it belong to, and try and solve it for that class. And this is actually why C++ succeeded, because I was building for what I wanted, but because I've generalized, my friends and colleagues came and said, well, this is a good solution for what I'm doing. Can I use it too? And so that's how it grew. So yes, it did grow. Here's the evolution chart. It shows from when there was one user. I got my first user after 6 months, and up to somewhere 6-7 million people. There's a chart here that shows when the various features came in. Notice the interesting break in the curve where you have the exponential growth, and then it starts declining, and in theory things should keep declining. That did not happen. My theory is twofold. One, hardware stopped getting faster in a single thread, so you have to actually, good programming became useful again, and also you needed to have something that could be used by many organizations, and all the big organizations building other languages tried to get you to use their language and only their language, and therefore if you wanted to work on all of the platforms, Windows, Android, Mac, etc., you ended up with a language that actually wasn't everybody's, every organization's favorite language, because they didn't collaborate very well. Okay, so the static type system here, we need low-level features to implement the high-level ones. We want static type, good interfaces for checking, and interfaces should have enough information so that we can check them well and optimize them well. And well, I said this before, and here's some examples. Provide equal support for building and user-defined types. And I worked down the declaration syntax should be the same for all type. There should be an underlying memory model. I needed overload rules. I mean, we have overloading from day one. After all, you can say an integer plus a double in C. There's overloading for you. And so we work it. If we build a complex number, we should be able to use integers and complex numbers together, etc., etc. And if you want to do that kind of thing, you need operator overloading. Interestingly enough, operator overloading started not with plus and minus. That's what everybody thinks. Actually, what I found was that I needed assignment and initialization to control lifetimes. I needed subscripting so that I could build containers. I needed parentheses so that I could have objects that behaved like functions, function objects. That became lambdas later. And dereferencing for smart pointers. And then with those, the first operators to be defined was actually the logical operators, because some colleagues of mine were building hardware and they needed and, or, and such. Not the fancy stuff like plus. The world is stranger than you think. So the direct map to hardware, I mean, the memory is down there. You access it. There's addresses that they become pointers. You do composition. If you stick things of the same type together, you can get an array. If you mix things, you get a struct. This is one of the key successes. Got it from Dennis. It's a simple abstraction of hardware. There's no registers or caches or anything like that, but it's an interface in between the programming language world and the hardware world, and it's worked beautifully. And no, it is not math. Math is hard to map. This is a simple map and is key to a lot of the portability and performance of C and C++. And you have to get away from that low level, and that's where you get the abstract. You get the types like a vector with constructors, destructors. They lift the level of abstraction from the, as you see, pointers and size to. You can have initialize a list, you can have assignment, you can have subscript operators that are properly range checked and things like that. So we are raising the level of abstraction, and here I parameterize the vector, because why would you want a vector of doubles? Well, if you're a physicist, that may be sufficient. But the rest of us want vectors of integers, of strings, of chess pieces, you name it. So there I have some examples, a vector of double, some well-known constants, vector of strings, some supposedly well-known language designers, and these things apply recursively. So there I have a vector of pairs of strings and J threads. Everything works there. Constructors gets it built up. Destructors clean up the mess, if there is a mess, which will be there because everybody here grabs resources that has to give back. I really dislike resource leaks. When you build things that runs for a long time or in places where there's no repairman, you really don't want a leak. Space probes and that kind of stuff. And so anything you acquire and give back is a resource, explicitly or implicitly. We do not want explicit return of resources because we know people forget that. We forget that when it gets to scale. If you don't believe it, ask any librarian. People take out the books and they forget to bring them back. This is not a computer science problem, it's fundamental. So every object has a handle in a well-organized system here. You really have to know that it's a resource and handle it. And if we root all the resource handles in scopes, everything works nicely. And so you need to control the lifetime, construction, destruction, copy, and moves. Moves is because copying, as you see in sort of the basic stuff, is fine. But look here. Here's an object, right? Now it's over there. I didn't first make a copy of it and then destroy the original. We have to be able to do this. So that's where the basic model is, and it's complete. We can move objects from place to place, from scope to scope, from thread to thread. This is pretty fundamental. There's the move semantics, the way we always do it. We make an object, fill it with good stuff, and return it. And when we use it, we have to sort of not copy, and the way you do it is you sort of steal the representation and zero out the representation, and it goes away. As a matter of fact, that is a complicated way of doing things. The more clever stuff is to figure out that you are about to move this object, then build it where you want the target to be. And so you don't even get this stuff. So here we have an example. If we use the move constructor and we fill that vector with a million elements, the cost of moving it out is maximum 6 word assignments. Usually we can do better than that. It's dirt cheap, like nothing. And we were doing that even back in the early 80s, but only in C++11 did it become systematically supported and well known. So I assume you know object-oriented programming. A lot of people learned it in school. Even I learned it in school in Simula. But C++ is not an object-oriented programming language. It's a language that supports object-oriented programming languages and other things. It supports it rather well, But I don't like this idea that there's one right way of writing code, one paradigm you have to follow. If you go over decades, the paradigms you're supposed to follow and do exclusively change. I think that you need supporting of the way people, it has to be driven by the problems. And you find the style of code should be appropriate for the problem, not according to some theory. So we got inheritance from pretty early, virtual functions later, etc., etc. And my impression is that most classes don't fit into a class hierarchy. Most classes that fit in a class hierarchy is single inheritance, and multiple inheritance of interfaces is universal in a standard, in a statically typed language, but the types that need multiple inheritance of data are fairly rare. So you go from the most common, which is really well supported, and then through less important areas. And then you get all of these discussions about, say, multiple inheritance, which people are arguing about the 1 or 2% case. That's not the most important. The important thing is to keep simple things simple and efficient. And one of the interesting things was people complained about the C++ model of inheritance for quite a few years, and then a group of Java-oriented people set out to prove that C++'s inheritance were unsafe. They managed to prove that it was sound, theoretically sound. It was 20 years after I deployed it. But anyway, so there's object-oriented programming. You have the classical class hierarchies. You have interfaces. I wish I had called abstract-based class an interface. It's naming is hard, and I'm not very good at it. Then you build a shape on top of it. That's where you add the data, and you build the hierarchies as usual, and then you can use the class hierarchies. I mean, sometimes you need pointer or reference semantics. That is, you point to the interface and you don't know what it is what it is that you're actually doing. So you have the classical example of a collection of shapes, and you want to draw all the shapes. This is an example that I borrowed from the Similar guys. This one is back to the 60s. It's not very new. In those days they used plotters. Now we have screens and things, but it's the same. So here I want to draw all of a drawable sequence of elements, and I go through. Of course, these days I use a range for loop to draw them. Drawing them means that you look up to figure out what type it was and draw it in the appropriate way. That's object-oriented programming. And here I have made the sequence of drawable things as a vector of shared pointers of shapes. Ta-da. Anyway, I said I didn't like the preprocessor. The macros can be usually removed either with constant expressions or with templates. We apply type deduction to get the type right. All of this is properly typed and scoped, not like macros. We have modules, so we don't have to get into the includes and get enormous source files. And we have a source location type in C++20 so that you don't have to use __ capital file _ and that kind of stuff, and then get into the macros. We don't have contract yet. We'll see if we'll get them in 26, but that would allow us to get rid of assert. Compile time computation, we move as much as we can from runtime to compile time. It runs faster, and we don't have to have error handlers for it. We started from the beginning, trying to move things to compile time. It's interesting that constexpr was initially deemed in the standards committee unimplementable and useless. I think we have proved otherwise over the last 10 years or so. Compile time programming any sufficiently simple function can be evaluated at compile time. We can argue about what is sufficiently simple. Theoretically, I can build multi-threading at compile time, but I don't think that would be a good idea. But anyway, it works. It works not just for the built-in types, but also for the types we built. Here is an early example of something I got from an embedded systems organization in Japan. They wanted a compile time integer square root. And so we just stick constexpr in front of in front of the function. The compiler checks that it doesn't have dependencies that can't be handled at compile time. In other words, it doesn't read or write stuff that isn't passed to it as arguments. And so anybody can do square root of 9, but if you want the square root of 1, 2, 3, 4, you will either get it wrong or you'll use a doodle pad, and over the years it might be wrong, and you can read the code better this way, and it's been checked properly, and you get the right result. It doesn't just work for built-in types. Here's something from Chrono. I want statically to verify that June 21st in 2016 is a Tuesday. This program will not compile unless this is true. So you can do this kind of stuff at compile time. And also, one of the things we use it for is suffixes. I would like the MKS system, the SI system, to be represented in the code so that I don't make stupid mistakes about units. And we can do that. We will see if we get the support for this in general in the standard. People are working on it. And again, this is not brain surgery. There's an example down there. Operator literal. If you put an S after something, then a long double with that suffix is converted to the appropriate type. It's a one-liner. It may look strange the first time you see it, but it's not complicated and it is very efficient. So error handling, you need an articulated policy for handling errors. Just writing your code and making up your mind every time you see a problem is not quite good enough. We can have error codes and we can have testing, and that's for when you know that an error is possible and even likely and can be handled locally. So that's obvious. If you're opening a file, you know that sometimes the file doesn't want to get opened or it doesn't exist. So you should check it right where you can. On the other hand, it doesn't work well with constructors, it doesn't work well with operators because there's not a return value that you can check, or you have to pass more values in. And if you try to use error handling based on if then else and error codes for things that you can test, you get ugly and slow code with exceptions. On the other hand, exceptions are for things that are rare, they're exceptional and handled locally. And you usually have to propagate the error up through the class hierarchy. No, not possibly the class hierarchy, definitely the call chain. And failures to check can give termination, not wrong results. And it doesn't work well with pointers, which is what a lot of people's problem with exceptions is. You should not have resources owned only by pointers because you can't do things well in that situation. So with RRI it works. And the alternative is expensive and complicated error code hell. You have to test at every level whether you have an error or the real thing. And that can be painful. If it has to go up 50 calls, this gets expensive. If you have to pass two values all the time, the error code and the real thing, it becomes expensive. So there's a very nice paper by Khalil something or other who proves that exceptions can be used effectively to make code smaller and faster on small embedded systems. Go to the YouTube and see the very detailed talk about this. I've been saying it for years, but I never had the numbers. The numbers now exist. And so here's a little example here, a piece of code. It grabs a lot of resources that has to be given back. It opens a file, which, as I said, you should check immediately. But how do you do error handling for the rest of it if you don't have exceptions? You have to test for about maybe a dozen places. The code bloats, and the opportunity for making a mistake increases. So some of you will use printf. When did you last check the error code returned by printf? Never. But you know, these days with networks and such, the output stream sometimes disappears, and your output just went into nowhere. You really should check your output. But it doesn't happen every month that you have that error. So something has to handle it, and the exceptions were for that. So let's go to generic programming. This is a thing that started in the really early days. I wrote a paper in '81 saying you needed generic programming and macros could do it. I was half right. We needed generic programming and macros could not do it. But I got the right problem. It gives terser code, more direct expression of ideas, which is absolutely key, and zero overhead abstraction, and it's type safe. I chose a marine diesel engine here as the example because I know the fuel injectors in that one is written with generic programming. And see the engineer there at cylinder head number 5? This is an interesting embedded system. It's bigger than most we think about. Anyway, generic programming is pervasive in the standard library. Containers, algorithms, concurrencies, locks, memory management, I/O, the works. It's all over the place. So we started with macros and then wanted to get something better. I outlined the criteria and made the first design. Extremely general, zero overhead, well-specified interfaces, and I could get 2 out of 3. And so I picked the 2 first ones, spent another 20 years finding how to specify precise and flexible interfaces to generic code. This is what's called concepts. It was sort of finished and working in a few years ago, and in the standard 4 years ago. So you have concept-based programming here. I'm sorting a sortable range. You have a vector of strings, I can sort it. I have an array of 128 integers, I can sort it. I try to sort a list of integers, and I can't. Because a sortable list has to have random access. It says so in the definition of sortable range, and well, it gets caught right there. And notice the things that are happening here. We have specified exactly what we want, precisely. And because the compiler knows that, there's lots of things we don't have to say anymore. Type of container, type of element, number of element, comparison criteria can all be defaulted. And the way you specify the interfaces is here's find if. It needs a range. That is something you can go and go and traverse. And the iterators has to be something you can use for sorting. They have a predicate that you can test on the elements, and then you can write range if, and you can do the useful things here. Here, the function object I have specified as a lambda, which is the way you write function objects when you don't want names of things, when it's a simple thing that's only used once. If you use more complicated function objects, give them a name, it's easier to maintain, it's easier to understand. And there's how you define a concept. A sortable range is a random access range. It's in the library. And it has a sortable iterator. It's in the library. As usual, we're programming using other people's work very often in the libraries, so we don't have to invent all of the basic things. And here I am inventing a basic thing. You can also find it in the library, but I wanted to show you how to do it. I want to say that two types are equally can be compared with equality, and it basically says that less than and equal and equal has to return booleans. Boolean is another concept which I happen to have it defined. And I default the second type to the first, so it works with homogeneous comparisons and with comparisons of two different types. And I'm just testing it here. I'm testing that int and double are equality comparable. Yeah, they have less than, they have greater than, fine. Same with just plain integers, of course. And then I try to compare integers and strings. No, it doesn't work. You can't do equals on a string and a integer. So we've always had concepts. This is something that you find in C, and every domain has its concepts. C++ has arithmetic and floating types. The STL iterators, sequences, containers. In math, we have monads, group, rings, and graphs has vertices and things like that. Okay, are concepts essential? I mean, we lived happily with them without 30 years. Well, not always happy. If you've seen the error messages you get from misusing templates, you'll see it's not so happy. It's a problem that had to be solved, and we have now solved it. They are being deployed. They should be working perfectly in all mainstream compilers. Perfectly is probably slightly an overstatement, but certainly I don't write templates without concepts anymore. Modules, something that has been a pain in the neck since the early days. It used to be that using the preprocessor was optional in C. That's a long time ago. Then header files were sort of small and the code was large. Now header files are large and the code is small. The problem is a nuisance. Also, include A followed by B is not the same as include B followed by A. That's a sort of bugs. It also slows down the compilers amazingly. We want modularity. Import A, import B is the same as import B, import A. That means that the code has been cleaned up to the point that we can do really good things with it, like compiling it fast. And so here's an example of a module, and I really hope we'll all use modules almost exclusively in a few years. I want a map printer here, which is a simple example that fits in a slide. And I import a lot of good stuff I need to implement my stuff with. Imports are not transitive, so my users aren't affected by the fact that I grab some stuff, and then I write perfectly ordinary code. If I want to export that operation or type or whatever it is, I just stick the word export in front of it, otherwise it's private to my implementation. And you know, modules are not just for the standard library. Here's an example I borrowed actually from one of the members of the committee. If you include their library, which is for embedded systems, by the way, you get 500,000 lines of code after the pre-processing. Now, our compilers are blazingly fast. It doesn't feel like that because you import all of you include all of this stuff, so they have a lot of work to do. If you use import instead, there's far less work for the compiler to do because the modules has been semi-compiled before that. Here she got a 25 times speed up. Look at the video that's listed there, Contemporary C++ in Action from CPPCon. It's a splendid talk. It shows how to use modern C++ and actually compile much faster than we're used to. I did this little experiment myself. If I do Hello World with IOStream or import the whole standard library, it compiles 10 times faster with the whole standard library. So say there's 10 times as much information in the standard library than there is just in IOStreams, then compilation has speeded up 100 times. Don't expect 100 times all the time, but maybe think about 7 or something like that. It's fast. And so again, modules essential. We have lived with them for 55 years, not happily. This is where people drink too much coffee because they have to wait for the compiler, and the builder, and the linker, and all of this stuff. So basically, we've always known that we needed modules, but getting something like that in, where we are recommending you reorganize a few billion lines of code, is dramatically difficult. The build systems has to be adjusted. The way we package up our code should be adjusted. But I think it'll happen because the carrot here, use carrot, is 10, 25 times faster compilations and fewer bugs. So what's not essential? Most language features are not essential. They are the result of history and probably not as good as we could have done them today with 10, 20 years of hindsight. But you know, we need stability, so we can't just clean up things all the time. But this was the essential things I wanted to show. Concurrency, apologies, I cannot do it. That'll take a whole other talk. Yeah, the matrix was done in C++. That's a bit scary. Anyway, the very first library done in C with classes back in 80-81 was a library giving me coroutines and a scheduler so that I could write pseudo-concurrent, quasi-concurrent programs. So that's back. And what could become essential? What are we working on now? Without compromising the existing stuff. The stuff I'm been presenting here is, in my opinion, essential. That is, if you want to write really good C++, remember these sets of features. We want coroutines again. They are in C++ 20, but the support in the library is not quite up to snuff yet. We're coming. We're getting a more general model of concurrency. It is deployed at scale, so there's a chance we'll get it in the standard in 26. Static reflection, we've been working on ways of doing things that you can do with macros these days, looking at existing code, writing code based on that. I hope we're going to get it. People are working hard on it. I was in different groups this week, but last week, I mean, and they're working hard on it. It looks good, and I would like to see functional programming style pattern matching. It would simplify writing code, simplify selection, and increase type safety. I'm not sure when we might get that. And oh yeah, there's C++ on Mars. So basically, don't get stuck in the 20th century. We are further on, and it's obvious that it's difficult to move ahead, but how? We've been working on guidelines and enforcement of guidelines. So I recommend the C++ core guidelines. You can find them on GitHub. I have meetings with Herb Sutter and a couple of other people every second week. It's something going on, and you can use it today. But we would like enforcement. We would like guarantees. And so we're working on this kind of stuff by saying, first you extend your language with the ideal abstractions, then you can ban things. And I would like to get rid of subscripting of pointers because they cannot be range checked. I want to use spans and range check them. I want to eliminate dangling pointers and things like that. It can be done, but not for arbitrary code. So there's an example of a span. We have a lot of code that says there's a pointer and there's n elements. Well, we have a type called a span, which is a pointer and n elements. But now we can check it. And it's easier to parse, and it's shorter to write code. Make simple things simple. So a really good new feature makes it safer, faster, and easier to write than the old ways. And this is a sort of an example. Invalidation is something we would like to catch. I have a function there. I grab an iterator into a container. I pass the container around. I do a pushback. It relocates all the data. Now that pointer is invalid. We can catch this. Try using the core guidelines. You will catch some of these things. Not all of what we have built are deployed yet, but we know how to do this. So basically, I'm suggesting a set of profiles for the standard that provides enforcement of the kind of guarantees that we would like, enforcement of the kind of code that we would like to write in the modern day, as opposed to old-fashioned code. And there's the model again, with the list of things. And this is what it's all about. Again, repeated. And there's a bunch of references. I'll make the slides available to people so you can click through and find this stuff. Okay. Done. And in case you thought I was talking very fast, I thought I had an hour till I got up here. So I speeded up by, well, a quarter. I once came into a conference and somebody was going on for half an hour about some other language, how wonderful it was. I wasn't prepared. So I stood up and says, well, to maintain the usual speed differential between your language and C++, I'll speak for 3 minutes.
Thank you so much, and thank you for mentioning enforcement. We are going to enforce a very, very brief Q&A session. So we'd like to hear your questions, and the first question will be the shortest one. Who's got a short question? One over there, please, over there, the mic. Can we get the mic over there? Thank you.
Thank you. Recently was a couple of arguments used to invent new language, like C++ library is slow.
I'm having a great trouble understanding
Can you speak
what you're
up,
saying.
please, like very loud?
Yeah, there was, well, it's working now. There was a couple of arguments used recently as an argument to invent new language, like C++ library is slow or C++ is not safe. So what is your recommendation for younger people here? Is it worth spending time inventing new language, developing new language? Or maybe there is another option?
I think I summarized it in this talk. And if you already know how to program, the long answer is the 250 pages of a tour of C++ third edition, which I believe is in Polish also. And that's where you can get it. And don't believe everything you read on the web. And you can write really good C++, really good reliable C++. It has been proven again and again and again. People tend to use examples for sloppy, old-fashioned, usually C code to prove how dangerous it is. Just don't do that.
We've got one question over there. It's a short one, isn't it? Yeah. Promise?
So my question is about, have you considered doing more dramatic...
Again, I don't get it. I'm sorry.
Mic closer to your mouth, yeah, like this.
Okay. Have you considered more dramatic dropping of legacy? I mean, deprecated. More, there are, as you mentioned, there are a lot of things that are legacy, and you should drop it, yeah? Have you considered like putting it not compilable in the next versions of C++?
I can guess what you said. I didn't hear much. C++ is evolving. It was meant to evolve. And certainly the new features don't work with old compilers. And certainly I don't recommend you use absolutely all the new features because they haven't been sufficiently supported. It doesn't, people don't understand how to use them well. So for production code, I deploy with a slightly older compiler version. I mean, I had real trouble understanding what you said, so maybe I'm answering the wrong question.
How about this? How about I propose that we leave it for now as it is. Feel free to grab and stick to Bjarne during the break like Higgs boson to a mass particle. And we're going to take a break, and we need to vacate the room and do our thing. We will continue in about 10 minutes as advertised. Other than that, Bjarne Stroustrup, everyone.
Thank you. Thank you.
Don't forget to rate the talk. You can do it using our app, and we will continue after the break. Thank you. All right, thanks very much for showing up. Don't forget you can rate all the talks using our specially customized app. You will have received a QR code in your emails with your invites. If you haven't got them, you can always scan the QR at the reception desk and rate the talk the way you want it, and you want to give all those talks 5 stars, obviously. Like this one, prepared by our next keynote speaker, Herb Sutter. Now, Herb is an author, consultant, speaker, designer, and co-designer of various ISO C++ features and chair of the ISO C++ committee. He's also a programming language nerd whose focus is on enabling our program code to be both clean and fast. Clean and fast? You must be a magician as well, Herb. No? As you know, we always like to collect fun facts about our speakers, and to do this, we asked Herb about his favorite Star Trek movie, and he immediately said, Galaxy Quest. Just to explain to those who have no idea what I'm talking about, Galaxy Quest is a parody of Star Trek. Anyway, peering forward, C++'s next decade, let's have a big hand for Herb Sutter.
Thank you all for coming. May I just learn a little bit about you just for a moment? So I'm going to ask 3 questions, and if you could cheer to let me know your answers if it applies to you, all right? So Bjarne just showed us that he's been working on C++ since 1979. By my calculations, that makes C++ 45 years old. Think of your age. How many of you are 45 years old or younger? Can I hear you? All right. You know what's next? How many of you are over 45 years old? Okay, fewer, we're gray, but we're feisty. And how many of you kind of like C++? Well, good. Then you probably won't be bored for the next 45 minutes because Bjarne has talked a lot about where C++ has come from and where it's currently in progress of going. And I'm going to take a bit of a risk by going forward to the next decade because I think what we have learned about C++'s trajectory this year is informing us very well for what to expect in the next decade. The usual disclaimer applies. Prediction is very difficult, especially about the future. Yogi Berra. But let's take a look at what is coming, what is in progress, and what it will mean for our next decade. I'm going to talk about reflection, and I'm going to talk about safety as the 2 main topics, but then talk just a little bit about how that helps with simplicity as well. And there's an intersection between those 2. Reflection and safety may seem like unrelated topics, but they're related in timing because they're both starting to land significantly, it looks like, fingers crossed, in C++26. They are related technically, which is probably not obvious, in that both are about greatly reduced undefined behavior, and both of them will simplify what we do. So let's see first, what about reflection? What is it, and why is it going to be so impactful for us in C++? The short definition of reflection is that it lets the program see itself. And generation is to let the program generate more of itself. So usually I'll say reflection is a shorthand for both reflection and generation, because I think generation is part and parcel of it. But I'll often mention both just to emphasize it's not just about reading, it's about also generating more source code. So when we think about generative C++ styles, that's going to be something that we have very little of today. mostly in forms of very obscure patterns, common but obscure, like CRTP. And if you know what that means, you know way too much C++. But we're going to really increase the support that we have for doing this. And because all of this is done at compile time and the program is reading and writing itself, of course, that's very meta. That's what meta means. And so we call this meta programming. But I want to make one big distinction, because if you are familiar with reflection in other languages, this has an important difference. So in Java reflection is important. If you make a virtual call using reflection versus doing it directly, it will be 3 to 5 times slower, because it's runtime reflection in Java. And it's still super powerful. It's still very popular, enables many styles. But this is C++. That's not how we roll. In C++, we are looking at reflection that is purely at compile time. Now, that does not mean that you can't compute something at compile time and then store it in a data structure to use at runtime. You can save the data and use it later. But unless you do that, you pay 0 runtime overhead for using reflection. This is not something that's new. As Bjarne just mentioned in the previous talk, this is part of a 30-plus year arc toward more and more compile time programming in C++. And as we're looking at bringing this into the standard, the very first proposal that aims, if fingers crossed, if it succeeds, if in the next 2 meetings we can do it by June of next year, to put reflection, the first parts of reflection into the standard. That's proposal P2996. We like to talk about P numbers because that's what we do. So you'll hear that number a lot from standards committee members, but that's the first main proposal to add the first step of reflection. So into hopefully C++ 26. Hopefully that will succeed, but that's not the end. So if you look at that and you say, oh, but there's not really generation yet, that's okay, because there are already other proposals to introspect more kinds of things, to actually then cross that dotted line into actually generating code. There are prototypes of many of these available, and I'm going to show a little bit of code, but these are stepwise. Not all of them will be in the first release, but we are going to be building these out, hopefully starting with C++ 26. Now, here's one of many examples. I actually chose a short and simple example from 2996 so that we can absorb it in real time on a slide. But if you're interested, and I suspect many of you are, please go to that paper and you will just search for WG21 P2996. You will find it. It has many examples, many of them intriguing, including a more advanced example of what I'm about to show you. So thank you, Matush, for this example. Here, what we have is a program that is a very simple command line argument parser. And the idea is that I have this struct, my options, and this is going to define what are the command line options that I want in my program. I have a string file name as one option, and it will default to input.txt if you don't write one, if you don't write it yourself. An integer count that defaults to 1. And then in my main line, I'm going to call this parse options function and pass it the type myOpts as a description of what I want my command line parameters to be. Make sense? Now, so far, this may look like normal C++ as we have been using it for years, but there's already something a bit different in how this works, because after I call parse options, it's going to return me an instance of myOpts that has opts.file filled in with a file name, opts.count filled in with an integer count. One's a string, one's an integer. And if you're reading this code and you're starting to think, oh, but I can see how most of that works, but wait, how do I at runtime match a runtime string on the command line that matches this compile time name of the data member? Then you're asking the right question. So here is a look into the implementation, and I'm highlighting just a few key parts to pay attention to. Again, at first, this looks like a normal piece of code. Template, type name, opts, and then there's our parse options function, and it's going to take a runtime span of string views. These are the command line arguments, whatever it is the user wrote on the command line. But notice in this case, the first thing I do is I have this new thing called template for. The syntax might be tweaked, but right now in the prototype where this works on godbolt.org, on Compiler Explorer, this works as template for. And notice that I am iterating over the non-static data members of, and then there's this funny new thing that we just decided a couple of days ago, this is what the syntax is going to be, is this double hat. It is some people are trying to get it to be called the unibrow operator, which is saying, you see this type, you passed me a type. Templates have been doing this for years. Here's the new thing. I am going to reflect on that type, and I'm going to look at the structure of the type. And this is something new. This is something we could not do before. And I'm actually going to have a compile time range for loop over the data members of that type. And I'm just going to go and see, and I'm going to call ranges find if. This is normal C++ code. And I'm going to see if one of the variable names in the type, which is compile time, matches the runtime string the user wrote on the command line. And if it does, I'm going to go, so the type itself is a function input. The structure of the type is a function input in a new way that we haven't had before. I'm going to use this expansion statement, reflect, and use these meta functions, and then I can do error checking, and then finally notice there's this funny thing called a splice operator. What this is saying is, all right, I figured out the command line, the member of the struct that I'm trying to match. That's the command line, switch that the user specified. Take that name, which I just matched the user writing at runtime, stick it in at compile time to the program, because I matched it so I know it's the right one, and try to take whatever the user wrote as a string value for that command line option, and stream it using the normal IO streams into opts.thatName, into that member of the option struct. Now, what this will do, it will do a type-safe conversion, which will also fail if the input is not of that type. Like, let's say that it's an integer, it's supposed to be an integer parameter, but you gave it something that's not, the user wrote something that's not an integer. This is type-safe. We will catch that. And then we can give a nice error message that if you gave the wrong type, we can say so. So here's an example, just a screenshot from this working on Compiler Explorer today, where if the user wrote --count42 and --file name Scott Meyer's Effective Modern C++ PDF, because of course everybody should be reading that book, then we can see that opt.file has been given the string value, Scott Meyer's EMCPP PDF. Ops.count has been given the integer value, 42, which has been converted from a string to an integer at runtime, but we've been matching the struct members to specify the command line options at compile time. And it's type correct, because if you try to say, oh, give me a count of Scott's book, well, what does that mean? That's not an integer. Count must get an integer. I don't know, you mean the page count, the word count? No. You need to specify an integer, and you can say, sorry, count is not a valid int, because this is all type safe. So to find out more, there are a couple of current implementations that are tracking this. One is based on EDG by David van der Voorde, and one is Clang-based by Dan Katz of Bloomberg. And there are other related efforts, including MyCPP Front Compiler, but those first two ones are implementations of the actual proposals currently being progressed in the Standards Committee. So you can find them both on Godbolt. So now let's switch gears and talk about that second topic, about safety. This too is part of what's going to dominate C++'s next decade, because just as we've just talked about reflection and how it enables a whole new method of programming, and where we're going to be delivering parts of it, hopefully starting in C++26 and then over the coming years, it's also going to take us a decade to learn how to use it, to learn what's possible. So I expect to see a spurt of growth of experimentation and learning and really pushing new boundaries in doing things that were impossible or impractical before in C++. And it's going to take us a decade to absorb this, and it's going to be fun to learn how to take good advantage of this new power that we've never had before. But putting safety first in C++ is also kind of a new thing, because we've always taken the view that, well, safety is something you could always write safe programs in C++. But you had to really pay attention. And can we do something to still stay C++? So we're not turning ourselves into some other language, to stay true to our values and ideals and talk about backward compatibility, but still do something substantial about safety. Well, I wrote an essay about this earlier this year. The link is at the bottom. And the actual problem that I argue we should be looking at in the near term is, first of all, parity, not perfection. And what I mean by that, parity means being the same. So there is no perfectly safe, perfectly type and memory safe commercial programming language. There is not one. Now, there are ones that are much safer by default than C++, and we call them memory safe languages because they are substantially safer. And the ways to go wrong, there are fewer ways to go wrong. For example, in Java and C#, in purely safe code, I'm not talking about using unsafe escape hatches, just in safe code, you still can use an uninitialized variable. For example, by doing a virtual call in a constructor, because in Java and C#, virtual calls are deep. Therefore, if you call a virtual function in a constructor, it will dispatch to the derived type whose members have not been constructed yet. And this isn't something where we say, oh, look, they're unsafe too. No, that's not the point. They're definitely safer, a lot safer, and there are fewer ways to go wrong. But they're also not perfect too, and that's okay. They teach their programmers, don't do that. Be aware of that edge case. So it's okay for us not to be perfect either, but we want to get to the same level of safety. That is something we want to do, and where we have to do real work to get it. And there are 4 specific areas that we need to do. This is not excluding other areas. Concurrency safety and other things are important too, but the first 4 main important ones are type safety, bound safety, initialization safety, and lifetime safety. Initialization is part of type safety, but I'm going to split it out especially. But when you look at bounds and lifetime, sometimes you'll hear terms like spatial safety and temporal safety. They mean roughly the same thing here. So why am I saying those are the 4 important ones to look at first? Again, not excluding concurrency safety, but we're interested in that too, but why is that something that we can look at longer term? Because these 4 have 2 important properties. These 4 are year after year after year the 4 biggest causes of memory safety vulnerabilities in the field for security issues, for security incidents. They are what attackers are exploiting. Second, these are the 4 that every single memory-safe programming language does better than C and C++. By definition, if we had parity, roughly the same error count, that it's roughly as difficult to write bugs by accident in these 4 areas as other programming languages, we wouldn't be having a conversation about moving to other languages, because we'd be the same. Now, again, concurrency safety is also interesting, for example. We should be looking for that too after these, because of the commercial languages, the memory-safe languages, only Rust currently tries to give concurrency safety guarantees, which is great, but it means you can be a memory-safe language today without that. So we all should be trying to raise the bar and achieving those things too. Safety, good, but here's what our focus ought to be. And so we've been making great progress in that. We've already, in the C++20 standard, for example, standardized span of T so that we can actually say use that instead of pointer arithmetic because the span knows its bounds. We have started removing safety-related undefined behavior. I'll have a bit more to say about that. And we're working on static safety profiles with mostly static and also dynamic checking where necessary, where we're taking some well-known rules already and moving them to compile time so they run on the developer's machine before check-in. That's important. And of course, there's other work going on, such as -F hardened, and implementations are giving you more security guarantees as well. But it's really important that we're not talking about changing C++ into something else. It is true that we have some pretty sharp knives. Do you feel like you have some pretty sharp knives when you're writing C++ code? Do you have like nicks on your fingers sometimes, some Band-Aids? Yeah, it's a tense chuckle because we've all been there, right? But we need the sharp knives. If you're going to have a Michelin chef, you can't have a Michelin chef who needs to do all sorts of things and then take their sharp knives away and say, sorry, we should only give you safety scissors. Well, they can't do their jobs. C++ programmers can't do their jobs without the sharp knives. And besides which, if anybody came up with a proposal that would try to take your sharp knives away, out of my cold dead fingers, right? Nobody is going to take a sharp knife away from a C++ programmer. The problem, though, is it's too easy to use a sharp knife when you didn't mean to in C++. And to me, that is like having a kitchen that is full of knives that are just lying around on the floor and on the counters, so you have to watch very carefully where you step. And it's like writing code where you wrote something unsafe by accident. You didn't mean to, you were trying to be diligent, but it just compiles and silently runs and doesn't do what you expect and you may not notice. And that's way too easy to do in C++. So today, that's kind of like we say, well, watch out. C++ is performance and control by default. That's where we came from. Safety is always available. So when people say, I can write safe code in C++, that is both true and beside the point. Because it is absolutely true, but it's just very much harder than in other languages. So I propose that what we ought to be doing is staying in the same kitchen with the same knives. We love our C++ kitchen, we love our sharp knives, but just flip that to safety by default and performance and control always available. Just put the knives in a drawer. That's all. That's what safety profiles are for. So that's the whole idea of them, is just take the knives, just put them in a drawer. The drawer is not locked. You can open it anytime you want and take out any knife you want. But now you can walk around on the floor without cutting your toes by accident, nearly as much. Here is something we've already done earlier this year, and this is, between this and reflection, I actually view 2024 as a pivotal year where we have started to make major changes for the first time that affect users broadly. For I think the first time since C++ 11 to that level of magnitude in terms of the impact it's going to have on the way we write code, that starts another cycle, another generation of C++. Now, we all know about undefined behavior. How many of you are super familiar with undefined behavior? Yes, right? How many of you would like to be less familiar with it? Right, so the problem with undefined behavior is anything could happen. And we say, oh, you know, demons could fly out your nose, it could format your hard drive, which is a slight exaggeration because what actually happens is merely time travel and leaking secrets and creating security vulnerabilities. And that is plenty bad enough. So in March of this year, the C++ Standards Committee adopted what may seem like a very small thing, a new kind of behavior. Now, we've always had well-defined behavior. The standard says exactly what this code does, and a compiler has to make it do that. We've had implementation-defined behavior. That is, the standard doesn't say what will happen if you write this code, but your compiler manual must tell you exactly what happens. It must be deterministic. And of course, undefined behavior. Well, we've now got another one of those called erroneous behavior. This may seem small, but I'm going to explain why I think it's really powerful. It is well defined as being just wrong. And let me just walk through that. This means it is something that is legal C++ code, but we say, yeah, even though we let you write that in the standard, it is wrong for you to write that, and we are going to officially take note that that is wrong. And we're going to say it must have a well-defined result that depends on your compiler, but it can't be undefined behavior. Now, to give you an example of why this is so important, this means we can take things now that were undefined behavior and make them erroneous behavior, and just by doing that right away, there's no time travel, there's no leaking secrets for that. And the first place that we adopted it, this general tool, was as of C++ 26, reading uninitialized local variables is no longer undefined behavior. If you just take your existing source code and recompile it with a soon-to-come C++ compiler, C++ 26 compiler, it will be safer. I'm going to come back to that because that's a super important adoption story. So what does a C++ 26 compiler do instead? Well, if you write an uninitialized local variable, it is now required to write something. You can't rely on what it's going to be, but it's not going to be undefined behavior. It's not going to be whatever bits were there before. It's not going to be time travel. It's not going to be an exploitable security vulnerability. And you get that just by taking all your million lines of code and just recompiling in C++ 26 mode, and you get less undefined behavior and more safety just by recompiling. That is a super powerful story. So here's an example from the screenshot from Godbolt. I've got two functions, and I call F1 and then I call F2. F1, among other things, puts a character array on the stack, which, oh, it happens to say secret. Maybe I don't want other people to know what that secret is. So then I just return from F1. Okay, what does that do? It pops the stack. So now the stack space is not used. But what's in that memory? It's not been overwritten, right? So it's still sitting there. It's now in deallocated memory, deallocated stack memory, but that still contains the secret. And then I call this other unrelated function that just happens to be called next in this particular call site, and it has, look, an uninitialized local variable, just happens to be the right size, but it could be a bunch of ints or something else, and it will see by default the bits that were already there because you didn't initialize it with anything. If you print this local variable, which has nothing to do with this one, today the comment says this likely prints secret. It prints secret on GCC. It prints secret on Clang. It prints secret on MSVC. That is not good in a world where software security and software safety are important, because this is a form of memory unsafety. Take that same code, just recompile it with a C++ 26 compiler, and today, even before C++ 26, on the right-hand side of the screen, you can see the switches you can use on GCC, Clang, and MSVC today to get the same effect. And that just goes away. I have not changed the source code. All I did was recompile it with, today, these non-standard switches on the right, and in the future, with no special switches at all, just by recompiling it in C++ 26. Now, I want you to think about what this means. Quantitatively and qualitatively. Quantitatively, this automatically eliminates some fraction. It's not a majority, but is it like 5%? I don't know. That's still a large number of security vulnerabilities and other bugs. Just automatically eliminates them. That's a major step forward. But qualitatively, how do I deliver it? Like, if any of you ship a product, how many of you have ever in your careers shipped a product and been sad when customers didn't adopt it as fast as you would expected that they would? I see a few hands. Like, that's happened to all of us, right? When we design a new product, even if it's the next version of an existing product, we have to pay attention to adoptability. How easy is it for customers to use our new product, to use our new feature? This one is delivered in a way where all I do is take my existing code and recompile it, and it just gets safer. That is the holy grail adoption story. Zero manual code changes. I just take my existing code, compile it in C++26 mode, and it has less undefined behavior. It is safer. And this is just the first step, and we're going to be doing more of these things. But I love to see how the committee has shown it is serious, not just about improving safety, but doing it in an adoptable way. That's not some ivory tower, oh, make all these changes to your source code and then it'll work. Like sometimes that's necessary. I don't mean to disparage that as always being ivory tower. Sometimes that's necessary. But when we can do better, everybody is so much better off. We get our features adopted more, users benefit more, and we improve the world's C++ code and make it safer. So one of the major efforts happening that you'll see entire other talks about is the safety profiles framework. We had the first set of safety profiles that came into the main evolution working group just a few days ago last week. And so if Bjarne and I can do, and helpers can do a whole lot of work over the winter and sacrifice our winter break, maybe we can start getting some of that even into C++26, because we believe it's an urgent thing to start getting type and memory safety profiles. Think of them as warning families, as a set of rules enforced at compile time. They guarantee that certain kinds of defects just can't happen if your code compiles successfully, and to make it easy to opt in and opt out, and to be selective and incremental about that. Many of these rules are rules we already know, but we want to shift left. That is, we want to take them from maybe some post-build static analyzer and run them at compile time, typically in the compiler, like a warning family, but also with a view to adoptability. To the extent possible, I'm proposing that we get some of the benefits of profiles, at least just by recompiling our code. So much more detail on that is to come. And finally, let me just give one example, because there isn't time to go into I have quite a few examples of how both reflection and safety will help with simplicity. But as we're already talking about safety, let me give just one example. And again, I want to draw a line here between what the standards committee has approved and what I personally am proposing. However, what comes next is something that I am personally proposing that just a few days ago, for the first time, the standards committee seems to like. So it still needs to be approved, but it's already partway through approval, and I think it's something that will help us. So let's start with reflection. So we're going to talk about safety and simplicity, reflection, and then safety. One of the things I'm proposing is a small but important syntactic sugar, so that if we write this code, which we can already write in the P2996 prototypes, that it will let us declare classes. So we're write classes to say, hey, I'm not just writing any class, I'm writing an interface, I'm writing a value type, I'm writing a container, I'm writing a proxy, those kinds of things. And to have a syntactic sugar so that the code on the bottom is merely sugar, but important sugar for the code on the top. So the idea is today we can write an interface in C++, an abstract brace class like this, but we have to remember most of those lines. And it would be nice if we could just say, hey, here is a meta function which uses reflection and generation to say, take the ifoo that I wrote on the right-hand side, just take that source code and generate all these defaults, generated functions, and checked constraints. Make my functions virtual and pure virtual by default. Declare my pure virtual, declare my virtual destructor if I didn't already. Make sure I'm not copyable, and force a rule like that I don't have data members, because an interface shouldn't have data members. This makes programmers' lives simpler. It also makes tools simpler. So if you just look at, say, Qt. Qt is one example of a system where we have to have extra annotations outside the source code today that we could get rid of in the future using reflection and generation. The details are in my paper P707. But if we could write the code on the right-hand side, which I showed first on stage at CPPCon 2017, 7 years ago, and is now getting real, not only does that mean our code is simpler, not only does it mean our code is more robust because we have fewer ways to go wrong because the boilerplate is being generated for us, but also our our build tool chains can get simpler. Ideally, we could get rid of side compilers that parse and process the extra annotations and put it all inside the single C++ compiler using reflection and generation. So not only is our source code simpler, but our build systems could be simpler. Now, this isn't going to happen in year one, but this is an evolution that I can see happening over the next decade, and I know that vendors who have these build systems are just waiting for this. Similarly, in COM at Microsoft, you have these extra IDLE-style extensions. It would be nice to be able to avoid all that boilerplate in the side IDLE language by just declaring our intent and doing the equivalent using reflection and generation. And that gives us a much simpler build model than either C++ CX or C++ WinRT. And people are doing this themselves. Here's an example from Benedikt Hegner and Axel Naumann from CERN, where they have a YAML script that generates 5 related C++ classes from every class defined in the YAML. And they could simplify their tool chain as well. When I showed those examples 2 months ago at CPPCon, I gave that talk. It was over. Finally, I could relax a bit. I could stop worrying about my slides. The next time, so I went to my room and relaxed. The next time I left my room, next morning, I thought, okay, I'm going to go down and get coffee. All right. So I walk out of my hotel room, start walking down the hallway. Between my hotel room and the elevator, I met a conference attendee who said, hey, great talk. I can't wait for reflection. You know, we have one of those code generators, those side code generators in our team that we use to generate C++ source code. This, what you described, would let us get rid of that. We would love that so we wouldn't have to maintain that thing anymore, and we'd have a simpler build model for our project. Oh, hey, that's great. So he joined me. Elevator doors open, we get in, doors close, we go down partway. The elevator doors open, another person comes on, neither of us knows, says, oh, hey, I liked your talk yesterday. Do you know that we have at our shop a custom code generator that could... And in Berlin a week ago, I asked for a show of hands, how many people have that at their shop? And something like two-thirds of the people raised their hand. How many of you in your current shop have something like a code generator that is generating C++ code for your project? Yeah. Don't tell me that people aren't aching for reflection and generation. Do not expect people to take 10 years to adopt this feature. This will be adopted like hotcakes. And this is C++'s next decade. It is going to dominate, I think, our next 10 years of C++ by making things easy that are hard today, but more importantly, by making things possible that are impossible today. You know, I gave the example there of example of C++ CX. I was the lead designer of C++ CX, which was a set of non-standard extensions to C++ in the Microsoft compiler. I was also the designer of C++ CLI. I led the design team for that, non-standard extensions to C++. I've been saying since that 2017 talk that part of my motivation for pushing for reflection and generation in the language and metaclass functions is because I don't want to ever have to design C++ CLI or C++ CX again. I know what it takes to do it. The reason we did it was because we couldn't express all that information in the C++ source code. I want to be able to write it all in C++, and I couldn't 15 years ago. But soon we will be, 20 years ago for C++ CLI, but soon we will be able to do that. And finally, one note about how safety can simplify our code. And this is the adoption story I was talking about. So this is the feature I'm proposing, but that just a few days ago, the Standards Committee started showing some interest in, so I am not advertising that this is for sure in C++26, but fingers crossed, there's a chance it might be. And I've implemented this in my CPP front compiler as a proof of concept. Now imagine in your source code, every time you have a subscript expression of the form A subscript B, right? If A is a container that supports std size, and if B is an integer, at the call site, right there in that subscript expression, the compiler can, and CPP front does by default, generate a bounds check. And I happen to also have implemented a version of the C++ draft proposal for contracts, and a violation is reported through violation handling. We can do that other ways, but that's what I happen to have implemented. But what's the benefit? Because often when we think of bounds checking, like a bounds checked span, I want a bounds checked vector. But if you do it that way, if you do it intrusively, where every container and every type has to implement bounds checking separately, I got to wait for my library vendor to do it and to ship me a new one, a new library. It probably won't have an ABI issue, but it may have maybe skating on that ODR line, like having an assert in the body, where yeah, the two functions, safe and unsafe, if they're built with and without checking, aren't the same, but close enough. Comdat folding can make a squint and make it okay, so it's not a violation. I don't have to worry about any of that stuff. Furthermore, because this bounds checking is done at the call site, as soon as I implemented that, ever since I've implemented that, I've been using the GCC standard library, the Clang standard library, the Microsoft standard library with full bounds checking for everything for 2 years now, and it's great. I have bounds checked span. I've been using it for 2 years. It's great. Bounds checked vector, bounds checked ranges, bounds checked views, and you know what else? Bounds checked Qt, non-standard Qt containers that support std size, because that is a well-known idiom that many third-party container libraries also support. And it just works. I just compile the code, and I didn't have to get a new library. I didn't have to wait for to update the standard. And so my proposal, which I hope succeeds, and we're going to work over the winter on the initial set of profiles, and this is one detail that's in that paper. I hope that maybe for C++26, like holding my breath and crossing my fingers and toes, that you might be able to recompile all your existing code with the bounds safety profile on and get full bounds checking for all your subscripts. Now, it doesn't check your iterators. Iterators are harder, and that can be an ABI break. But all your subscripts, that's already another huge step forward. And it's important because of those four main safeties. Remember, type, bounds, initialization, and lifetime safety. Bounds is the easiest, and it's the most important to make progress on, because in like the top 4 or 5 security common weakness areas that attackers are exploiting, out of bounds read, out of bounds write. They're always in the top 5. They're the worst pain point, so it makes sense to start with that. So here is how I live in CPP2 right now with either of those two definitions of A. Uncomment either line, maybe int as a C array or int as a std vector. I actually wrote code like this: print A sub 1, print A sub 2, print A sub 3. You see the problem, right? Off by one error. I'm not going to ask for a show of hands how many of you have done this, because we all have. And this is what happens today. So this is a screenshot of what happens if I compile this in the CPP front compiler and the Microsoft compiler. I get exactly the source line, if the source location header is available, where the problem is, the function name, bounds safety violation, out of bounds, attempted access at index 3, the actual range is 0, 2, and this is not hardwired to the Microsoft compiler. The same thing happens with GCC 14 and, on Red Hat, on Fedora. And the same thing happens with Clang. This is something that we could, a taste of the kind of thing that we could deliver in the standard to make our code simpler, our tooling simpler, through reflection and safety improvements as what I see are the two big drivers of our next decade of C++. So I'm excited about C++. I really think that this was a turning point year because we've been talking about safety for a decade. The core guidelines are a decade old. We've been talking about reflection for 20 years in the C++ committee. But this is the year that it's starting to get real. This is the year we put erroneous behavior and eliminated uninitialized locals in the standard. This is the year that we design approved reflection for the standard, both for C++26, and hopefully they'll both get in. We are starting to finally see these proposals land, and this is going to create a beautiful new decade, open up a new, fresh era of C++. Bjarne, for C++26, he made the point that, or C++11 rather, when C++11 came out, he said, you know, there's been so many usability improvements here that C++11, even though it's fully compatible with C++98, it feels like a new language. I think we're about to do that again, and to make C++26 feel like a new language. And then just as we built on C++11 and finished it with C++14, 17, 20, the same thing with this generation. That's how I view it. I'm very hopeful for a bright future for C++. Our language and our community continues to grow. And it's great to see us addressing the problems we most need to address. So we have an answer for safety. We have an answer for simpler build systems and reducing the number of side languages to make C++ work in practice. And I'm looking forward to the ride for the next decade and more. So thank you for your time. We have time for a couple of questions, and then we're going to go to a break. Shall we take a couple of questions? You can see better than me who's got their hands up.
Feel free to raise your hands and ask questions, but before that, I think this talk and the author and the speaker deserves a nice applause.
Thank you. Thank you. Yes. Yes, sir.
Hi, thank you for your presentation. Is it on? Yeah, there we go. Thanks. I had a question about the advent of erroneous behavior in C++. What will be the runtime cost of losing undefined behavior? And is there a case-by-case basis on which I can re-enable undefined behavior?
Excellent question. So every time that we put something in the standard that could require an overhead, you will always have an opt-out. In this case, if you want to opt out, you can put the uninitialized, no, actually, I keep wanting to call it that, but we renamed it indeterminate, the indeterminate attribute on that variable, and you'll get your glorious undefined behavior just like you always had it. Oh, great, he's going, yes, fist pump. That shouldn't be your default reaction, but it's okay. We're going to make you type it to get it, right? But you can, remember we said we're not taking any sharp knives away from programmers? You, sir, have your sharp knife,
yeah,
but you just need to write the attribute.
It's a good idea.
So one thing I didn't mention here is one of my papers that got encouraged, and I have a lot of work to do between now and the February meeting, if I want to get some of this in C++26, is I actually proposed that we take a stab at taking all undefined behavior that's safety related, which pretty much is all undefined behavior, and provide a way to turn it off by default. And in case you think, oh my goodness, that's a pipe dream, that's scary, hear me out. A, we already do it in constexpr code. How many of you were paying attention or already knew when Bjarne said on the slide that constexpr code has no undefined behavior? Yeah, this is a little known secret. We've been secretly smuggling an entire large amount of code that already in C++ that has no UB. Like literally, there's more and more constexpr code. It is zero undefined behavior already, okay? But that's at compile time because you basically run an interpreter and interpret everything. What about at runtime? Profiles comes in because profiles give you a way to opt in and out. So here, my proposal is take all of the undefined behavior that we already ban in constexpr code at compile time. And for each such case, also turn it off by default at runtime in one of two ways. If it's cheap enough, only if it's cheap enough, turn it off by default in the whole language, just like we did with uninitialized locals. And you still have an opt-out if you want it, right? But turn it off by default for everybody. But you're not going to do that for signed for signed overflow, right? Like no, not even C# turns overflow checking on by default. They can't afford it either. So for the things that do require overhead, and that's a poster child, is overflow, disable it by default in a safety profile. If we can do that, then we have the story that you compile all your existing code in a C++ 26 compiler, hopefully 26 or whatever C++ future compiler, with safety profiles enabled, and it has no undefined behavior. Now, it may be slower. You may need to opt out of a bounds check in a loop or whatever, right? But I think this is important because it's pretty cheeky. It's pretty audacious. I don't think anyone expects C++ to put a serious dent in undefined behavior. Never mind actually have a plan to get rid of it. Now, I need to prove this out, but I have a dream. And that dream is that I want to prove out in the next year, not in the next decade, in months, not in years. So, but you'll always have your opt-out, sir. You will always have your sharp knife. You will not lock your drawer. You can always open the drawer.
That sounds very helpful. Thank you.
Yeah.
Thank you so much. One question over there, please. Not far from the camera.
It's coming from your other side.
Thank you.
Hello. Thank you for the talk. It's working. Thank you for the talk. I really appreciate the effort for simplicity, but I cannot stop feeling that this syntactical legacy seems to still holding you back, or us back. And the introduction of this double hat operator is like really nerdy, and by heart I love it. But on the other hand, I feel like one day we're gonna wake up and think that, oh no, we're writing in Perl. So what's your take on that?
Sure, and I'm going to not throw pearls before, never mind. There's too many Perl jokes. Your code will not be littered with reflection operators. You will be able to write powerful libraries that use reflection, and then you just use the libraries. Like that command line library, the call site saw no reflection at all. It just called a template. It just passed a type. The implementation got to be powerful on steroids like you've never seen before. It's the Arnold Schwarzenegger of implementations, right? The 1970s, 75 Arnold Schwarzenegger, not the 2024 Arnold Schwarzenegger, right? He's pretty good too, more facial hair. But it'll be in libraries. My other answer to that is, can we keep adding to C++ and make it simpler? And the answer is yes, we can, if we're careful to add features that let programmers directly express intent that they couldn't before, so they can now express what they want to do rather than how to do it. And a poster child example for that is the range-based for loop. Every single one of us could write a range for loop by hand. Iterator equals begin, iterator doesn't equal n, plus plus I. You could do it, but it wasn't declarative. The compiler couldn't see or the human reader couldn't see just reading the first line of the loop that it visits every element once. The range for lets you directly express your intent. Yes, it made the language a bit bigger because we added a language feature, but it made C++ source code simpler. It made it faster because now compilers can see that you've expressed your intent, and just looking at the first line can hoist a bounds check out of the loop. That's faster. It doesn't have to analyze the loop to see if you're only incrementing and checking end every time. It doesn't have to work nearly as hard. It's features like that. And of course, we have to be careful not to add features that only do this one little thing and it's complex and doesn't fit with the rest of the language. We definitely have to avoid that. But to the extent that we take things that programmers are already doing, but they're doing it manually, and we let them express what they want to do so they can, that's what metaclasses are all about. So I write less boilerplate and express my intent directly. C++ code can keep getting simpler even as the language does grow. Yeah.
Any more
all right,
questions,
well, thank you
please?
all.
Yes, one over there.
Oh, we're going to take another here. Right on the aisle. That's very convenient.
Yeah, thank you. So one direction is to extend C++ and the features, but another direction is, which you partly follow, is CPP front and other sort of alternative implementations or simplified implementations of C++, like Carbon language from Google. So what is your opinion about that direction?
So in a nutshell, in another talk I've called this if you're going to make like a 10x improvement to an existing thing, I've called it the TypeScript plan and the Dart plan. So both of TypeScript and Dart, the reason I say this is not to be pejorative about, because Dart had other issues that were political and stuff, but I just mean technically that both tried to do a major improvement over JavaScript, right? One of them competed with JavaScript, and that gave Dart a lot more flexibility in being able to do things differently, but they didn't coordinate with the ECMAScript committee. They did their own thing, right? Which, that's a valid technical choice. It gave them more design freedom, and they could do things they couldn't do otherwise. TypeScript decided to be cooperative, pure extensions to JavaScript. They work with the ECMAScript committee. I don't know if how many of you know this, but many current ECMAScript features that are standard ECMAScript were TypeScript features. So TypeScript was not just some competing language, it was contributing back regularly to the main language. That's what I call the TypeScript plan. Carbon is great, but I have not seen a single proposal from those people for ISO C++. CPP front is almost nothing but proposals to ISO C++ that I'm proposing for today's C++ syntax. Nearly, like most of my papers in the last decade, even before I announced CPP front and CPP2, came from that work, because I've been doing that work for 9 years now. Having said that, there are a few simplifications that you can only do by actually having a simpler syntax, and so I also have an experimental syntax that's sort of an alternate syntax, but that's still, you write a class, it's still a C++ class. One for one. You write a function, it's still a C++ function. There's zero friction, seamless interop, no thunking, no wrapping, no marshalling, right? It's still C++, but a different skin, like a different syntax. You only need that to get, you know, some simplifications like the simpler grammar and context freedom and order independence. But most things, including the safeties, including about half of the simplicities, including from parameter passing and meta classes, can be applied to today's C++, and that's what I'm trying to do. In fact, I don't know if I'm going to have any time to do work on CPP front for the next 2 months, because the ISO C++ committee just approved so much work for me and Bjarne to do that we've pretty much already promised to cancel our holidays between now and we were not making that up. We actually said that. There's always Christmas 2025. Because the feature freeze deadline for C++ 26 is just a few months away. In June is the feature freeze deadline for C++ 26. If anybody wants to get anything in, they better be working hard this winter to get those specifications ready. And even then, you know, fingers crossed, it depends on if the committee agrees that it's baked enough and so on. But I think the main difference is, are we contributing to improving ISO C++? Or are we doing our own thing? Both are valid answers. You get more freedom if you go do your own thing. But I think it's super important. And why am I spending all this time in ISO C++? Not just because I'm some C++ lover on a fanatical level. You may accuse me of that too. But it's just because I want to have an impact. I'm a user of this world's society and civilization. I use this world's banking system. I rely on this world's hospital system. I rely on this world's power grid. And damn it, I don't want that compromised. I want it to harden it against attack. And if I put all my energy into some new programming language, I will have some impact, but it's going to be much smaller because I can only write so much new code. If I can find a way to just recompile, that's why you keep hearing me say that, to just recompile the billions of lines of C++ code that exist today and make them even 10% safer, and I hope to make them much more than that safer, I will have had an outsized effect on securing our civilization. And I don't mean to speak too grandiosely, but look at all the C++ code that needs fixing. If you can find a way to do that, it will have an outsized impact and benefit to society. And that's why I think it's important, because C++ is important. And not leaving all that code behind and helping that code too, as well as new code, I think is super important. And that's kind of my motivation. Does that make sense? Yeah. I'm sure we need to take a break now. Thank you all for coming and listening to these talks, and you'll enjoy the rest of the day too. There's a whole bunch of great speakers coming.
Herb, thank you so much. Once again, Herb Sutter, everyone.
Thank you.
Feel free to entertain Herb with more of your questions during the coffee break. Other than that, enjoy your break, and we will continue at 11:15. 11:15, please, everyone. Thank you. Okay, welcome back. Now, a little announcement before our next talk. At the very beginning, we're going to need your smartphones, so could you just take them out and have them ready at hand, because we are going to need them, all of them, in just a moment. I'd like to introduce our next speaker, Phil Nash. And Phil is the original author of the C++ test framework Cat2. He's also a member of the ISO C++ Standards Committee, organizer of C++ London, as well as co-host and producer of CPP Cast. He's previously worked in finance, mobile and development tools, but recently became fully independent, offering training courses in, of course, C++. More generally, he's an advocate for good testing practices, complexity reduction, and correctness. Now, Phil also has an artistic side and has been known to put his talent to the art of songwriting. And he even created a piece on C++ built systems. So let's have a quick listen and a quick look. And feel free to take your phone and switch on the torch. Thank you. And wave along. And here's the piece.
When I was young, I'd never need to use Conan. Make config was just for fun. Those days are gone. I built myself. Don't want your lips. I built myself from the source.
The best developer among singers and the best singer among developers, Phil Nash.
I'd never need to use.
Is that going to stop? Well, thank you for that. That wasn't my idea. Welcome to Modern C++ Error Handling, where I won't be doing any more singing, you'll be pleased to know. So I am Phil Nash, as you heard in the introduction. In fact, it's covered most of the things that I would normally have said. But I will just quickly do the logos. Although I will first of all say, I'm a regular conference speaker. I think I recently counted, I've done about 200 conference and meetup talks, which is far too many. You shouldn't learn by my example. But this is my first time at Code Dive, so thank you for having me here. Can tick that one off now. So the logos, as you heard, co-host of CPP Cast. Who listens to CPP Cast? It's a bit hard to see in this lighting, but I think that's everybody, just for the record. Just in case not, if you listen to podcasts, you should definitely check out CPP Cast. We've got one of the original co-hosts in the front row here as well, who'll be doing a keynote later. That's Jason Turner, of course. Shaved Yaks is my own company. I went independent earlier this year, as my intro said. So I now do training, run some other conferences as well, and I'm writing software. But just recently, I've also started doing some work with Undo as a developer advocate. They do time travel debuggers. I'm not going to talk about that now, but if you do want to hear more about time travel debugging or thread fuzzing, do catch me afterwards and we can talk more about that. But we're going to talk about error handling today. And I've put the modern C++ prefix on there. And it's a very deliberate choice. It's not just for the meme. Because I've actually done a couple of talks on error handling before. Both pre-pandemic, both pre-C++ 20, which is significant because both of these talks were quite forward-looking, especially the second one, looking at things that weren't in the standard yet, that were going through the pipeline, and some that were even a bit further off. Which was really interesting at the time, but now they're a bit dated because some of those things haven't really panned out. Some have actually made it into the standard, and they look slightly different to what I talked about then. So I thought it was time to do something updated. What we can actually use today, what we should use today, how that works, and mix in a little bit of new stuff as well. So that's really what this talk is about, bringing us right up to date. So let's get started. Now this talk is divided into two parts. This first part is going to be the longest part. A series of total disappointments. There's a couple of little minor jokes in there, but the disappointments word, it's not something I've made up, something that's been around for a few years. And it's this idea of an error path that is predictable. You know that it can happen, you're just a bit disappointed when it does. But you do need to write code to handle it and maybe do something else. So all sorts of things fall into this category, and we're going to cover many of them in this section, including exceptions, but also error codes, and as we'll see, optional and expected. So because this material has a lot of code in it, it can get a little bit dry. I asked ChatGPT to generate me a whole series of robots that are going to help guide us through this. So look out for those. Here's our first one. And we're going to work on this example. Very simple function, parseInt, takes a string view, returns an integer. You can sort of guess what it's meant to do. And I put in a very simple, simplified implementation. Don't get too distracted by that. It's just slideware. But it does show us that there is a couple of paths out of this. And you can see there's a couple of return statements in there. There's not really any error handling in this, at least not yet. That's what we're going to add. So you can probably see there in the middle, the first non-numeric digit it finds is just going to return out with whatever it's got so far. Let's see what that looks like in practice. So I've got a few different values we're going to pass in. We're going to see this a lot. So we're going to pass in the string 42, of course, and that's going to parse correctly to 42. If we say 42x, because it stops at that first non-numeric digit, it's just going to return us the 42 it got so far. If we start with the x, then it just returns 0, because it didn't accumulate anything, but it started with a 0. Now that sounds pretty useless. Bear in mind, this is actually the behavior that IO streams gives you by default. You stream a string in and then try to stream an integer out. You'll get a 0 if it didn't actually manage to parse anything. Can actually be useful sometimes. That might be what you want. But you can't distinguish that 0 from an actual 0 that was in the string. Usually you're going to want to do that. So what can we do? Well, one thing we can do is actually to write a separate function whose only role is just to validate that string. Now, you might think that's a bit silly. No, we should do it all in the same function. We'll get to that, but there are cases where this is actually appropriate. Because you don't always actually want to parse a string. You just want to tell whether it is an integer. So it can be worth having this anyway. But we will address the redundancy in a bit. So all this is doing is just finding if there's any non-numeric digits and returning false if not. So here we have some error handling. Well, really, it's the purpose of the function, but we're just using a Boolean. That's completely appropriate still. If you just want a yes, no answer, is this thing or not, Boolean is perfect, of course. This is modern C++ error handling, so I'd be remiss if I didn't bring no discard into it. Not as useful here as it is in some other cases, but do get into a good habit of using no discard on functions where the return value is actually really important. So we'll put no discard in there. I'm not always going to use no discard or const or no except or any of the other things that might belong on some of these functions. It is slideware, but I will try to remember to put them in where it's appropriate. All right, so in usage, we can write some code that just calls it int, takes a different path. Nothing too surprising here yet, but just to show you, that's what we're going to get out of that. Okay. Now, the problem with this is those two error cases, the one where we have some initial numeric digits, and we do actually parse a string out, potentially, and the one where we start with no leading numeric digits. We can't distinguish between the two with the Boolean. So we could change that to an enum, of course. This one just three states, it's fully numeric, starts numerically, or it's fully non-numeric. That's really the only difference we're making. Again, pretty straightforward. But now we've distinguished between those two cases. Great. Okay. All right, let's get to that redundancy, because we're doing all the same work again that we're going to do in parseInt. So calling this and then parseInt, doubling the work, doubling the implementation. We don't want to do that here. So what can we do? The trouble is, of course, with this parse status or the Boolean, that's sort of blocking the return channel. We're already returning something, so we can't return the actual value anymore. We have techniques to work around this, even some really old ones. Out parameters. I'm sure you've all used out parameters in the past, usually taken by reference. So one of those return values, instead of returning, we'll pass it in, we can set it in the body of the function and return. This works. It does the job. We've done this for a long time. I'm sure still sometimes can be a case for it today, but probably not too much anymore. But it does the job. Actually, the biggest problem with this, for me, I think, is that it prevents sort of functional composition. We can't really take that return value and then pass it into another function. We have to store it into intermediate values. Just a very, very brief mention, another older technique, setting a global variable like erno. But this is not really how you use erno anyway. It's got all sorts of problems. Don't do that. We won't discuss it in too much depth. The first real solution, not particularly in modern C++ these days. Exceptions have been around for a long time. Fallen out of fashion a bit in recent years, and I've talked about that before. But still, the default choice for error handling is C++, and a very good choice. Solves all the problems we had. Doesn't interfere with the return channel. Doesn't change the signature at all, in fact. And it shuffles all the error handling off to the end. Very low, maybe zero overhead on the happy path. Really good choice. So I want to be clear, because we're going to talk about lots of other different options. Exceptions are still a really good choice if you can actually use them on your project. A lot of projects can't. Some justifiably so, many not. But if you can use exceptions, they are still a really good choice. And just to address some of the criticism against exceptions, do watch Khalil Estell's CPPCon talk, C++ exceptions for smaller firmware, which sounds like a contradiction, but, well, watch the talk. I won't give it away, but he basically says that most of this overhead we can get rid of. So if you thought exceptions were too expensive, watch this talk first. That's all I'm going to say about exceptions for now. They'll come back briefly a bit later. But modern C++ error handling. We get to C++ 17, we got stood optional. We've had that for a while now. I'm sure most people are familiar with it. I won't spend too long on this, but let's just see what that example looks like if we use stood optional. So now our return value is stood optional of int. And in the error return case, we just return an empty optional. Otherwise, we return the actual value. And in usage, behave a bit like a pointer. We can test it in an if statement. We can dereference it if we've got the value to get the value out. And otherwise, we know we didn't get the value for some reason. So pretty nice, actually. Nice, clean way to address this. And actually, one of the problems with exceptions, the actual problems, is it's not very good for control flow style error handling. And sometimes that's what you need. A function like this, where we just maybe want to test whether a string contains an integer, we don't really want to use exceptions for that. So this is actually quite a good approach. But we've taken one step back at the same time. We've lost that ability to distinguish between the different error cases. So good start, but can we get back that additional ability? All right, move on to C++ 23. Now the current standard, as of quite recently, ironically. We have stood expected. Much newer. You may have heard of it. You may have even used it. But it's still going to be a little bit less familiar to most people. So we'll spend a little bit longer on this. So stood expected actually looks very similar to stood optional. The only real difference is we've got a second template argument, which is an error type. Now, I've used an exception type here, stood runtime error. Don't be distracted by that. You wouldn't normally do that. And I actually regret putting that in the slides, and I thought about changing it later, but it's actually for a load of slides, so we're stuck with it for now. But it does show that you can do that. So In the error case now, we can return 2 different exceptions depending on whether it's the first digit or not. And then we can test that in our usage. So in our test usage code, the happy path is exactly the same as optional. We can test in the if statement, we can dereference using the star operator. But in the error path, we've now got this dot error. It gives us the error object. In this case, it's an exception, so we can do dot what on that to get the message out. Again, I probably would have written this with that enum that we saw earlier instead of an exception type. Don't be too distracted. But that solves the problem. It's actually pretty good. Nice, clean, easy to use way to handle error cases or unexpected cases more generally using stood expected. The problem is, and it breaks down a bit, and this is true with stood optional as well, when you start to scale up, when you have multiple bits of code that all have different types of error handling using stood optional or stood expected. This one, we've only got 2. And you can see it's actually a lot more complicated. I'm going to just walk you through this. Don't worry too much if you don't follow it all. It's not that complicated, but it's just lots of little bits. So let's zoom in a bit. So we actually start on line 3, which is part of the problem. We're calling parseInt, same parseInt as before, returns a stood expected of int and stood runtime error. We put that in an if statement. So in the happy path block, we know that we've got an integer, so we can dereference our expected, subtract 1 from it, and we've got a new integer. Well, so far, so good. But then the next thing we want to do, and yeah, I admit this is a little bit contrived, we want to divide it into 1, so sort of take the reciprocal, which means we've got to guard against division by 0. So that's why I put that in there. So we're going to test first, is this integer 0? If not, then we're happy path, we can carry on. But otherwise, we've got to create another stood expected. And notice now, because we're actually dividing into a floating point number, this one is going to be a stood expected of float and stood runtime error. So we can't use the original one anymore. And that's why we had to pre-declare it at the top. So we're using assignment in both of these cases. But then if the outer if block, we went into the else clause right in the middle there, we had an error. Well, now we got this, we actually need a stood expected of float, and we've got a stood expected of int. So we need to move the error out of there into our new stood expected of float. Finally, we've got our stood expected of float, and we can test it and dereference it at the end as before. So yeah, it's not rocket science. You can follow it all, but it's a lot of tedious little details you've got to get right. And look, the happy path ends up in the middle. We started a few lines in. I mean, maybe we can put the happy path at the end a bit if we just invert the if conditions. Exactly the same code otherwise. We just put the happy path at the end. But it's not really that much better. So what else can we do? Well, a big problem here is this anti-pattern that you see a lot of, well, we need to set something based on some conditions, so we're going to have to pre-declare an uninitialized or default initialized value, and then assign it later. Whereas really, we wanted to do that all in one go. And there's just a general pattern to solve this, to rewrite that, which is to use an immediately invoked lambda expression. Fairly well known now. Probably most of you are familiar with this, but just in case not, you can see we've introduced a lambda right at the start there, which is returning our final stood expected of float. It's capturing the string on the way in. We're doing all of our conditional stuff inside of there, but instead of assigning inside, we're returning out of it. And that return can now be used to initialize directly our stood expected of float. You can see it's being immediately invoked at the end there. So it's just a nice way of addressing that nice general pattern. If you haven't really used that before, I encourage you to do so. That's not what this talk is about. But there is one way that we can clean this up a little bit. It's okay. It's not too bad. But we can do better. We're using stood expected here. We've already got C++23. C++23 introduces some additional functionality, the so-called monadic operations. for both stood expected and stood optional. So there's the 4 member functions I'm going to introduce you to. 3 of them are shared between both types. The 4th one is stood expected only. Let's see what we can do with those. Now, we've got monadic up there. I'm not going to talk about monads. You don't need to know what a monad is to understand this, just what the functions do. So let's go through that. All right. So we start with parseInt. So it's much better already. Now, parseInt is returning our stood expected of int and stood runtime error. Now, stood expected has these methods on. So transform is the first one we're going to use. They all take lambdas. And those lambdas take what we call unwrapped values, so that the dereferenced value in this case. So we've got an int coming in. We don't need to check it first. Transform's only going to get called if it has a value, and it will call it with that value. So that's a bit simple already. And in there, we just do that return I-1. Nice, clean, simple. That is going to then rewrap that back up into a stood expected of int and runtime error. And now we can call the next member function on that. And we're going to use .andThen. And .andThen also only gets called if you have a value, unwraps the value, passes you that. You don't need to worry about that. But this time, it actually returns a new stood expected. So that's why we've had to spell it out there. And we can use our stood expected of float. And then we've got our check against 0. We've got our divide by 0 error case. Again, we can just use returns here. So that's also a bit cleaner. Now, why do we have this difference between transform and then? Let's say with and then, we can actually spell out the whole stood expected return value. And in this case, we have changed the value type. That's not the reason we had to do it here. We could have done that with transform. That can also change the value type. But we also needed to be able to return either a value or an error again. So this one is doing error handling. So and then does error handling. Transform will only transform the value to another value. That's the difference. And then finally, we've got our final expected of float. We can do our usual test at the bottom. So far, so good. So but let's compare that with what we had before. That's sort of the best we had without these functions compared to this. So not a lot less code, but it is a lot simpler. Once you get used to these functions, it's a lot simpler, a lot cleaner. And look at the control flow, or the data flow. We start with parseInt. The integer goes in at the top, goes through each line in succession. There's none of this in and out, heavy nesting. Much cleaner once you get used to it. All right, I said there were 4 monadic operations. This is 2 of them. Another one is or else. We could tack that on at the bottom. So or else will get called in the case of an error, and it will actually pass you the unwrapped error. We're not using it in this case, that's why I just put auto there, but you can get the error if you need to operate on it. And then it returns a whole stood expected. Again, you can change the types if you want. But the idea here is that you can provide some sort of default or backup value. It's a bit like value or on stood optional. In fact, expected has value or as well. But value or is eager in that you have to give it a value that you've pre-computed if that's an expensive operation. Whereas or else is lazy. You're giving it a lambda. That lambda is only executed if there is an error. So you can actually have some sort of computation in there. You also have access to the error object. So you may need to take that into account. And you can even provide a return an error from here as well. So it is more general, more flexible. But you can use value or as well. And that means at the end of this, now we're guaranteed to have a value in our expected float so we can safely dereference it. All right, that's or else. There was one more, which is transform error. Now this is the one that's unique to stood expected, and perhaps for obvious reasons, because it actually operates on the error value, which optional doesn't have. So if it is an error, like with or else, you get called with that error. This time we are using it. But like transform, rather than returning the whole stood expected, you only have to return a new error value. It's just literally transforming that error object. It can be a different error type, as we're doing here, but we don't get to change the value. So here we're just taking the message out of our exception type, wrapping that in a string, and returning that. So at the end, when we say .error, we just get a string back. Fair enough. Bit of a contrived example, but hopefully illustrates how this all works. So just to summarize the magnetic operations, these are the four, and then or else transform and transform error. The first three shared between stood expected and stood optional. The last one specific to stood expected. A couple of other minor differences as well. Or else for stood expected gives you the error object. There isn't one for optional, so it doesn't give you that. But otherwise, they work the same way. This might be a little bit easier to sort of internalize, because I think that's the big difficulty of this, is actually internalizing all the different semantics. If you put it in this grid, it really sort of divides up across 2 dimensions. So, and then and transform deal with values, or else and transform error deal with errors. And you get the unwrapped versions of each. And the other direct dimension, and then and or else, will always return a stood expected. You've got to construct a whole new stood expected, which means you can do error handling if you want. Whereas transform and transform error, you stay in the world of values or you stay in the world of errors, which is much simpler if that's what you want to do. So you had the choices. You could actually just stick with and then or else and do everything that the transform functions do. But if you can stay in the world of values or stay in the world of errors, then it's cleaner to do that. And really, that's all there is to it. It's just a case of familiarity. Hopefully, that example has shown that it does clean things up a lot. It's worth learning. It gives you a lot. So that is the error handling features in C++ 23. Stood optional, well, we already had. Stood expected, we got. And these 4 functions. But that's not the end of this talk. We have another section to get through. So, part 2. Now, while the whole previous section was mostly language dependent, C++ 17, C++ 23, we got into a lot. This section is going to be mostly language version agnostic. You can use what I'm going to talk about in any language version. We will talk a bit about contracts, particularly towards the end, which are an upcoming, hopefully, language feature. They are still on track for C++ 26. Not a done deal yet, so we'll see. But although I'm going to mention them, we can do everything that we're going to talk about without them, so don't worry too much about that. We can also mix in things like stood expected as well, as we'll see. Now, for this, we're going to use a different example. So it's almost like the inverse of what we had before. We had a parseInt, took a string and returned an integer. Now we're going to take an integer and return a string. Okay, but it's not quite the reverse. As you can see from the name, we've got some expectation on that integer. So month as string suggests that this is going to be a month number, and we're going to return the name of the month. So again, let's look at a possible implementation of this. Simple enough. We've got an array of month names at the top, some sort of global or static. And we're just going to index into that. Nice and simple. Does the job. We've got a -1 on there, so our month is 1-based, 1 for January, and so on. Which means 0 is out of bounds. And that's the thing. This function is only valid for integers between 1 and 12 inclusive. Anything else is going to be undefined behavior. And that's something we need to be very careful about. Now, we can get rid of the undefined behavior. Oh, before we get into that, let's just actually see what the undefined behavior looks like, possibly. I ran it on my machine with these 3 values, and this is what I got. So the first case where I passed a 0, I actually got an empty string. In fact, I think most of the numbers past 12 initially just gave me empty strings. And that's the thing with undefined behavior. Sometimes it seems to give you something reasonable, but it's lying to you. It took about 10,000 before I actually got into some garbage memory. But that's the thing with undefined behavior. It can be misleading. Sometimes it seems like you're getting away with it. We don't want to invoke undefined behavior, but it can be useful to have it in the code. And it's a big hot topic at the moment, but right now we still embrace undefined behavior in the code. We just want to put in ways to avoid actually invoking it. So I said we can actually remove it completely by turning this into an error handling case. So this is like the disappointment handling, whole of the first section. We just talked about any of those techniques, including exceptions, stood expected. We can do a test up front. In this case, we're throwing an exception, and we never actually get to the undefined behavior. So that's a perfectly valid approach to doing this. But if you do want to keep the undefined behavior, because that avoids doing that if statement, and that may matter to you, there's other reasons as well, then what can we do? Well, we could do the check externally. So here you can see it's off in the test if function. So we've taken the check out of Mumford's string. We're always going to make sure we pass it valid data, so we'll do a check there. But it seems like all we've done is just push it up a level. But this does give us an advantage, because now we can do that check just once, and we may call Mumford's string many times, or several functions like it, that all depend on Mumford's string being validated. We validated our data, and now we can call functions that depend on that. Okay, so far so good. Now, just because we are not choosing to do this as error handling, doesn't mean that we shouldn't check that range at all. So we should probably put at least an assert in there, so that in a debug build, it's still going to be doing that checking and will let us know if we've got a bug in our code that's invoked that undefined behavior. We want to weed that out. So if we do get contracts, as we're going to see a little bit later, there's other ways to achieve the same thing. In this case, an assert is perfectly fine, so I would at least do that. But now we've got some duplication. You can see our range check is in the code twice. That's also dangerous, because that can get out of sync. And now if it gets out of sync, we're going to be exposed to that undefined behavior again. If only we had something in C++ that lets us deduplicate bits of code. Of course we do. We can refactor that out into a separate function. I'll call this one isValidMonth. Now we can use that in both places. Technically, there is still a little bit of duplication here. I've got that function name, but an identifier repeated is much better than some detailed logic with consequences. So this is a much better situation. But it's still a bit painful to have to do this if check every time and remember to do it. Is there a better way? Well, if you're doing something a lot, again, what do? You factor that out into its own function or class, whatever the abstraction is. We could do that as well. So we can write another function. I'm going to call this one Mumford string checked. And in there, we do the if check. In this case, we're going to return the stood unexpected instead. So we can use any of these error handling techniques. And if it passes the check, then it's just going to forward on to the original function and return that instead. And now we can use Mumford string checked anytime we need the safer version. So we could do this with exceptions as well. But we've got the choice. We can opt in, we can opt out. But we've got a bit of extra boilerplate now. 2 functions instead of 1. A little bit painful. We'll address that in a minute. Before we do that, one more thing. We've chosen to have a longer name for the safe version, the checked version, which sort of implies that the default is the unsafe version. Nothing to stop us just switching that around. So now we have Mumford string unchecked, which you can opt into. Well, the default is now the safe version, which actually checks. And you're more likely to use that, because that's just how we are. So starting to get there. We've got the choice. We can use the contract version, we can use the checked version. But I mentioned that boilerplate. Well, let's just change our error handling to exceptions, because now we've got the same signature for month for string and month for string checked, apart from the name itself. Which means we could actually do something interesting. So bear with me on this. If we make it a template, we've got an enum here for checked and unchecked, non-type template parameter. Got the enum, defaults to checked. You can do it the other way around if you prefer. And inside the function, we're going to do an if constexpr. So if we're in the checked mode, we'll do our check, throw an exception. Otherwise, we carry on with the unchecked version. We've still got the assert in there, just in case we skip that. You notice in the usage code, we don't even have to put the angle brackets in if we're using the default. So it just looks like a normal function. But if we want to opt into the unchecked version, we'll just apply that template argument. So one function gives us both approaches to dealing with that error. Not too bad. We've still got a bit of duplication in there. Now, I said it's minor duplication before, the two calls to isValidMonth. Now they're right up against each other. It just feels a bit like, can we do something about that? Best I've come up with so far, maybe there's a better way, let me know. If you could tolerate a macro, we can hide all that boilerplate in there. But it's not bad. Assert or throw just looks like an assert. Now I've put spelt out the whole exception call there. If you can go with default version, we can make this just like an assert. Not too bad, considering what that's giving us. So, not too bad. I think we can still do better. Might actually be more code, but I think it's going to be better in the long run. Because the problem here was the difference between the range of the int, which is, 4 billion, with what we call the domain of the function, which is expecting a number between 1 and 12. It's a big difference. And all of this has been in service of just bridging that gap. And where possible, I prefer correct by construction techniques. Probably familiar with this term. Let's see how it applies in this case. Really, in this case, it amounts to having some sort of strong type around our month abstraction, because that's really what we have, this implicit abstraction of a month that we're having to sort of check around the code. Let's just centralize that in a single abstraction. We'll call it month. Now, you can use third-party bounded integer libraries that would cover you in this sort of case. But this is a more general approach anyway. It's actually not that much code. Although, I mean, this is slideware, but you don't need a lot more than this. We're just going to wrap that integer in there, but we're going to validate it on construction. Literally correct by construction. So if it's not valid, in this case, we're going to throw an exception. We can still get the value out using the value method. Now in usage, month for string, instead of taking an integer, takes our month type, already pre-checked. Again, as I said earlier, if you've got many calls to month for string or other functions that all take months, you don't have to keep checking. You don't have to worry about, was this checked or not already on this code path? If you've got a month, you can guarantee it's already been checked. Correct by construction, really simple approach to just centralizing any actual checking. Now, because we've done that, we can push that checking as close to any boundaries as possible where we might get unvalidated data from. But there can still be some cases where you say, I know I've got an integer guaranteed between 1 and 12. I want to construct this month without any overhead. So we sort of need another constructor, but we can't give it a different name. So I'm going to use what we call tagged invocation. So just write an empty struct at the top with unchecked. That's our tag type. Only purpose is to provide us an overload. So now we've got another constructor which takes unchecked as its second argument. Doesn't use that, it's just for the overload. And in usage, we just pass a default constructed unchecked in. And usually, this can get optimized out Last time I said that, I got called up. Somebody said, oh, but I put this in Compiler Explorer and there's still some overhead. Maybe sometimes, do measure if that's important. But usually, you should be able to get away with it. So worth bearing that in mind. Now we're back to all of the opt-in, opt-out that we had before. We pushed the check-in closer to a boundary. We've got nice, easy to reason about types we can use anywhere, and they're always checked. Okay, running a bit short on time. I still want to talk a little bit about contracts. Now, I said we're not going to rely on having contracts. They're not quite here yet. This is not a talk about contracts. I recommend a talk by Tima Dumler, one of the authors of many of the contracts proposals, who did an excellent talk at CPBCon on that. Not sure if that one's available yet, but do watch that when it comes out. There was also one by Lisa Lippincott, which is a bit more the philosophical angle to contracts. So watch one or other or both of those talks. But if we did have contracts and we wanted to solve the same problem, let's go back to just the free function version, keep it simple. Then we would put this precondition check, actually between the name of the function or the function signature and the body. So you can see it's outside the curly brackets. But otherwise, it looks very much like the assert we had before. And it's playing basically the same role. Main advantages are finer grain control. We'll see a little bit more of it in a minute. It's sort of part of the interface, so you can often see it outside of the function for different purposes. And it's just a bit more expressive as well. Now, we don't have this yet, but, the other advantage, by the way, is we actually get a lot more information out if something fails. We can get something pretty close today if we're willing to write another macro. So, slideware. I only put this together for the purpose of this slide. This is not a proposed library or anything. And it doesn't exactly match the contract's proposal. It's just enough to demonstrate the essential points here. So very much like the assert macro, but one thing to notice is this violation handler. So if a precondition check or any contract check fails, rather than just immediately aborting, it's going to call this violation handler with the stringized version of the expression that failed. So here's my implementation of how to deal with that. I'm not going to go through this in detail. It doesn't matter. This is not anything to do with the contract's proposal. This is just my attempt to make this all work and hang together. The bit to notice is that the violation handler is itself a function pointer, which means we can replace it with something else. We've got a default violation handler, just prints it out and aborts. But we could, for example, very useful for testing, replace that violation handler with one that throws instead. You see at the top, we're throwing that logic error, which means we can actually test our contracts. Normally they would abort, but just for testing, we can say, no, make this one throw. That's really useful. And people that have had their own contract libraries have been doing this for years. And there you can see now that's an exception instead. There is a little bit of a problem that we need to be aware of. If we go back to looking at this signature, and if we make the return value a string view instead, because we know that everything is in global memory, that should be stable. Apart from that contract check, there's nothing in here that should throw. And we might be tempted to put a no except on there. But now you can see, hopefully, because of what we just said, because we can replace the violation handler with something that throws, that's going to come into conflict. So if we do try to test that, it's not going to work. It's going to abort because of no except catching the exception. So take the no except off and this all works. This is the essence, or at least part of what's become known as the Lacoste rule. It's actually been around since early C++ 11 days, been applied to the standard library. But more recently, it's become more sort of proposed as a general principle for library design or in general. To quote from this paper, so I think this really captures it. Absent of vanishingly rare and compelling engineering reasons to do otherwise, deviating from the Lacoste rule is invariably and absolutely a terribly bad idea, especially within the C++ standard library specification. So he was holding back a bit there, I think, but gives you an idea. What's really the problem here? No except was really originally put in to allow us to provide move semantics. Because move operations, the move constructors, move assignment operators, usually should be no throwing. They usually can be. And if they are, we can detect that and have more efficient, particularly std vector, maybe other containers as well. That's why we should always put no except on our move constructors if we can. That's great. That's what it's for. Pretty much anything else, it's going to come into problems like this. There's other problems as well. So don't use no except for that sort of thing. But here's my list of workarounds. So the first one is to follow the Lacoste rule. Don't use no except. Well, I've said with preconditions you want to test, but actually in general might be a better way to phrase it. But if you do need to, if you've got simple preconditions like the ones we've been looking at, like that is valid month, maybe just test that rather than the functions that use it. And then you can put no except on the functions, but not the predicates. Or consider that overload, the checking policy idiom thing, the thing with the enum and the template. Because that lets you check the throwing version in test code and be reasonably sure that's testing the actual checks. Some other things that people do, which I don't advise so much. Wrap no except in a macro. Compile it out to something different for testing purposes. Not a good idea. Or use dev tests. Google Test has these. Can be useful if you want to test that something aborts, but really slow, so you don't really want to be testing contracts that way. So by default, follow the Lacoste rule. I'm out of time, so I'm just going to rush through my summary. Those are all the things we looked at. Disappointments where you have predictable errors. You want to handle this lots of different ways. Exceptions, it should be your default choice. Optional and expected probably cover pretty much all other cases these days. So learn the monadic operations so you can make better use of those. Talked a little bit about contracts. A narrow contract is one where you have that difference between range and the domain, or other things where there's undefined behavior if you invoke it incorrectly. Preconditions specifically, we talked about these throwing violation handlers, useful for testing. Don't use no except. That has been modern C++ error handling. Thank you very much. Do we have time for some questions?
Absolutely brilliant talk, Phil. Phil Nash, everyone, once again.
Thank you.
I'm afraid that in the interest of time, we're going to have to skip the Q&A session, but I'm sure you will take some questions during the break. Cool. So feel free to approach Phil and ask him questions. In the meantime, we're going to take a short break and continue as advertised. Thank you.
Thank you.
I think it's time. Thank you so much for coming back so punctually. We will be continuing with our artistic side of Code Dive. And the next person to speak is Guy Davidson. He's the head of engineering at 6 Impossible Things Before Breakfast, where he attempts to make the impossible possible. He's also a member of the C++ Standards Committee and the chair of programming languages for the British Standards Institute. A former radio presenter, Guy also sings first bass for the Brighton Festival Chorus and has played the Mrs. Mills piano at Abbey Road. Let's have a quick look, shall we? So this is Miss Mills, for those who are not familiar with very old English music. She was a pop star at some point. Okay, this is the piano at Abbey Road. You might remember Abbey Road from the Beatles' famous record. So that's the actual piano. And this is Guy playing the piano. Other than that, it is portable floating point calculations. Let's put our hands together for Guy Davidson.
Right, let's, come on, you can do this. Excellent, yes you can, thank you. Hello everyone, my name's Guy Davidson, as you heard. I played Lady Madonna on that piano, which was written in that room. Most of the Beatles songs in the mid to late 60s were written on that piano, so I just had to play it. Here's our agenda. We're going to be talking about non-integral values, standardizing non-integral arithmetic, standardizing C++ for non-integral values, and improving reproducibility of non-integral values. This was a 1-hour talk. It's now a 45-minute talk. Yes, we can do this. Right, non-integral values. So let's start with our arithmetic operations: addition, subtraction, multiplication, and division. Each of the inverse functions, subtract and divide, can create results outside of the original domain. So, for example, addition on natural numbers will keep you in natural numbers, whereas subtraction on natural numbers will sometimes take you to the integers. Multiplication will keep you in the integers. Division will put you into the rational numbers. And rational numbers are ratios. The clue is in the name. They are countably infinite, which I find quite exotic and lovely. I'm actually a mathematician more than I'm a computer scientist. Half of the rational numbers lie between -1 and +1, which I also find extraordinary. They're very analog. There's something of the cosmos about them. They're delightful. Every 2 rational numbers has another rational number between them. And they're reducible via the fundamental theorem of arithmetic, where you can factorize prime numbers and do cancellations and things like that. Has anyone here used a slide rule? You should all go and buy a slide rule and learn how to use it, and get in touch with the true center of the universe. So yeah, I like rational numbers, until of course I have to add them. Adding rational numbers, very unpleasant. Multiplying is easy, but with addition, you have this cross-multiplication going on. You know how to multiply fractions, you know how to multiply rational numbers. You can tell that it doesn't take long for things to just get too wide. Once you've started adding 30 or 40 of the things together, you overflow horribly. And factorizing is a rare opportunity. Having coincidentally matching prime factors is actually quite unusual as things get larger. You might think you might use an arbitrary sized integer class to represent things, but then you've got the same problem. You're running out of space all the time. Hang on. There we are. And it increases the time to compute. It takes up memory. You can't just say to your clients when they ask you, well, how long will this operation take? You can't just say, well, it depends. They don't like that. But we came up with a solution quite a while ago. And it depends on who you ask exactly when. Decimal fractions have been used for several thousand years. But if you're familiar with the decimal point, and I hope you all are familiar with the decimal point, this turned up in a book by John Napier on constructing logarithms. It was published at the beginning of the 17th century. Now, the decimal point tells us that we are now approximating via sums of powers. The final digit after the decimal point, sorry, the first digit after the decimal point, gives us the number of tenths, the next the number of hundredths, and so on. By adding more and more negative powers of 10, precision can be improved, but there are only a small set of numbers which can be represented exactly, because since we're in base 10, the prime factors are 2 and 5. The only rational numbers that could be represented exactly are those whose denominator is representable as a product of powers of 2 and 5. So for example, 1/8 is 0.125. 3/40ths is 0.075, 75 thousandths. And other numbers, though, aren't so lucky. In fact, most numbers aren't so lucky. Here's 1/7. This is represented as 0.142857 recurring. But I got this when I asked Clang to show me what 1/7 is. And as you can see, it's quite wrong. All numbers that are not exactly representable will recur over a maximum of 10 to the power of n digits, where n is the number of digits in the dividend. And this inexactitude might seem quite problematic. It could spell doom for engineering, but it doesn't. Here we are in a building. This building is not falling down around us. We've managed to accommodate it. And how did we manage this? What is the size of the observable universe? U. What's the size of the observable universe? No idea. OK. One day, someone will know. Actually, that's the answer. 8.8 times 10 to the power 26 meters in diameter, which is a lot. That's pretty big. But look at that exponent. 26 decimal places gets you the width of the universe to the nearest meter. And there are certainly more than 26 places in that expression of 1/7. 36 decimal places gets you the width of the observable universe to the nearest atom. And atoms are small. So honestly, 26 decimal places is quite enough. You might get some error. We can deal with that. Right, what's this value? Now, you might tell me it's 26,998. And you would be completely wrong. Well, not completely. If you assume this is an integer, then yes, it is 26,998. But what I haven't told you is that the lowest 4 bits are reserved for negative powers of 2. So this value is actually 1,687.375. And adding and subtracting these kinds of numbers is simple enough. We don't care about powers in these operations, but let's try some multiplication. Now, if you pass these bit patterns to the multiplier, you get this. And as you can see, this is not 18. This is 288. To get the expected value, you have to right shift by 4 bits. And this tells you straight away that there is some overhead in working in fixed point arithmetic. Since fixed point arithmetic isn't natively supported by C++, you have to manually write a fixed point class. And you might decide to use CPU intrinsics to implement this. And some processors do actually support fixed point arithmetic. But that final part of the operation where you shift the result by the number of bits in the fractional part also highlights another problem, because precision falls away with each calculation. Now, simulations. Now, I write games, and games are mainly simulations. They make heavy use of Newton's laws of motion, which involves a lot of multiplication. And it won't take long for your model to diverge noticeably from what the user might expect. The problem we have is that the binary point is fixed at bit 4, which means we have to divide by 16 after every multiplication. And if we wanted more precision, we would have to divide by even greater numbers, which would yield an even greater error. So in the prior example, if we simply left the value alone and shifted the binary point to the left after each multiplication, there would be no loss of error, but we'd soon run out of magnitude. So let's look at another representation of numbers. So in the first line, we are performing addition. We've got 3 decimal places in each number, but the second number has a higher magnitude. And look at the results, because the results of the addition has 4 decimal places. The results of the multiplication has 5 decimal places. So this looks good. We can accommodate the expansion of precision rather more easily than with fixed point arithmetic. Now, rather than keep the decimal point in the same place in the number, what we are doing is storing the number in 2 parts. We have a value and a magnitude. The value part is known as the mantissa, while the magnitude part is known as the exponent. And note what's happening in the mantissa. It's getting longer. If you're working to 4 significant figures, then you have to decide what to do with the remaining figures. You could truncate the value, or you could round to the nearest value. And this is a tricky problem, and this will return to bite us later. So let's try something in binary. Now, we have to make some decisions. Which part is the exponent and which part is the mantissa? And I'm going to choose the bottom 6 bits for the exponent and the top 10 bits for the mantissa. So that gives us this. Now, when we were in base 10, our mantissas lay between 0 and 10. For this example, I've decided that our mantissa lays between 0 and 1. So looking at the leftmost 10 bits, counting left to right, we have 1/4 plus 1/64 plus 1/512 plus 1024th, while the rightmost 6 bits total 11. And this gives us an exponent of 2 to the 11th power, which is, of course, 2048. This evaluates to 550, and a similar approach to the second value evaluates 0.2890625. I'm using the color coding there to match the bits to the corresponding powers of -2. But we've got a problem, because if we look at the representations, we have this, and multiplying those two representations using standard integer arithmetic won't actually do the job. The process of floating point multiplication is actually quite a task. And the schema I propose does not invite a unique representation for each number. For example, these two numbers are the same. The value on the right has multiplied the mantissa by 4. So the exponent has been reduced by 2, since 2 squared is 4. Also, how does one represent negative numbers or negative powers? And that would cost a single bit of resolution for the exponent and mantissa. And another problem is interoperability. How do you communicate to your clients how wide the exponent and mantissa are? What if you're exporting a library to some anonymous third party? How do you identify your choice of rounding algorithm? There is plenty of room for error, and this sounds like a job for standardization. So IEEE 754 is what you're looking for. The standard was first published in 1985. Who was alive in 1985? Some of you, indeed. Fewer and fewer every conference, it seems. I'm not killing people, by the way. It just happens. It's coincidental. It's undergone some revisions since then. In fact, the C++ standard refers normatively to document ISO/IEC/IEEE 60559:2020, of course. And this is ISO importing third-party standards into its ecosystem. It's the same thing as the latest revision of IEEE 754. You don't need to read this standard. You can simply rely on your vendor implementation to be conformant. This is my straight face. Indeed. Thank you, Hannah. Anyone play this? Yeah, good. Some people, good. Again, fewer every conference. It's disappointing. So I worked on this. I was the... Thank you. Oh, really? Stop it. No. It was years ago. It was 20... God, it was 20 years ago today. No, it wasn't today, but it was, over 20 years ago when this came out. The thing is, we started this in 2001. It was actually released on the 10th anniversary of the first broadcast of the first episode of Friends. Anyone here watch Friends? Okay, still relevant. Good. All right. And it featured multiplayer action over the internet, which was quite hard to achieve because there were many megabytes of state which had to be synchronized with each player at 10 hertz. Now, that's quite a big ask of the internet even now, but back in 2004, it was lunacy. Even transmitting the data from tick to tick was infeasible. The only thing we could do was transmit the commands that were issued to the simulation of the world to each agent and update each agent's simulation equivalently. And this was a really tricky problem. It was very easy to write code that was not deterministic. Now, you might forget to fully initialize an object, and you'd get stale data from the stack instead. You might pass a reference to an object to the camera and inadvertently change things locally. There was just so much stuff that could go wrong. So we devised programming guidelines, debugging strategies, we locked everything down, and it served us well for 2 decades. It continues so to do. But Sega, who publish all the Total War games now, they're very keen to see a console version so that Xbox and PlayStation and even Switch players can join the fun with PC players. And now, it would be quite feasible to have Switch players playing with other Switch players, or Xbox players competing against other Xbox players. But no publisher wants a fragmented audience. You should be able to connect to a lobby and play with anyone at all. Just do it. Just do it. That's basically what publishers say, because publishers are not engineers, they are publishers. And you might be thinking, well, crossplay is a thing. You might have heard of crossplay. And that only works because crossplay is doing very simple stuff. You know, you're not flinging megabytes of state around hither and thither. And you might go on to think, well, won't the same code work the same way and yield the same results on different platforms? We've got a standard. That's what it's supposed to do. 2 + 2 is always 4, isn't it? OK, that's not quite true. You know about the butterfly effect. If you make one error, everything goes wrong quite quickly. How many engineers do we have here? OK, all right. Well, the rest of you, thanks for coming. I hope you're still keeping up. I have a simple example here. Who's heard of Compiler Explorer? OK, good. All right. So I've got a simple example here, 42 lines of code that explain what's going wrong. Unfortunately, we don't have internet here. So, right, there we are. Wow. This is a big screen. OK, all right. Things start to go wrong at the very first calculation. Let's see if this spotlight pointer works. Whoop. Oh, look at that. Brilliant. Things start to go wrong. Oh, where are we? There. Now, up here, I've got all the bits from all the operations. This is really hard. I've got all the bits from all the operations written out here, and they start to diverge at distance. Which is our first calculation. So here we've got the we've got the NVIDIA compiler here. That gives us a number ending in 7. We have the Clang compiler here. That gives us a number ending 9. Much sadness. Much sadness. All right, come on. There you go. There we are. Let's get rid of that cursor. You'll also see that proj_vector y is divergent as well. And this is a real problem, and I want to focus on reproducibility across implementations. So we're going to talk about standardizing non-integral arithmetic. The IEEE decided to standardize floating point arithmetic 1985. Then the IEC thought, oh, we'll have that, and they imported it in 1989. The British Standards Institute in 1990. IEEE said, you know, this is great. Let's have another version. Let's revise it. They did that in 2008. So this bunch of people went, oh, great, another version. And then they did another version in 2019. Yeah, indeed. I'm hoping that's the last version, but time will tell. So this is where we are now, BS, British Standard, ISO/IEC, 60559:2020. Learn that number. If you say it enough times, which I certainly have done over the past year, it will just roll off the tongue. So I'm going to stay current and focus on the latest version. So the standard specifies formats for binary and decimal floating point data, addition, subtraction, all of those things, conversions between different formats, floating point exceptions and their handling, including data that are not numbers. And I'm going to do some foreshadowing here. There we are. And I'm also going to highlight parts that aren't especially relevant to portability, which is those. So in the section on definitions, abbreviations, and acronyms, there is some more foreshadowing. So this is fairly mundane. Language defined, behavior defined by a programming language standard supporting this standard. That's what you expect. But implementation defined is not. Behavior defined by a specific implementation of a specific programming environment conforming to this standard. So this suggests that this standard is already aware that implementations may differ of the same language. And this, as I've said, is the problem that we're having. Now, onto the meat of the standard. I'm going to rush you through this because, you know, you could try reading it yourself. It's actually quite an easy document to read. It's about 4 hours, 2 glasses of wine, a rainy afternoon. Do you have rainy afternoons in Poland? OK. Next rainy afternoon, read the standard, 2 glasses of wine. Anyway, 3 binary formats and 2 decimal formats are defined in clause 3. There are 11 clauses in total. On the binary formats, because C++ only works in binary, we have this one, which you may be familiar with, single precision, and this one, double precision. And that's it, 11-bit exponent, 52-bit mantissa, and 1 bit for the sign. So it's time for our first piece of implementation and language-defined text. The choice of which of this standard's formats to support is language-defined, or, if the relevant language standard is silent, or defers to the implementation-defined high. There we are. The names used for formats in this standard are not necessarily those used in programming environments. So back here, they call this binary 64 in IEEE, but we call it double, if double conforms to binary 64. Now, the standard then goes on to tell us what I said earlier, that floating point arithmetic can only represent a finite subset of the continuum of real numbers. Consequently, certain properties of real arithmetic, such as associativity of addition, a plus b plus c, is not the same as c plus b plus a, unfortunately. They don't always hold for floating point arithmetic, so order of evaluation matters. So that's clause 3. Now, clause 4 deals with attributes and roundings. Attributes are associated with the program block. There are 2 different kinds of attributes. Some change the operation of functions. Some are implicit parameters. Rounding falls into this category. There are 5 rounding modes. 5. Oh, well. Rounding is a beast. During the production of Rome Total War, as we were trying to achieve determinism, we would find that desynchronization would occur on machines with different graphics cards. And it turned out that one graphics card driver preferred a different rounding mode. That's fine. So when you executed code from the graphics driver, it would change the rounding mode. And then it wouldn't change it back. So all of the well-behaved graphics drivers, they keep things nice and clean for us, but one didn't, and this caused divergence. It made me very grumpy indeed. Clause 5 is where things get meaty, because nearly a quarter of the document is taken up with this clause. The standard is quite comprehensive, identifying the set of functions that shall be added by a conforming implementation. Particularly, we have rounding functions. We've got next and previous functions, log functions, arithmetic operations, everything that you can imagine. The usual arithmetic, of course, but also square root and fused multiply add. And this is where things become problematic. FMA computes x times y plus z, rounding only once to the destination format. And it differs from a multiplication followed by an addition, because this would yield 2 rounding operations. Remember what I was saying? When you multiply things, they get bigger, and you've got to truncate them. Every time you truncate, you lose some precision. With FMA, you only get 1 rounding, but with regular calculation, you'll get 2 roundings. That's where the problem lies with FMA. Let's go back to Compiler Explorer for our example. And so you can see where the problem is. Right, there we are. Oh, spotlight. There we are. Right, FMA. At this point, we're calling an FMA. That's 1 rounding. But over here, there is no FMA at all. And so, sadness. You won't always necessarily see a different result. You know, a half times a quarter plus 3/8 will always evaluate the same way, because there's no rounding required. They can be represented perfectly. But sometimes, unfortunately, there's a bad word in deterministic evaluation. Because the compilers are free to choose how to implement these expressions. They can reorder within an expression statement as appropriate for the optimizations chosen on the command line. And you'll note here that none are chosen. This is all just, the compiler options are empty. But we can resolve this by breaking the expression statement into single computations. If you move everything into a single operation and then put a semicolon, then we do get some. We do make some progress. It's not quite problem solved though, because when we switch optimization on, it's anybody's guess. And who wants to run an unoptimized game? It's not a thing. But we've witnessed all sorts of divergence with different optimizations, and it's not a sufficient solution to merely break down all the expressions, but it's a start. There's a truckload of stuff going on here, frankly. There are conversion operations, sign querying, negation, different types of rounding, ordering, comparison. One day I'll do a full walkthrough of the standard and what it means. This is not that talk. If anyone's familiar with the Goldberg paper, you'll be surprised what else there is. But we'll rush on for today. But yeah, the Goldberg paper on what every programmer should know about floating point arithmetic, absolutely worth reading. So infinity is a remarkably simple concept as far as the standard is concerned. You can do anything with infinity, you get infinity, and it's also signed. But nans, not a number, are really quite subtle, because you can use them for initialized objects, or loudly signaling invalid operations, or quietly signaling exceeding range, or generally identifying that something has gone wrong. Nans propagate, because once your program has gone wrong, it can't be recovered with valid data. So nan takes advantage of representation rules, because not every bit pattern represents a valid number. I haven't gone into depth on encoding. It's an interesting field. The sign bit might seem trivial, but there are some interesting edge cases. How do you choose the sign of 0? I'll leave that for you. Clause 7 talks about exceptions. So invalid operations, square root of a negative number, for example. And there are some things you can't do with infinity. You can't multiply it by 0. You can't divide it by infinity. Division by 0 actually gets its own exception, and so does overflow. And when a result can't be represented by the target's type, this is the thing that gets thrown up. And underflow happens when a result is smaller in magnitude than can be represented. So a number between 0 and the smallest floating point number will generate an underflow. An exact happens if no other exception is raised, and the result differs from what would have been computed were both exponent range and precision unbounded. And this is a matter of magnitude. Clause 8 also talks about exceptions. Clause 9 describes some extra nice-to-have operations like trig functions. Next is Clause 10, and here's where things get interesting. So in Clause 5, we looked at how to perform a single operation, and Clause 10 opens with a summary of Clause 5. Clause 5 of this standard specifies the result of a single arithmetic operation. Every operation has an explicit or implicit destination. For numerical results, one rounding occurs to fit the exact result into a destination format. That result is reproducible in that the same operation applied to the same operands under the same attributes produces the same result on all conforming implementations in all language. And that is a bold statement. All conforming implementations in all languages. Language standards define syntax for expressions that contain multiple operations or combine them. So as we saw, A times B plus C times D. The order of evaluation of operations is relevant. This is a rule for expression evaluation. The formats of implicit intermediate results, and when assignments to explicit destinations round once and round twice. This is the FMA problem. And this is all a little exciting to me because the implication seems to be that if you write your code using single operations rather than expressions and write your own maths library, then you're golden. But I'm not saying that's trivial, but it's not impossible. And if you remember, I worked for 6 impossible things before breakfast. Now, the final clause, Clause 11, was added to the first revision of the standard in 2008, and it is entitled Reproducible Floating Point Results. This is the shortest clause in the standard, and tempting as it is to read it out in its entirety, I'll summarize because it describes what the reproducible operations are, which is basically all the ones that do something to inputs legally. It describes a reproducible status flag and a reproducible format, but significantly it defines a reproducible attribute, which is an attribute that is required by a language standard in all implementations. And the clause goes on to say any conforming language standard supporting reproducible programming shall support the attribute, support a reproducible format, and provide means to explicitly or implicitly specify any sequence of reproducible operations on reproducible formats supported by that language. And it shall also explicitly define a whole bunch of things, including reproducible results attributes, which indicates when reproducible results are required and when they are not. So you can switch it on and off whilst, in the program. The final part of the normative standard instructs users how to obtain the same floating point numerical and reproducible status flag results on all platforms supporting such a language standard. And it's a list of programming guidelines, just as we had 20-odd years ago. 5 do's, 9 don'ts. And this came as a bit of a surprise, because typically implementations are 60559 compliant, aren't they? Which means that specifying the reproducible results attribute in code should be all we need to get what we want, which is portable, reproducible, floating point operations. Why has no one told me about this yet? Well, let's see how the standard does specify floating point behavior. Standardizing C++ for non-integral values. You might find this a slightly sarcastic section title. Is anyone here sufficiently familiar with the standard to be able to tell me where floating point behavior is specified? Seems unlikely. Okay, let's go back to the browser stuff. We'll start with basic.fundamental, paragraphs 12 and 13. So we have 3 distinct types, float double and long double. They can represent floating point numbers. Wow, this is a long way up. The type double provides at least as much precision as float. Long double provides as much. So what they're saying is floats are contained by doubles, which are contained by long doubles. The types are collectively termed standard floating point types. And an implementation may also provide additional types that represent floating point values and define them as to be extended floating point types. The standard and extended floating point types are collectively termed floating point types. So this is the C++ standard. It's full of this lengthy, legally stuff. It has to be precise. The final paragraph is a bit worrying. Except as specified in basic.extended.fp, the object and value representations and accuracy of operations of floating point types are implementation defined. So, yeah. I felt a sickly panic when I read this, and I went scurrying to basic.extended.fp to see what was on offer. So this is what's on offer, and it simply says you can define a type that matches binary 16 as defined in IEEE 754, and also binary 32, binary 64, binary 128. There's another one called bfloat, an AI float type. But again, it tells you nothing about operations, accuracy, precision, nothing at all. And it turns out that C++ has almost nothing to say about floating point arithmetic. It's really quite casual, and the reason for this is that not every implementation platform is IEEE 754 compliant. If the standard started mandating compliance with IEEE 754, or more particularly 60559, then suddenly we would have a whole section of implementations that were no longer compliant with C++. What to do? Now, this is a less sarcastic heading because C is also defined for platforms without IEEE 754 compliance. And again, there is nothing mandating floating point behavior, but there are some annexes to the C standard which help us out. More than half of the references to 60559 in the C standard are actually in these annexes. Let's take a quick look. Annex F spins through 60559 in much the same way as I described it earlier. C23 defines a macro called this, std IEC 60559 BFP. If an implementation defines this with the value of that means that the implementation conforms to the specifications in this annex for binary floating point arithmetic. Annex F goes on to cover a lot of 60559. It provides mappings for names. So, for example, binary 32 in 60559 is named float. In 9899 is the number of the C standard. Binary 128 is named long double. Sometimes symbols are used. So compare signaling not greater is not x greater than y. Compare quiet not greater actually is a name, is greater. Sometimes cases are changed. So next up, this is the IEEE name, the 754 name, gets called next up by C because of snake case. Annex F works its way all through. And it makes changes to names, introduces symbols, adds identifiers for functions to carry out behaviors. You can't just say, apply everything in 60559 and walk away. You have to actually spell it out and modify according to the prevailing standard and drafting rules, for that matter. Annex F9 covers optimization. This section identifies code transformations that might subvert IEC 60559 specified behavior and others that do not. And there are statements about code removal, code motion, expression transformations, all of this sort of stuff. And the rest of the annex looks at math.h and tgmath.h. Annex G looks at complex arithmetic, and Annex H looks at interchange and extended types beyond float, double, and long double. But wait, I hear you cry. Wait, indeed. What about ISO IEC 60559 Clause 11, reproducible floating point results? Well, what indeed? It doesn't feature at all. They just don't mention it at all. I think, I probably need to talk to some people who've been on the standing committee for a long time, that reproducibility was introduced in 2008, but the C standard at that time was just coming up for revision. And no one's done it, no one's proposed it. You know, if you don't propose a thing, it doesn't get in. If anyone's ever heard of allocate unique or make unique was added 3 years after we had unique pointer because we just forgot. We had make shared, but we didn't have make unique. This is what happens. Optimization. So fusion and reordering are the two methods of optimization available to the compiler. As we've seen, FMA can be problematic. Reordering is not an option for reproducibility either because of the characteristics of the processor being targeted and how it's not associative. How do we overcome reordering and fusion? We basically have to rewrite the code and put semicolons everywhere. But the trouble is, it's ugly. Now, MSVC does have some floating point options. FP fast, sounds like it's for optimizing, and it is. It moves stuff around. It's absolutely not reproducible. Precise is the default compiler behavior. The compiler preserves the source expression ordering and rounding properties of floating point code. It's much more, but it's slow. It is so slow. GCC has things like float store and fnomath erno and unsafe math optimizations and no trapping math. Again, finer grained control of the floating point environment. And all of these will change the behavior. And these are the things that often guarantee faster performance of floating point code. And then fastmath, which basically turns all of these on. So if we turn off all math optimizations with single operations for expression and write our own math library, are we golden? Now, I don't know about you, but one of the reasons I like using C++ is operator overloading. The ability to build complex expressions that look like they've come out of a textbook. They're easy to understand. They do what they're supposed to do. When I started programming, which was in the 1980s, who was alive in 1980 when I started programming? Great. Again, fewer and fewer people. This is aging. This is you lot in 30 years, okay? But they're easy to do. They're easy to understand, operators. It's just like a textbook. I had an awful time putting math functions together in the 80s. Honestly, it was, oh, have I really got to do things one step at a time, is what I'm thinking to myself. There's got to be a better way, and I have some ideas. So, improving reproducibility of non-integral values. Oh, I've got 10 minutes left. What do you mean, 5 minutes, young lady? It says 10 over here. But anyway, this is what we're doing as a first crack at 6 impossible things before breakfast. We've got a geometry template library. It takes an arithmetic type as a parameter. Currently, we're defaulting to float, and it's working fine, but it's not deterministic. What we need is a type that can be taken as a template parameter to our geometry library. Exhibits floating point-like properties, so exponents and things like that. It's reasonably precise. We don't need it to be thoroughly precise. We just need it to be consistently precise across all platforms. As fast as possible. Obviously, we're making games. Hang on. I missed something out here. We can actually do better. We can try changing the standard. Now, that class from the prior slide isn't going to fly in the standard. It's extraordinarily specific insofar as it sets aside 60559. So, no, that's not good. What we want is some way of preventing reordering. Now, one idea that's been floated internally to my employers is the idea of having fences, like memory barriers. But that becomes terribly unergonomic. It would greatly reduce the legibility of the source. An idea I had recently was a new attribute, reproducible, which would identify a function as being immune from floating point optimization. And this would also advertise to the linker that link time optimization was not available for the function. But it's still a function qualifier, like const. You can qualify functions by const. And one problem with such a function, though, is it must not call any functions which might affect its reproducibility. So this is quite a complicated bit of analysis that needs to be performed at compile time. And the same problem arises with the idea of pure functions. Anyone heard of pure functions? They're great. Pure functions are functions that you just execute them and they have no outside context to worry about. So they're eminently threadable. We don't have pure functions in C++. It's been proposed. We do suddenly have pure functions in C, only they're called unsequenced functions. And another thing they've done is they've snagged the keyword reproducible. So we need to come up with something else. In committee last week, we reviewed my paper, P3375, reproducible floating point results. It's pretty simple. I define this enumeration and this class. And the class defines operators, but specifies that execution behavior of operations on objects of type strict float shall preserve the literal meaning of the source code. Operations shall not be reordered or fused. Don't take the wording too seriously. The paper was well received, but there is little appetite for adding yet more overloaded operators into the STD namespace. In my next revision, I'll simply propose the functions which the operators implement, and in this way the user can build their own version of the class. There's another paper in the same sort of space, and this proposes rather drastically deprecating these two functions, fesetRound and fegetRound. Anyone here use fesetRound or fegetRound on anything more than an occasional basis? Brilliant. That means it's probably a ripe candidate for deprecation. And we replace them with a struct called struct rounded, which represents the rounding mode. And then we have static functions bound there, which will do add, sub, multiply, divide, FMA, square root, defined as binary functions. They're all carried out with the rounding mode passed to the constructor of the type. But neither of these papers are near complete. Things might not look great for C++26, but there's always C++29. But there is actually a larger problem, which is controlling the floating point environment. It's a mishmash of mechanisms, because first we've got command line options like fastmath, and these are set before the compiler even starts to execute and stay in place for the entire duration of the compilation process. Then we've got preprocessor pragmas like hash pragma stdc fp_contract. And these are set before compilation starts during the pre-processing phase. And finally, we've got C library functions, such as fe_getRound. Some of these are set at compile time, and some are set at runtime. Some are modified at compile time, and so on. And these come from properties described by 60559. And these mechanisms date back to C, but what we can do now in C++ is use const_eval functions to execute things at compile time and compile time only. So this gives us opportunities for much finer-grained control of the environment, testing if an attribute is available during the compilation stream, and then compiling code paths conditional on that availability. Template metaprogramming, I'm sure some of you have tried that out. It's quite a tricky problem, though. I was speaking with Hana yesterday about it, and it's not as easy as I thought. You'll be hearing from Hana later in this room. Do go to a talk, it's great. Thank you, Hana. But I hope to bring this paper to the next committee meeting. That's in Hagenberg in Austria on February the 10th. For any of you who fancies joining the committee, we need more bodies. It's an entirely voluntary effort. Anyway, this is where we are at the moment. I showed you how humans and digital machines deal with non-integral values, and then we looked at how this idea has been standardized, how we incorporated that into our standard, and finally, I wondered how we can improve on this, taking us towards portable floating point calculations. Thank you. Ask me 2 questions. 2 minutes.
Thank you so much, Guy. And let's do that. 2 questions, please. So question number 1, over there, please. Thank you. Lovely.
I have a question. Maybe I just didn't catch it during the presentation.
It was quite fast.
Yeah, it was very good also.
Oh, thank you.
How did you actually manage to provide this simulation coherence on those different devices in the game you were describing earlier?
It was the same binary.
Okay, so...
Same binary running on x86 processors. So that level of similarity is sufficient.
Okay,
but for example, on the PlayStation, you're using a different compiler.
Mm-hmm.
So that will give you different, entirely different characteristics. Some compilers are quite happy to put FMA in place. Other compilers aren't. You need to coax them a bit more. And the problem that we have is that things on the command line, for example, are vulnerable to different versions, changing the way that things work. So it is quite a deal creating a reproducible environment on a compiler. I'm not going to say it's impossible, but it's impossible.
Okay, thank you.
One more question, please. One more over there, please, the second row.
Run! Run! Go on down the stairs. Imagine there's a Roman legionary after you with a javelin. Ah, safety's for... Actually, no, safety is for C++.
Got it now.
All right, then, yeah.
Hello.
Oh, hello.
Great talk.
Thank you.
Are there any tools like we have UBSAN and ASAN, maybe some FPSAN to detect that something bad is happening, something that could be not reproduced on other machine?
You're going to have to ask me that again. I'm sorry, I wasn't paying enough attention.
So
it's been a long week.
We have different tools to detect, let's say, undefined behavior.
Yes.
So are there any tools that detect operations on the floating points that could yield different results on different architectures?
I don't know of any tools. If anybody does, do get in touch with me. Unit tests, unit tests would be great. In fact, one of the big problems with reproducibility is in the finance industry. You write some code, you write some unit tests, and then the unit tests work fine on your Windows platform. You then take those unit tests onto Linux, and the unit tests fall over. And that can be really a problem for an industry that's heavily regulated. You know, you've got to then come up with all sorts of regulatory sort of workarounds. It's, you know, honestly, the finance people, the banking people, they were biting my arm off when I said, hey, do we want reproducibility? Yes, yes, we do. You know, oh, maybe you give me some money. No, we won't. But it's the thing they want. This is the thing. It's a voluntary organisation. You know, the committee is made up of volunteers. You know, we're not hand selected by our brilliance. I'm not brilliant. I'm just enthusiastic. So you know, all hands to the. You know, do think about joining. Do think about helping. Poland's full of great engineers. I'm sure we could use your help. So yeah, tools. No unit tests. They highlight the problem. Anyone who wants to write some tools? That'd be great. Got 1 minute.
So I'm going to say, Guy Davidson, thank you very much.
Thank you very much.
Thank you. If you're staying, we've got some lighting talks coming up. If you're going, it's called a lunch break, and don't forget to come back, and we will continue at 2:15. Thank you.
Good afternoon. It's great to see all of you here, especially considering it's lunchtime. To make it worth your while, we're serving up some intellectual appetizers with 2 brief yet highly engaging presentations. My name is Dorota Kostecka, and I have a pleasure to be your host during these lightning talks. Let's kick things off with a hot topic that's buzzing in the tech world, DevX, which is short for Developer Experience. Our next guest will go deeper in the context, exploring how positive DevX can be achieved and its impact on business gains. Introducing our esteemed panelist, a seasoned IT expert who's navigated the entire spectrum of roles from developer to architect and project manager. With a PhD and a deep passion for teaching, he seamlessly blends technical knowledge with business psychology. As a regular contributor to Programmista magazine, he delves into complex technical topics and insightful peopleware concepts. Please welcome Maciej Norberciak.
Hello. Let me share a revelation with you. Software is eating the world. Every top company in the world, and by top I mean top economic performers, are software companies. Big tech. Ta-da! Yeah, thank you, Captain Obvious. But when you look at it, just Microsoft, out of those companies, produces and sells some software. The rest produce software internally, but they don't sell it. NVIDIA sells hardware, the Amazon sells pretty much everything, Tesla sells dreams and promises, and some cars I've heard. Apple, oopsie. Apple is not even a proper company, it's a cult. And Alphabet and Meta, they are saying ads and you, I mean the users. No, what I meant by software company is that those companies and many others produce software internally in order to use the software to differentiate from their competition, and not just big tech. Big pharma, big oil, big banks, big retail, big consumer goods, all the big money companies are software companies. And what do those big money companies want? Of course, they want more money, yes. So imagine that you are a consultant, and one of those big money companies come to you and asks, dear Mr. Consultant, we would like to have more money, can you help us with that? And you say, first and foremost, gentleman does not talk about money, we talk about revenue, so you want more revenue. What is the limiting factor of your revenue? Oh, you are a software company, so the limiting factor is obviously your capacity, your ability to produce more software. More software, more revenue. In order to have more capacity, you need to hire more developers. Here is my bank account. Okay, yes, Mr. Consultant, thank you for this fantastic piece of advice, but you see, we already did that and that happened. And we hired more developers, and they actually started to produce more software, but yeah, they are expensive and they are eating into our bottom line. We also found out that those new hires are not that good because good developers are few and far between and expensive and entitled and have many more vices. So you see, Mr. Consultant, we need to make do with what we have. All right, it's not a problem, of course. You have to simply make them more productive. And before you will do it, you need to measure the productivity in order to establish a baseline. Oh, Mr. Consultant, good news, we already did that. You see, we are measuring the number of code lines, the number of tickets closed, and the number of commits per developer per day, and it doesn't really work. I mean, when we announced we'll be doing that, all those metrics increased tenfold, but you see, we found out that we have just one guy who contributes most of the productivity. And he has this metrics through the roof. We gave him, of course, big fat bonus and a promotion. But this doesn't improve our situation in general. This guy, by the way, he's probably Polish because he has this funny Polish name, Bash Script. Yeah, you see, big money company, it's not like those metrics do not measure the software developers' productivity. They do to some degree. But they are susceptible to something called Goodhart's law. Goodhart was, or actually is, he's super old but very much alive. He is a British economist. And he was talking about British monetary policy, but the law is universal. When a metric becomes a target, it ceases to be a good metric. If you want to evaluate people based on some measurement, they will alter their behavior in order to make this measurement better, not necessarily their work better. So you need to think differently about measuring software developers' productivity. Okay, so Mr. Consultant, please tell us, by all means, how to measure individual developers' productivity. Oh, well, you can't. You can't, because only gods can judge software developers, gods and other developers. You see, software development from management perspective is simple. Yeah? Developers develop, programmers program, write source code. But it is much more complicated. You see, apart from writing these source codes, they also think. They read documentation, internets, source code in order to seek information. They also communicate a lot, and sometimes when they need to, they even relax. Relax at work. It's outrageous, Mr. Consultant. What to do with that? Let's go back to the matter at hand. You see, software development nowadays is very much a team sport. And in teams, you need all sorts of players. Of course, you need those people who do stuff. They are essential. But also you need people who help them. You need people who remove obstacles from the path. You need people who tackle those bureaucratic tasks, paperwork, all those tickets you love so much. You also need sources of knowledge. People who drink and know stuff, or know people who know stuff, or know where to find people who know stuff. You need people who do maintenance, wobble the cables under your desk. And you also need people who are simply good for morale. My point is that you need to measure the productivity on team level. Oh, yeah, Mr. Consultant, we could do that. We could measure the velocity. They have this thing, story points, so we will measure story points per sprint and we'll see. Yeah, no. It's too simple. You coming from sales, you think that you can boil down all the things developers do into a single measurement. No, it's not really a good idea. You need to make some effort to measure some aggregates. And there are metrics for that. One is called DORA, for example. You measure deployment frequency, the time between your first commit and the delivery to production, how many of those changes needed retraction or patch or hotfix, how much time you need to dig yourself out of a catastrophic failure, and sometimes you also can measure reliability. It's a popular metric. It's popular to criticize it because the correlation is not causation necessarily. There are other metrics like SPACE, and this is an acronym. All good metrics have an acronym. SPACE is an acronym from satisfaction and well-being, performance, activity, communication, collaboration, and efficiency and flow. So there are 5 different dimensions. In every dimension you have a couple of metrics. You end up with dozens of metrics. You can't measure them all because it will confuse you, it will confuse your developers. You have to adjust. You need your context, your company's context, your way of working, your company culture, the things you are working on, the specificity of your development team. My point is, it's complicated, but it's doable. Okay, Mr. Consultant, so let's assume we have a way of measuring productivity of our software developers. Let's go back to the original question, how to make our developers more productive. Oh, it's very simple. You need positive DevX. The what? DevX. Or DX, it's an abbreviation of developers experience. This is how your people think about their work, their company, the technology they're working on, the systems they are working with, the processes, the organizational culture, everything. Okay, I think we get the point, Mr. Consultant. So what are the factors of positive DevX, can pray tell? Oh, their name is Legion because there are many, and of course they are all contextual. But it boils down to 3 dimensions. First, feedback loops. People, while developing software, often wait for something. Some machines, for example, for the code to compile or for the tests to run, but also for other people, for review, for answers to questions. And all those delays introduce frustration and loss of focus and interruptions, and sometimes people switch to other tasks, which is very costly. So we need to minimize the length of the feedback loop, minimize the number of interruptions, so our developers can get into flow state more easily. Flow state, or being in a zone, being locked in, is this state of being positively energized, completely focused, immersed and happy about your work. Everyone who programs has those experiences sometimes. You start to code, you code, you remember, okay, I have to eat something and maybe go to the toilet. Oh, 6 hours have passed. How? The more you are in flow state, the easier it is to get into flow state. The more productive you are, the more your DevX is positive. Finally, cognitive load. This is the amount of mental resources you need to put into your task. The higher cognitive load is, the more difficult the task is, the longer it gets to perform, and you make more mistakes. Software development is not an easy job. Okay, we get all those CIs and AIs and IDs and whatnots in order to make our jobs easier, but at the same time, the systems we are working on get more and more complex over time. So the cognitive load stays quite high all the time, and we need to bring it down by having good clean code, having good comprehensive documentation, having uniform and easy and fast access to tools and resources and that kind of stuff. And thanks to that, we can shorten our feedback loop and get into flow state more easy and have an overall positive experience. It is all interconnected. Okay, Mr. Consultant, thank you. That was brilliant. Here's your check. Now, having taken our money, you can be truthful with us. Please tell us, is it this DevX? Is it a thing? Does it really work, or is it just another buzzword? Big money company, yes and yes. You see, DevX works. We already have some science to prove it. There is research that shows that positive DevX have a positive effect on developers' productivity, but we actually already know it for 40 years. You see, there was this book, or is this book, the bestseller called Peopleware. Authors argue that the biggest problems in software development come not from technologies we are using, but from people we are working with. And they talk about things like focus and interruptions and flow states. And there is even a chapter called Working Here Should Be a Pleasure. And they talk about open spaces and dress codes and things like that. This term, and of course, they have a lot of science inside to prove their point. This term Peopleware was coined in 1977. The book was first published in 1985, and the last edition, third edition, updated with new chapters, with new science, new research, came in 2016. So either this is one of those bestsellers that nobody has read. It happens. Stephen Hawking wrote this book, Brief History of Time. Everybody bought it, nobody has read it. Or there is another explanation. And I can't tell you now because I already taken your money, you capitalist speaks. Trotsky and Marx were correct. Revolution never ends. Thank you very much. If you want to if you want to know more about DevX and measuring developers' productivity, there will be an article by yours truly, shameless self-promotion, in Programista magazine. If you read in Polish, you should read Programista magazine. Subscribers have already access to this edition. It will be in newsstands in a couple of days, I think. Thank you very much. I can take one question or two.
I think we do have a time for one question. I think I have a little helper here with the microphone.
Have you read The Brief History of Time?
I was in high school. Actually, I couldn't buy this book because it was a bestseller. It was sold out, so I read it in the library, a couple of chapters at the time, and yeah, I couldn't understand a thing.
Thank you very much, Maciej. Oh, sorry. Sorry, go ahead.
Test. Okay, it works. Thank you, Maciej, for your presentation. And I have one question. If you had to choose one thing to make a developer happy, what would you choose?
Money.
Thank you.
Thank you very much. Maciej Norberciak. Hello again. It's undeniable that AI and ML are fantastic at crunching data and handling repetitive tasks. But do they also have the ability to support us in more nuanced, human-centric areas? Our next guest will shed some light on the potential of AI-powered tools in improving leadership, emotional intelligence, or decision-making skills. Please welcome a distinguished expert with nearly 2 decades of experience in both industry and academia. Armed with a PMP certification, Masters in Computer Science, MBA, and PhD in Business Leadership, he masterfully combines academic excellence with practical insight. Teaching at Politechnika Wrocławska, he imparts his knowledge on subjects related to management and IT. Various passions like badminton, swimming, and hiking add a refreshing balance to his impressive professional achievements. Here, you can see Erwin on his dream motorcycle. I give you Erwin Wong.
Thank you so much. Hi, everyone. Good afternoon. So you saw me on my dream motorcycle. You know, the funny part is because I'm not tall enough, when I ride that, only my nails are catching the floor. So I need to have long nails in order for me to stand properly. Anyway, so let's start. I welcome you to my talk about AI-powered leadership development. So for quite a while, okay, this example of leaders born or made have been a question that we're asking all the time. Like, for sure, some of you has a leader that you admire. Someone you look up to, right? Like, I really want to be this leader. And then, at some point, you're asking, is this leader born or made? We are asking that question. Well, there's a study from Harvard, okay, from across 80,000 participants with many different multinational companies. And they found out that leaders become dramatically better after their 6 months of leadership development program. So it means that there's a chance. If you want to be a good leader, there's really a chance for you. And the second is, you know, the funny part is we are all asking ChatGPT. And then I tried asking, hey, ChatGPT, are leaders actually born or made? You know what ChatGPT says? Leaders is likely both born and made. While some people may have the natural tendencies that make it easier for them to lead, skills like or other qualities can be cultivated through experience, training, and practice. So ChatGPT is AI, right? So we have heard about AI most of the time. It's the trend nowadays, and you're hearing AI in different technologies. AI refers to the simulation of human intelligence processes by both machines and software. So there are a lot of different applications. Like in health, they can actually use AI to identify a pattern based on the symptoms and provide some diagnostics. In addition to that, in energy, they can optimize certain distribution and make the energy distribution more efficient. Another is in terms of commercial. AI can actually help you create the sales forecast. In addition to that, AI can also provide a recommendation or recommend any product to the customer. And logistics and transport. AI can be used for autonomous vehicles, as well as optimization of different delivery and transportation routes. So, according to statistics, 1 in 10 cars will be self-driving by 2030. I'm sure you've seen this in the news. This is the new autonomous car made by Elon Musk, okay? Next, 64% of business experts expect AI to increase productivity, which is better. Another is AI is expected to see an annual growth rate of 37.3% from 2023 to 2030. In addition to that, 97% of business owners believe ChatGPT will help their business. So, is the world ready for Tesla's new domestic robots? This was just last month. Anyone has seen that news? Quite few people. But you could see Elon Musk releasing their robot that could be used and powered by AI at home. It can help you with household chores, etc. We have also used AI in many different ways. We can use that to respond to texts or emails of your colleagues. You can use that to answer financial questions. I use AI to plan itinerary. Hey, ChatGPT, create me an itinerary in Zakopane. So ChatGPT recommended places for me to visit. It can help you craft an email, prepare for job interview, and write whatever post. AI is very powerful. Now, but the question is, can AI really help great leaders? Yes. Humans are wonderful creatures. We can be smart, creative, and kind. But we can be sometimes messy, inconsistent, and imperfect. So think of it, AI is something like Iron Man, wherein you have an exoskeleton with you, and it will give you additional strength, additional power. It can help you intellectually by allowing you to process vast amount of information and make good decisions. AI can help you emotionally, like deepen your understanding of an employee and advise you what is the best path forward. AI can also help you socially, like understanding the team dynamics and how you can foster diverse thinking and create a safe environment for your employees. So there's a Harvard research again saying that how AI can make us better leaders. AI can make us better leaders, can make us more human. Okay, that despite its challenges and risks, AI has the potential to catalyze a new age of human leadership. So, however, as great as AI can be alone, it cannot make us just a better leader. You have to do something within yourself. And you have heard about many different AI-powered leadership development, which I will talk to you more later. But let's remove the AI part. Let's talk only about leadership development for now. Any leaders here? Can you raise your hand, please? Okay, there are quite a lot. And you know that as leader, how are we being developed by our company? First is there's a set of training structured for us to study, to learn how to really lead properly in our roles. It has been centered about just live training. But now, it's different. Because with just live training, they cannot create a customized learning path for you. But you know, AI can help customize a learning path for you that suits your needs on how you will become a better leader. So it is transforming how we prepare leaders. It will reshape leadership skills, training, elevating our core skills, and introducing new ones. But remember, AI will not make leadership obsolete, but it will compel leaders to work more intentionally on skills that require higher order thinking. So, for leaders, what are your key takeaways on how AI can help you? It can help identify patterns and behaviors on how you can perform better in different roles. It can help you personalize experiences and tailor coaching. It can also help you gain insights into your own performance and behavior. Aside from that, for organization, AI can be used to measure the effectiveness of leadership development initiatives. It can actually be used to identify and develop potential of future leaders. So AI isn't just changing the skills that are a focus for leadership. AI is already transforming how we prepare leaders. In fact, there are a lot of different tools. One of these is this website, FEAI. Okay. FEAI creates summaries with actionable insights. Imagine this. I'm a leader. I have 20 direct reports. I will send them a survey and questions, giving me feedback, and then the AI will analyze it and recommend action on how I can become a better leader. Imagine the power of AI. Second, you can use AI for your next sales pitch. You want to practice your sales pitch? You want to practice for your interview? AI can help you. It can give you recommendation. Okay? It will give you a lot of conversation practice. Next, this talent guard, another tool, okay, it can transform your business in such a way that it can give you 360 feedback. It can help you succession planning. It can help identify potential employees to strategically plan and fulfill future succession planning and talent needs. Imagine that. You have an AI who understands the kind of work that you're going to do in your company, the skills that you need, and the AI will help develop and prepare better leaders for you in terms of how you will have leaders to lead that certain part of your project. Isn't that exciting? That in the future, AI will really transform the way we become a better leader. So now, I think it's time for me to demo, okay? I wanted to show you how AI really actually works. This one, I'm a little bit scared. You know, during conference, if there's demo, sometimes it fails. But I hope it's not. Okay. Hi, Gemini.
Hey there. What can I do for you?
Well, I wanted to talk about my direct reports, and I want to have a difficult conversation with my direct report. Can you help me?
Having those tough conversations can definitely feel awkward. What's the issue you're facing?
Well, he is unable to deliver results. I wanted to talk to him about it. Can you help me?
Okay, that makes sense. It's frustrating when someone isn't pulling their weight. Is there anything specific he's supposed to be doing but isn't?
Well, he didn't deliver the project on time. So how do I communicate properly to him?
Okay, so it sounds like this isn't the first time he's missed a deadline. That makes it a little trickier. How about we try framing this as a chance for him to improve, rather than just focusing on the negative?
Okay. Can I practice what I will say, and can you help me? Give me some recommendation?
Absolutely, I can help with that. Let's start with what you want to say, and then we can figure out how to make it have the biggest impact.
Okay. So that's one sample that I wanted to show you. So actually, if you try that, the AI will help recommend how you will rephrase it properly, will give you points on what to say, what not to say, how to understand your employee deeper, and also it will help you craft a good communication path, a training for you to become a better leader someday. So AI is really exciting. I hope you see the power of AI on how we can leverage AI. That someday, those skills or trainings that we have to be face-to-face or we have to do the same pattern all throughout, but rather it will be a customized base and a training that will really be suited for your needs. So thank you. That's all that I have to say for today. If you have any questions, please let us know, or you can add me in LinkedIn and we can connect and talk about AI or leadership. Thank you so much.
Now, do we have any questions to Erwin? Over there? Yep.
Okay, Erwin, what do you think about the security? Because you will share with the AI or any other application your personal data information about the company. How you then feel that you are sharing that? And of course, these AI tools are not regulated, not controlled by anyone. So it's like really open for everything. And are you not afraid that later on that could be used by someone to profile yourself there?
I agree. Thank you. Really good question. Nowadays, we all know that security is a challenge with AI because everyone, we don't know who's going to read that data. But you're correct. One thing I wanted to promote is that in Nokia, we have Nokia GPT, wherein we have our own version of AI, wherein the company told us that if we wanted to use certain questions, rather than putting it in ChatGPT, wherein it's public, we can use our own Nokia version GPT so that the security is much safer. But you are correct. We have to be careful in terms of what we divulge in AI because it can cause some harm which we do not want. So, well, if you don't want the tough conversation to happen, you can just talk about yourself, like how you wanted to grow, what skills you need, and AI will help recommend you. Thank you. Any other question?
Erwin, I have one. I'm here.
Yes.
Okay. We know that the AI at this stage, there have still problems with the hallucination, the bad data that provides you. So once you would like to build the real leader with the big knowledge, with the big power, do you think we are ready now to ask tough questions and rely on the answers from the AI?
Okay. So in terms of building a really tough leader coming from AI, I don't think it is super duper 100% ready right now that you will just rely on AI. AI provide you recommendation, but it's not that AI will be your only solution. But I agree with you. When I did my research, because when I was doing some study on how leadership will grow, as you know, my PhD is about leadership. That's why I'm really curious about topics in terms of leadership. And then on parts where how we can use those recommendations by AI, the good news is some of them are really based on studies. So they provide good recommendation. But it's not that AI is fully reliable, that 100% you'll trust your life full learning with AI. You have to judge it, be fair on what you will get, and then, but using that as a stepping stone, AI is really very helpful. Dziękuję bardzo. Okay, so I think we're finished. Thank you. It's an honor to present to you my topic. Have a nice day, everyone. Enjoy the conference.
Thank you very much, Erwin. It was fantastic.
Thank you for your punctuality. How was lunch? Okay, this kind of lame energy means it's been wonderful and you are just a little bit asleep having eaten such great food. But the next speaker is going to energize you as ever. We've had Andreas before. So, you know, there are those Code Dive speakers. We tried to keep them away, but we can't. And they keep returning. Why am I not surprised? So, Andreas Fertig, he's CEO of Unique Code, and he's an experienced trainer and consultant for C++ standards 11 to 23. He is involved in the C++ standardization committee developing the new standards. He publishes specialist articles and textbooks, of course, on C++. And with C++ Insights, Andreas has created an internationally recognized tool enabling users to understand constructs even better. Previously, he worked for Philips Medicine Systeme as a C++ software developer and architect. And interestingly enough, Andreas' very first C++ book, you'd never guess what it is. He bought it in 1998, and this book still sits on his bookshelf. And the book was Scott Meyer's Effective C++ German edition. Let's have a look, shall we? In case you didn't know, Andreas keeps his books upside down. But this is the one, and again, some people, veterans of Code Dive, may remember Scott Myers was a speaker at this conference as well. So it all falls nicely into place. Ladies and gentlemen, and everyone in between, Andreas Fertig.
Thank you, Raphael. Hello, everyone. I mean, I cannot really see you, but one question first. Who is left-handed? Please, show of hands. All right, because I was wondering whether my upside-down picture came from the fact that I'm left-handed, and I tend to, well, turn the phone different than the right-hand people, and so it might turn up upside down sometimes. But anyways, you can fix that, of course, in software and with C++. Welcome to Code Dive. Welcome to my talk, Fast and Small, C++ When Efficiency Matters. Raphael already introduced me, so there's a little more to say to that. Why do I have the German version of Scott Meyer's C++ book? Because I am German. So that means that I speak German and I can read it perfectly. And at the time, I wasn't very keen about reading things in English. Nowadays, I switched that. My last name is a very German word. It's not really a very German name, but it's a very German word. It's an adjective and it occurs frequently in the language, more often than you think. You can translate it to finished, ready, complete, or completed. So everybody who finished their project basically uses my name. You can use that in other contexts as well. Sometimes it's really hard to distinguish the context. What do you mean, finished or ready, right? The one is the opposite from the other. So if you use just the word fertig, you have to listen very closely at the context to infer whether it means the one or the other. But I guess if you learn German, you know that's sometimes the case and not always very easy. I constantly have a disagreement with my spell checker. It's a very smart thing, so it's right most of the time, except if I sign something and my name shows up, because then in the middle it thinks what I'm trying to say there is Andreas is fertig, and not that's the name. So it tries to spell it with a lower first letter instead of a capital one, because, yeah, it's an adjective, right? So I couldn't teach it to do that any better in the past. But we are not here, or at least I'm not here to give you a German lesson. I'm not really a good German speaker, despite I'm German. I think I'm best in C++ grammar, not even an English one. And we are here to talk about fast and small software, right? Because that's important. I worked a lot in embedded software development for my career before I started training and consulting, but I still do a lot of these domains. And usually you have devices that are somehow constrained, and constraints can be that you have a physically very tiny device, but also in terms of memory resources or CPUs. So you might have to squeeze a lot of functionality in only a few kilobytes of RAM or ROM. So you want it to be small, but on the other hand, you might have timing constraints and you cannot lose your edge there, so you have to be fast. And in my experience, it's usually the one or the other. You have rare times when you can win both to your favor. So today I like to present you a couple of techniques, things I saw, where you can try to achieve either faster or smaller software in C++. So the first thing here comes from the standard library. What you're seeing on this slide is hopefully something that you already used extensively. It's a declaration of a unique pointer object f. And that unique pointer, it maintains a file type. And I'm working a lot with Unix, Linux, so I use POSIX API here, and that's a very good example. If I do a fopen to open a file, I get back, sadly for presentation, an object named file. So the type of that thing is also called file because it was easy, I guess. And what I'm doing here is I use the less frequent version of a unique pointer, at least to what I see on daily basis. And this is that I provide a custom deleter to my unique pointer. So this is why you're seeing a unique pointer version here with two types instead of the usual one. The first one is the type of what the unique pointer here wraps, so my pointer type. And the second one is some callable that's invoked instead of delete when the unique pointer gets destroyed. Okay? And this helps me that I can have a fopen returned object wrapped in a unique pointer such that once I'm leaving scope, the file is automatically closed, which is a very nice thing to keep your resources safe and let the infrastructure maintain it automatically. Now, to achieve that, I not only have to provide a second parameter to the unique pointers templates parameters, I also have to provide a second parameter to the constructor, telling it or teaching it that the function we are talking about is called fclose. So I pass in a function pointer to that. And it works perfectly. I'm happy with that. I have a safely maintained resource here. That's perfect. But how about efficiency? So what's the size of this unique pointer now? We aim to say a unique pointer is just a simple wrapper around the raw pointer, so unique pointer size should be equal to a pointer size, right? I think we still have a few of these unpleasant spots in the front if you want to join. I personally don't like them either, unless I'm on stage, but feel free, there are a few left. So if we check out that unique pointer size with, let's say, a static assert, in my particular case, it turns out that the size of this object f is greater than the size of a void star. So this unique pointer version here, it in this specific case has twice the size of a pointer. Because internally, the way I've written it, we have, or the unique pointer has to store two pointers. One for the actual data and another one for the function to call in the case we want to destroy it. That's fine. There are use cases when this really is all right, but in this example, I beg to differ. Because I'm calling a function fclose, there is no real runtime-ish thing going on where I have to decide which actual function I want to call upon destruction. It's fclose, and the address of fclose is known at latest as link time. So I have the address. Why store it in a pointer and not only waste storage space, but also have this indirection and store the address? It's little, but it's a waste of resources. So what can we do there? let's first start saying that in the way I use the unique pointer here, the second parameter, it's always there. If you don't provide any, the infrastructure, the standard library here, uses something that's called a default deleter or default delete, which, as I present here, is a class template with only one member function, and that's a call operator. That one takes a t star. The t comes from the template parameter, and internally it simply calls delete on the parameter that gets passed to. So whenever you use a unique pointer with just one template parameter, it always does this trick, at least in most of the implementations. So it never calls delete directly, it always goes over this default delete. So that's one piece of that. Now, how does the implementation of a unique pointer look like? A unique pointer's implementation can look like that. It's a reduced version based on more or less libc++. And it takes, well, no surprise, a class t, that's my first template parameter, and the second one, I call that one del here for deleter, and that one gets defaulted with the struct I just showed you, default delete of t. Now, if we start looking down in A here, we can see that in this instance here, my unique pointer does not directly store two pointers. It stores or it creates an object called compressed pair, and that one is typed with del and t star. And then we have the regular functions here, the constructors in B and C, so the one for one argument, constructing just a unique pointer with the default deleter, and a unique pointer with two arguments for the pointer and a custom deleter. And in each of these two cases, the data is simply passed forward to mpare. So mpare is the next thing we will look at. If we stay with the unique pointer, we can see it does the usual thing, right? It's not copyable, so the copy operations are deleted. It's only movable, so I implemented them here. And if you look down to D in the destructor, then it's, I think, worth to know that compressed pair is a utility class used frequently in the standard library. It's not just for the single case of unique pointer. And that's the reason why, if you look at the unique pointer, it might look very odd, because the check here now in the destructor of unique pointer is checking whether mpare.second returns false. So it's comparing a pointer or observing some Boolean value. And if that's true, then we are invoking mpares first with mpares second. So you could say mpare.pointer. So this is the check. If that's not a null pointer, then let's invoke mpare.delete with mpare.pointer. That's essentially what the code here does. Now, the compressed pair is this one here. And I had a hard time to decide which code to show you. I decided to go for the C++20 implementation because it fits nicely on one slide. The pre-C++20 solution would not have fit in one slide. So upgrade to C++20 if you can. What you can do in C++20 to make this code so small, so tiny, is to say, okay, compressed pair here, I think that was obvious from the slide before. It's a class template. It takes a deleter and a type name t. I used more proper names here. And then compressed pair comes with two member functions, first and second. First being of type del and second being of type t. And I'm using an attribute here that was introduced with C++20, no unique address. And what this attribute means is if the object del.t is empty, there is no requirement on your compiler to allocate storage space for this object. So you might have heard of a similar technique that was present long before C++20, EBO, the empty base class optimization, which roughly says if you have a class with no non-static data members, so you can have member functions in there, but you cannot have member variables that are not static, then your class basically occupies 0 storage space. But the moment you start asking it with size of, hey, are you 0? Your compiler says, well, the size of this struct is 1, at least 1. Because everything in C and C++ must be addressable. And to have an address to something, you need at least the size of 1. So EBO says, if your object has technically the size of 0, and you use this data type and derive from it with another data type, then the second data type size is just its own size, and the size of the base class does not contribute to the size because that one is 0. And this is the reason why the pre-C++20 solution would not have fitted in one slide, because I would have a lot of inheritance going on there. With the no unique address, you basically have this optimization on your hand. You no longer need the inheritance step to do. You can simply say, I'm interested in this type and the features of this type, in this case being the member functions. And no data members are required for me here. But I also don't want to do the inheritance dance because I don't want to model any is a variant or whatever. So no unique address here basically says if any of these types has the technical size of 0, so no non-static data members, it will not occupy any space in this structure. Remember the custom delete I showed you? The only thing it came with was a single member function, a call operator that invoked delete. So it had the size of 0. So that was the first thing that fulfilled this requirement. And that means that in my case here, the data structure first member, it does not occupy any storage space in the structure. My pointer, T, second, yeah, that will take up the size of a pointer, of course. Somewhere I have to store the information. And then I have the two constructors here, my compressed pair with one argument and with two arguments, initializing the two data members. And with that, you have that efficient tool in your hand that you can say, if you have data that you want to wrap somewhere where you're only interested in member functions and not in the data, but you do not want to store a pointer to that thing because you always only use these member functions, you can tag them with no unique pointer. And then it will not occupy any storage space. Or pre-C++20, do the dance with the inheritance and have an empty base class. So this is the heart of everything here, the compressed pair, because that one ensures that the custom deleter does not occupy any storage space. In the default case, right, because the version I showed you, the static assert, still proved that it occupied storage space. So let's optimize that one. We can write a better version of this delete with a custom deleter for file object than I showed you initially. And I'm continuing to use C++20. This is a utility that I like a lot. You can call it better. Maybe I refer to it as unique pointer deleter. So it's a unique pointer with a custom deleter. It's a using alias that's a template at the same time. So it comes with a template head. It takes a type named T and a C++17 non-type template auto parameter. Call that one delete fn. So that's my function pointer that gets invoked and deletes everything or frees everything, closes everything, whatever the action behind this is. And my unique pointer deleter, it's a using alias pointing to a std unique pointer of type T. And now the magic happens. The second parameter, my custom deleter, as I said, I'm using C++20 code here. So that one uses a decal type on a capitalized lambda. Because in C++20, you can decal type on a capitalized lambda. Decal type on unevaluated or have a lambda used in unevaluated context. And because it doesn't capture anything, it's not used or it can be used in that context. At the same time, because it doesn't capture anything, if you remember how lambdas work, internally they are just classes, and our captures are data members, and the call operator is a member function. Since I do not have any captures, I do not have any data members in this class. So I only have member variables, or member functions. And exactly one in this case, and that's the call operator. So this lambda here that does the same thing as the default delete that I showed you. It's basically an empty class with just one member function. And my member function here takes a t star. I call that parameter obj, and then internally I invoke delete fn with this pointer parameter obj. So that's totally transparent to everything. It can take everything that's invocable, and my usage here then is that I say unique pointer deleter of file of fclose. So I teach that thing the function I want to have it to invoke upon destruction, but my constructor just takes a single argument as usual. So I find that syntax way nicer because my users do not have to pass 2 arguments to their constructor, which seems odd somehow. And I do not have to repeat myself because I say fclose only once. That's the thing I want to invoke upon destruction. And now if you look at a static assert here, you can see if I check now whether the size of this object f is now equal to a void star, that static assert passes because I employ the same trick as the standard library does it by default with the default delete. So this is how you can optimize code where you use a custom deleter, but your pointer is basically, or the function that you want to invoke is known at compile time. Okay? Before, I added the size of one pointer to each instance of this unique pointer object. Now I reduced it. So you can see it either way. Maybe you just reduced your code by 50%. It's a good measure, right? Maybe don't tell your manager it's only about 8 bytes or so, but 50% is a better sales pitch. It's all about sales, even in programming. Can we do better? If you really want to squeeze out the last few, let's say, instructions, can we do better? There's still something that we can say it's not perfect. Remember how lambdas work? Lambdas are class type. They have this call operator that then gets invoked when we invoke the lambda. And since they're a class type and we have this call operator, a call operator is a member function, right? What do you know about member functions? The implicit things. The this pointer. Each member function in C++ takes this implicit first argument, the this pointer. And in C++23, we call it the implicit or explicit object parameter thanks to deducing this. But there is one parameter that this function always takes, and we know it's useless because there are no data members inside this class, so there's nothing that we would access with the this pointer. In C++23 now, you can do one thing better. You can mark your lambda static. That means that the call operator of this lambda is now static, and it has the same implications as if you make any other member function a static member function, that it does not come with the implicit this pointer. And by that, you are squeezing out 1 to 3 assembly instructions because the this pointer has not to be prepared and not to be passed. It depends on your architecture and usage. But this is what you can do on top if you have C++23 on your hands. It's not required to, or it doesn't work only on lambdas. You can put it on every call operator or every array index operator in C++23, but on lambdas alongside them. So that's an optimization you can do there. All right, so we had unique pointer. Are you using the standard library? Just by a small show of hands, as I said, I can't see a lot. Thank you. All right. Seems a lot of you. So you might use std string. And you might have heard of the small string optimization. So if you're looking at a std string, at some point we decided that allocating just a single byte from the heap might be somewhat of an overhead, and doing that frequently. So we looked for better techniques, and the one that's present currently is called the small string optimization. And that means that for a certain size of small characters, so let's say 16 or less, we do not go to the heap, we store them on the stack. So every std string object comes with some internal array which then lives on the stack. So if we are about to design such a string class, we can say, okay, we know that we need the size to be stored. So how many characters are currently in that string? We also need the capacity, because that's how many data can be stored there totally before we exhaust the dynamic memory and have to reallocate. Of course, we need a pointer to the data, and since we want to implement a small string optimization, we need something like a car array, let's call it MFSSO buff, with the size of, let's say, 16. And now, since we introduced two modes to our std string, small or large, we need to store the information in which mode we are operating somewhere. So let's add the Boolean to that, let's call it MISSSO, and say by default it's true, we start always in small string mode. So we carefully design that, and if you look at the static assert, that nice little structure consumes 48 bytes. Which is a lot, given that we tried to optimize for the small bytes, right, for just a few characters. One reason that it consumes that much storage is the so-called padding. So if you ever heard about that or haven't, C++ Insights can visualize that. If you look here and turn on the show padding information and then do the transformation, C++ Insights tries to show you nicely that this structure here is size of 48. It's aligned at an 8-byte boundary, 8-bit boundary, and and here is where all the stuff starts. And then we can see it ends with 7 bytes of padding. And this is because we squeezed in the 16-byte buffer and then a single Boolean, making that not really well padded. 7 bytes wasted in some of the embedded systems I worked with, that's a lot. That's a good fraction of the entire storage space that was available. So it doesn't seem the best to do it like that. So what I'm going to present is a short version of what the standard libraries do. Okay, so it's not my work, it's also a reduced one. The first one here is libstd.c++, that's Clang standard library. They say they have this structure and they store a pointer first and then a size. So that's what we worked out, right? But then they use a union because they say at one point we only need the capacity or our small string buffer. And to make all the implementations look similar, I decreased the size of the small string buffer here. I'm using 8. The real capacity is larger, it's more 16. So they say we only need the one or the other because we are either in small string or medium string mode. The entire structure here now consumes 24 bytes, so that's way better than before, but we only have 8 bytes for small string optimization. Then we have a couple of recurring functions here, maxcap, that tells you how many characters you can store in total. That's simply the size t's capacity. SSO capacity tells you how many bytes or characters can be stored in small string mode, and that's my SSO buffer capacity and buff -1 because we have to store the null terminator somewhere. So in this case, we can store 7 bytes of payload. And then we have a function to check whether it fits into SSO. And the next function is where they do the trick. Is_long. So is_long answers the question, are we in small or large mode? And what they do here is to say, we check whether pointer points to mbuff, so has the same address, or not. If it's a different address, we are in long string mode. If it's the same address, we are in small string mode. So this is how they removed the Boolean. They have this information already stored somewhere. Then we have the constructors for default construction, constructs a small string. We have a constructor taking a const star and a size t. That one checks whether the string fits into SSO. If so, it initializes mptr with mbuff. Otherwise, it would allocate dynamic memory. And then it has to check again, are we in long mode? Then we have to update the capacity, and finally would copy the bytes over, of course. Now, size and data in this implementation are now simple. They simply return the member functions, but capacity comes with a branch, because capacity now has to check whether it's in long or in small string mode. So this is where you're paying for. This is the check that has to be done. As I said, this is GCC's implementation. This here is Microsoft's implementation for the Microsoft Standard Library. They start differently. They say, well, we have this union and we decided that we only need mpointer or mbuffer. So it's nearly the same implementation, but they played the trick differently. And after that, they have size and capacity. This structure also sums up to 24 bytes. Their SSO capacity is also whatever size t gives you. SSO capacity itself is 7 bytes as previously. And in is_long, they are now checking whether the capacity exceeds the small string capacity. So this is how they store the information. They say we are using capacity all the time, but once we know the capacity exceeds SSO, we are in long string mode. Otherwise, we are in small string mode. Now, in their constructors, they start with small string in default construction. They, in the 2-argument conversion, they initialize mbuff here to give the union a defined member. Then they initialize size with the length. For capacity, they check whether it fits into SSO or not. If it fits, they initialize that one with the SSO capacity. Otherwise, with the length we have. Next, in the constructor's body, dynamic memory will get allocated in long string mode and data will be copied over. This implementation here now makes it easy to access size and capacity, but it comes with a penalty on data, because data now requires the branch, because we don't know whether we return pointer or a pointer to the small string buffer. So we squeezed the two together, but now we have penalties there. And this is something where you also have to check what you want to optimize for. Is data a fast path that needs to come out without branches, or are the others better? I personally don't know. I'm just showing you the implementations. I assume they measured and came up with a good idea. Now, the third implementation here, it's the newest among all of them. It comes from Clang, so it's Clang's standard library, libc++. And for all the quick readers here, you can see the last part on the slides says to be continued. So this is the first implementation that even in the reduced form doesn't fit on the slide anymore, because they are doing real interesting things. I like these bit fiddling things. I've done that a lot, and they are doing it. So what they do, they basically start out and say, we have two structures. Let's call the first one normal. And normal contains a size t large, a size t capacity, but they're bit fields. My large member is a bit field of exactly 1 bit, but of type size t. And capacity is a bit field of the size of a size t minus 1 bit, because we just spend that on large. And then we have a regular size t size and a pointer data. SSO, the other structure, that one says we have a single bit here for large, and followed by that a array, another bit field of uint 8t, which has the size of uint 8t minus 1 bit. And then we have a couple of padding bytes in there, followed by data. And data has the size of normal minus the size of a size t. So that data here has 16 bytes of payload. -1, as we will see on the next slide, for the null terminator. We pack the two in a union. We say we have small and large. The total size here is still 24 byte. And max capacity now is a reduced version because we did the bit fiddling. SSO capacity is the capacity of SSO data, so 16 bytes -1 for the null terminator, fits into SSO, and all the rest you've already seen. So this is their implementation. This is the one which gives you, even in the real world implementation, the most amount of small string capacity. But you're paying for that because if you look down to size, data, and capacity, now each and every of them comes with a branch because we have two unions and we never know in which state we are. So more SSO capacity, but maybe more branches. It's your decision, basically, what you want to optimize for. But this is what the implementations do. So this is enough standard library, right? Let's talk about something else, constexpr. Jason Turner does a talk later about constexpr, so go and watch that one. Here's one slide for me. This comes from a client. I had a consulting job there. They called and said they're close to the release and they're running out of memory. So they wanted some help to reduce the memory consumption. And I was looking at the code and I figured out that the device, it was a small device, networked, and it basically passed around strings. Call it a string distributor. No offense. And the heart of everything was a class called fixed string, something maybe similar we are getting in C++ 26. It comes with a non-type template parameter n, and this gives the size of an array that's stored inside fixed string of type char here, and the fixed string class also comes with a size t for m size, so we are carrying around the size. Then we have a default constructor. We have a constructor that takes a const char star, figures out the length, and copies everything into its internal buffer. There is a function size, and there's a function data, which grabs the data out again. And this was extensively used. They had two basic usages. One you can see in line 24. That was their first attempt. They said, okay, developers, let's use that fixed string class, and they make the mistake to tell them count the length of their string. I mean, who wants to count the length of characters, right? We are developers. So most of them sat down and said, yeah, 50, some 48, because it's such a round number. That should be enough. Okay, my string fits in, everything compiles, it's nice. They updated that and said, okay, we squeeze in another function called makeFixedString. That one uses template tricks to deduce the size of a fixed buffer and instantiate fixed string with a perfectly matching number. So the second one is obviously the better one. And as I show it, the two static variables here, x and y, they were static and const already. But when I came in, I figured that one out after a while and asked, why not make it constexpr? And they told me, because it will not change a thing. It's already static, it's already const. What will constexpr do? I was on their budget, so I had a little fight to get the time to add constexpr to like 10-ish places or so. And this here is Compile Explorer. I assume you all know Compile Explorer. And this time it's a 3 window version. On the left, we have the fixed string class. That one here has constexpr in capital letters here all over the place, so that indicates a macro, right? And I made the two variables constexpr as well. And then I have two compiler runs here. The one in the middle, that one is the original version, so I'm using C++20. I define constexpr to nothing, and I use 0. And the one on the right, that one defines constexpr to really be constexpr. Now, if you look at the original version, that one comes up with 209 lines of assembly instructions. There are a few blank lines that Compiler Explorer inserts, but let's ignore them. My constexpr version comes up with, oh, beautiful, 78. So it did cost me less time to add the annotations there than fight over the budget. And it's already way down. But they didn't compile with 0, right? So let's be fair and realistic. In 03, the original version uses 42 lines of assembly instructions. That's way better. The constexpr version, 31. Well, still better, but not that good, comparing assembly instructions wise, right? The main difference here comes solely from this piece of assembly instructions. What that thing does is it initializes your static data. It initializes your static objects, calls the constructors. So what happens here is real bad, because what's happening here is that the machinery says, oh, we have this string in the ROM, and now let's spend time and stack space and copy it from ROM to RAM to make it accessible to you. So this 10 instructions difference, it's a big difference. It consumes stack space and it consumes your runtime. Okay? This is not present in the right compiler run, because there is no reason to run a constructor at runtime. Look at this, because the compiler here perfectly understands the layout of my object. It already has it there. It can tell in assembly, that's your object X, and the first part of this object, this is the size, it's 22, followed by the string, followed by padding, because the developer simply said 50 bytes, followed by another padding because fixed string structure isn't perfectly aligned. And the same thing for Y, just with one padding, because that one is perfectly trimmed to the size of the string. So while we only have 10 lines of difference in assembly code here, the left-hand version is slower at startup, and it consumes your precious RAM, stack space at runtime. So this is what constexpr can do for you. This comes from a real-world example. At least at the moment, I cannot do any better on telling you constexpr is really worth it. And if you still believe me, and even if you do, go and watch Jason's talk later. Okay? So I hope you had fun. I could tell you some things that you haven't heard before. And before, I think we have a microphone here and open for questions. Let me say I had fun. Thank you. I'm Fertig. Thank you.
Thank you. Thank you so much, Andreas. And I think we've got if you'd be so kind, time for 1 or 2 questions. So questions, please. One over there in the second row, please.
Yeah, thank you for the talk. I wonder about memory utilization, but the compiled code. I think it was on slide number 8 where you showed how to use a lambda to wrap the deleter. And I believe, oh yes, here.
That one?
Yes, so there's a lambda in line 3, and I believe it will always create a function in the final binary. And that function, the only thing that it does is to forward to the actual function. So can we do any better? Do we need to pay that price?
I think we, at least to my knowledge, cannot do any better. Your optimizer might do, but you have to invoke that thing at some point. The only other option you have is, but that would eliminate that use case, to say you have two different versions of unique pointer. So a specialization, one that only takes one parameter and the other one that takes two. But with a custom deleter, you still have to store that information somewhere. So your optimizer might be able to peel off the first layer, but I'm not sure.
Okay, so if it's worth the extra step, then we can provide this specialization if needed.
Yeah, if you implement the unique pointer yourself, then yes, you could think about providing a specialization instead of packing everything in one implementation, but you would pay a different price. So question is, which one is the better for you?
Thank you.
You're welcome.
Thank you so much. Any more questions, please? One over there, thank you.
Actually, I wanted to ask the same thing. However, I have kind of an idea how to do this. Basically, I guess you could write a specialization for the template for function pointers, because you can make a template argument as a function pointer, and then the address itself is like kind of baked into the unique pointer type, and then you can skip the.
So you would basically say use this as the template head for a specialization of unique pointer. Your delete fn carries the information for.
Yeah. So you can either have like a general version of the template where the delete function is anything that can be called, for example, a lambda, or a specialization for function pointer explicitly.
Yeah.
And then skip the.
Yeah, you can do that. That's what I said. It's a question what you're optimizing for, because now you have twice the code to maintain.
Okay, lovely, thank you. Perhaps one more? Any more questions, please? First row, please, thank you.
Yeah, hi. So on one of the slides you showed the Clang's implementation of the short string, right? And there were a line where the union access was indiscriminately accessed. Isn't that undefined behavior in C++ to access non-active union member? Or is there any exception in the standard that allows that? I believe it was this is large method.
So you're talking about this here, and basically the straightforward access in is long to packed small that large, right?
Yes.
And exactly. You phrased that question so great for me just to answer, yes, there is special wording for these circumstances in the standard, not for std string, but in case if you're interested, I'm not sure I can bring that one up here. The section in the standard you're looking for, I'm failing to do that. Wanted to show you. Okay, it doesn't work. The section in the standard you're looking for is class.mem.general, and you want to basically look at paragraph 28, and I've written that down. I'm not knowing that from the top of my head. This talks about the common initialized sequence. And the reduced version, and turn the internet off for that answer, is if you happen to have two types that are coming without constructors and destructors, so just a bunch of bytes, and they have the same signedness and the same length of bits, it doesn't matter which one you're accessing.
Okay, so generally, if I am sure that this is well-defined access, I can do that without violating the undefined behavior that otherwise could be invoked here.
Yes, there is no UB here, but if you do this at home or at work, be really careful to understand the rules, because it only works in exactly such scenarios.
Okay, thank you.
You're welcome.
Thank you so much, Andreas. Thank you so much for your talk. Thank you for answering the questions, and you are now officially done. Everybody, Andreas Fertig.
Thank you. Thank you.
As advertised, we're going to take a short break and continue in just under 15 minutes. Thank you.
Thank you so much. Yes, thank you.
Thank you so much. Welcome back, and it's time to continue. And let me introduce our next speaker. Nevin Liber is a computer scientist in ALCF division of the Argonne National Laboratory in the US, where he works on COCOS, sickle, sorry. Looks like cycle. Sickle and Aurora, one of the world's first exascale supercomputers. He also represents Argonne on the C++ and Sickle committees as various chairs. He has worked in C++ across various industries and platforms such as big data, low latency, operating systems, embedded telephony, and now exascale computing. Now, the fun fact about Nevin is that he once went to a real Star Trek set, the Next Generation set, but he got a little spooked by Spock, so thankfully returned to a much safer C++, and that's why he is here with us today. So let's show him our appreciation. Nevin Liber.
Thank you. So, first of all, I'm a little scared because I'm in the official Argonne slide decks. If you can find my picture, you can look later. But what we do is, so I'm in the leadership computing facility of Argonne. We're trying to, we have a supercomputer called Aurora. It just got bumped down from number 2 to number 3. And we just do really cool research. I mean, Argonne does battery research, material science, physics, and this is to help enable it. We're also working on an LLM called Aurora GPT to run on our supercomputer. So what I do is, as he said, right, I'm working on C++, COCOS, Sickle, and on Aurora. The committee, I am the vice chair of the Library Evolution Incubator. I'm the admin chair. I'm also the vice chair of the U.S. delegation to the International Committee. And on the Sickle committee, I work on C++ compatibility. I'm the chair of that. So what is a variant? You're going to learn, that's about all I really know about type theory, so don't question me on it, please. But it's a discriminated union, right? It's a union that knows what type it's holding, right? And so there are product types. Those are things like, structs and classes, and generically we have a tuple that got added in C++ 11. And a sum type, the union, and now variant there's a few more sum types. Right. The 3 we added in 17 are any, variant, and optional. Any, by its name, can hold, it's a concrete type where there's no template parameter. Discriminated type, it knows what it holds, but it's open. The set of acceptable types is not bounded. It can hold any type that's copyable. And a lot of that is because the way it's implemented, roughly under the hood, is there's a virtual function that gets generated to do the copying. And because it's a concrete type with a virtual function, that has, the copy constructor has to exist. Even if you never copy the any object, it's still that code gets generated and must exist. It's just an artifact of how C++ works. But there are runtime efficiency concerns by using this. Like, if you want to find out what type it holds, it holds one of 20 types, it's cascading ifs, and that's order n. And one more thing that's going to come very important is that why do we want a no except move constructor in this kind of thing? This one has, yes, any has a no except move constructor. And because of the exception safety guarantees that Dave Abrams came up with. Like, the basic one is invariants are preserved, but no resources are leaked, so the object still can be destroyed, assigned to, etc. Strong means either the operation happened or it didn't happen. So you know exactly, it's in one of 2 states. Like, if an exception gets thrown, it's back in the original state. Otherwise, it's in the new state. And then, in order to build some of these, you need to know some operations that are no-throw. Operations you know will not throw an exception. And this will become extremely important in the design. It's the biggest influence in the design of variant that the committee did. So, why is no except move construction desirable, right? Well, it's an optimization when we're, say, growing a vector, right? If you want to grow the vector, right, it's at its capacity, you do pushback. So you allocate new space, and if it's got a throwing move, it's going to actually copy the elements because it wants to maintain not losing information. However, if you have a non-throwing move, then it just moves the elements in place and releases the old space. So that was a lot of the motivation for adding move semantics to C++ back in the day. And one optimization where we need no throw is swap, right? Because if swap throws, then we don't know the state of either element, the left side or the right side. And it turns out throwing move constructors don't play nicely with variant. And a lot of my talk will be just why not. So we have variant, and again we said, it's a templated type, right? Its template parameters are all the different types it can hold. It's a discriminated type. It knows exactly what it's holding. And in theory, it's a closed sum type. It holds exactly one of the n possible types that you've listed as template parameters. So for variant, right, the set of types is specified, right? So we can get space efficiency. We know the biggest type it can hold. We know how many bytes internally. We don't have to allocate things on the heap. And it turns out we can do runtime efficiency too if we use visitation. That can give us order 1 access to the object. And the third is optional, which is a templated type. It's a closed sum type, and it holds at most one of the templated type. Right? You can think of it as a range up to 1. People are trying to add that to optional now. So in some sense, it's a refinement of variant with a much easier interface to use. Right? You can use *O for an optional object to get to the value. So this picture's from we were all younger and more naive in those days. This is around when we started standardizing it. There I am, because when you take the picture, you don't get in it, right? So our committee, basically every member there wants to make C++ a better language, even if no two of us can agree on what that means. And ultimately, at the very end, approving the standard is a consensus of countries, right? It's one country, one vote. In the quote the Rolling Stones, right? You can't always get what you want. You have to choose your battles wisely. You can't fight everything. So fight for what you can live with. Now, this is not designed by committee. It's consensus by committee. So we don't really do design. We do a little bit of design in the committee work. For the most part, it's approval. And so when I give a proposal, I try to think of what I can live with and what I can't. And if I have to give up some stuff to get broader consensus, I will do that. If it's too much, I will, not threatening, I will just say, this does not meet my needs, someone else can standardize it. And we know the details matter, right? I mean, we just had the committee meeting here in Roslaw last week. And we know millions of developers will use anything we design in the language of the library. And especially in the library, we know millions of developers will model their types on what we do. It's also very hard to fix things later. C++, one of its strengths, and one of the things people argue about is is high level of backwards compatibility. We try for 99.9%. So when we were designing variant, there were kind of 5 major areas. The never empty guarantee, how assignment should work, how comparison should work, even how default construction should work, because it turns out that's not obvious either, and how to access elements. And there's various trade-offs in these. There's no right or wrong answer necessarily. For the most part, it's different committee members see the world differently, and we will make trade-offs differently. And the trade-offs for variant, there's space efficiency, runtime efficiency, compile time efficiency, and ultimately usability. So ideally, variant would have the never empty guarantee. Unions have a never empty guarantee, which means it would model exactly one of the bound types. But what happens if we relax that to at most one? How does it affect the trade-offs? Like for instance, assignment, right? If A has an assignment operator, should we use it? I mean, that question came up. Because it kind of assumes assignment is an optimization over destroy, then construct. Okay, maybe we should use assignment unless it doesn't have one. Should we synthesize one by doing destroy, then construct? Or should we always do it? Right? There's a consistency argument to be made. We should always do it. That way it always does the same thing. There's a different consistency argument to be made that we should use assignment because that's what people expect. That's consistent with the language. Consistency is a very hard property because it's always consistency with what? Emplace has similar issues. This emplace is creating your object inside the variant directly. So if you take this little example here, you're going to see a lot of this example. Right? Users expect v1 to hold a B object at the end of this. And you have to do this destroy then construct. Well, not quite. We'll get to other trade-offs. So what happens if you create a B object and that's fine, and then it tries to move construct it, and the move constructor throws? This turned out to be the fundamental question when we were designing variant that kept coming up over and over and over. Now comparisons. You could compare things in different ways, right? You can compare the alternatives then values, like you could say, okay, first I'll say if it's short versus short, and then I'll compare the values of what it holds. Which means if I have a variant, that didn't work. Uh-oh. Give up. So yeah, so you have a variant that has a short with a value of 3, and a variant with an int with a value of 2. Well, shorts are like less than ints, right? So you get 3 is less than 2. That's kind of surprising, right? But if you just compare the values, like, okay, I know these have numbers. 2 is less than 3. That, at first approximation tends to make sense to people. The problem with because one of the problems with just comparing values is that is a compile time problem, right? You need the entire matrix of comparisons, right? You need short versus short, short versus int versus short, and int versus int. And then what happens like with int versus string? What do? They're not normally comparable. You could just not compile it unless you have the entire set. Or you can throw an exception, like if you don't have one of the operations that you need. But it turns out, and this tends to be a more important principle, is that comparing values of different types can break transitivity. So let's say we had basically an operator that did string compares, like so graphically compare things. Right? So you have 200 is less than quote 30 because string-wise, right, the first digit's 2, that's less than 3. And then you want to do, so 30 is less than 5 because again, the first 3 is less than the number 5. But at the very end, right, you get like 200 is greater than 5, so that fails. That is a surprising result. Ultimately, the committee has to pick one. Or none, right? At most one way to do comparisons. At least if you want to use the less than the various operators to do it. So again, if you compare values, so let's say you have a variant of int, int, right? But they're in different slots inside the variant. Are those two things equal? They're not exactly the same. You could say yes if they're values, no if you compare alternates first. So we really we have to pick one. Like I said, comparison of alternates and values is kind of representational comparison. But again, then you get right, 3 is less than 2, and we know that's not true, but shorts are less than ints for some, that we make up an ordering. And basically the ordering is currently in the parameter order. However, that's, compile time, right, that's only order n. Right? A type only has to be comparable to itself. Then came the question of default construction. Should it be default constructible at all? We don't have to allow it. Should it construct one of the types in the type list? And is that state the same as the move from state of a variant? How do we access it? Do we want to be able to index by type? If we allow that, then do we still allow what happens to the variant of int comma int? Index by alternative. And we really want a better way than cascading ifs. We want an order one way to actually get to the element. So we use visitation. So at the time, like a number of us were looking at the different things, existing variants. The main most popular at the time was probably boost variant. Added in 2004, so it's been around a while. It has a never empty guarantee. Assignment is interesting. Sometimes you can default construct it. It compares alternate then values, and we have visitation. And assignment just uses the assignment operator of the if it's homogeneous assignment, just uses the assignment operator underneath. And they kind of went through, when designing this, a bunch of ideas. So let's say they wanted to not lose information. So they started with object A, and they memcopy the bits of object A away. Then just construct B in its place. And if that works, well, memcopy the bits of B, put the bits of A back, destroy A, memcopy the bits of B, and then you have a complete object. Besides being a lot of work, right? So if constructing B throws, you just memcopy the bits of A back, things are good. And Dave Abrams goes, this is fraught with peril. This is essentially not allowed by the language. This is just undefined behavior. You can't memcopy things and then memcopy them back and expect the object to still be around. So then double buffering, and that actually completely solves the problem at the cost of double the embedded storage. It has a strong exception safety guarantee, but many users find the space overhead unacceptable. Right, so here's construct and destroy. Right, construct A, construct B in a different location, destroy A. That works fine. If B can't be constructed, A is still there, no problem. So the current approach, and I won't go into the details for this one, there's a temporary heap backup. It kind of, I'll do a little bit, it kind of looks like this. You construct an A, you copy it over here. And if that copy fails, well, you try to construct the B. If that fails too, it gets fairly complicated. But that is what Boost variant has implemented. Right, these can both throw, which means this final A is actually a different A that's in the heap. It's not your original one. So if you have the address to it, that doesn't quite work. The way they did default constructible is that if the first type is default constructible, then that's what you construct the variant with. And if any type is no-fault default constructible, an exception is thrown. While changing the type, it goes to the first no-throw default constructible type in the type list. And they provided a boost blank so that gives you a type to be able to do this with. Kind of looks like that. The star is boost blank. Is a get function. You can index by type, which is kind of similar to any cast for any. But again, get's just cascading ifs. And then we have visitation, which means you pass it a function visitor, you pass it a function object that knows how to process every type in the type list. So apply visitor free function. Passes the held object to the corresponding function call operator, and this can be ordered one over the number of types. But it's kind of weird. It's kind of inversion of control, right? I want this object to perform work on behalf of whatever type I'm passing. And it's kind of weird, especially if you want to like do things like change the type the variant holds as part of this. Like say you're using your variant as a state machine. Generally, people don't think like this, and they don't like this. But those are really the two options: are get and visitation. Right, visitation, you just write this, and it calls the one of the type it holds. Get is cascading F, so order n versus order 1. So around this time, Matt Gobbled and I did this. We were both working at a trading firm, and we didn't like having to put boost blank in every single one of our types. So we were trying to get rid of the annoyances of boost variant. Right? We never wanted double buffering. We never wanted a heap backup. Like in trading, like the heap is that's just takes forever. And we almost always were adding boost blank to the list of types we had. And visitors always have to right? It's another type, so the visitors had to handle boost blank. And it just annoyed us a lot. And we wanted assignment to always be straightforward, like use the underlying one if it's there. So we decided, let's do an empty state that models the most one. Let's see what happens. And that worked pretty well. Here's the picture, and let me go back one. Right, if constructing B throws, then it's just like, it's an invalid state, really. There's no object there, so there's 0 objects that it's holding. So, and we had thought about proposing it. And our company was nice. They'd say, if you want to do it, that's fine. You can open source this. We have no problem. But I had too many battle scars from trying to get optional put into C++ 14. Optional was in the working draft at one point for C++ 14. And it got pulled because of relation operators. And I didn't want to have to go through that again. It was very frustrating. Because people were constantly revisiting old arguments without new information. And so we have the same debates, and they have the same results just about every time. So now I make you all committee members. What can we do in this case? Give me some ideas. Throw them out. I'll type them in here. We'll see if the committee covered them. It's how I check to see if you're awake, right? What do you want? Okay. Yeah. I can't find my point. There's my mouse, kind of. I've tried different ways of doing this. It doesn't work. Okay, I got. Okay, abort. What else? Anything else? What else could we do here? Oh. Right, so I had boost, right? Double buffering and most one and abort. Okay. Extra empty state. You can try much weirder things, believe me. The committee did. Yeah. Anything else? What was that? Well, okay, rethrow's fine, but what state do you leave variant in? Okay, UB. That I can. Sounds good. So require no throw move constructible. Okay. We'll start with this list, and we'll see if we cover all those. So back in 2014 at the Urbana meeting, my friend Axel, who works at CERN, came with a proposal for variant targeting library fundamentals, which we were doing technical specifications at that time. And it had an empty state. Assignment was always destroy and construct. Right, comparison was by values. He really wanted that. Default constructs to an empty state. And element access is only get, using get. And we had 17 people for this discussion. Only 17 people. And a lot of what we told Axel is there were a couple of us who agreed with some of his design decisions. We said, but your paper needs to design explore the whole design space. And his paper did not do that. And with respect to visitation, Bjarne says, pattern matching is a better solution to this, but this paper shouldn't wait. Variant's too important to wait for a new language feature. And so Axel agreed to turn visitation for variant so that there's order 1 access. But yeah, he needed to explore the design space. And he asked me if I wanted to become a paper author at that point. And I said, no, because of optional. I want to be able to walk out of the room if I don't like the way the discussion's going. And I can't do that if it's my paper. But I'll do as much work as you want behind the scenes. That's fine. So this is probably the major part of what he proposed. Assignment uses the embedded assignment of the type if you don't change the types. Alternates to an empty state, only types that are no except copy constructible. And it leaves out all types that can do allocation, right? You explore double buffering, right? Construct and destroy. Again, that solves the problem completely. But it's double the memory. Right? Comparisons by alternative then values. Axel agreed that transitivity was the more important property. He still hoped for a way to just compare values. So he does an update to the paper, and the mailing comes out. The committee is now concerned about this. They wake up. Remember, there were only 17 of us, and we were just fairly happy. No one else came into the room with questions. There were hundreds of emails. I was gnashing my teeth. I probably needed dental work because of that. And I was heated. A lot of those emails were mine, trying to keep the discussion focused. But very heated, but very technical discussion. Right? And we had comparison suggestions, because short is comparable with int, variant shorted should not be comparable with itself. Assignment, if no except move constructible, right? But here's the really contentious one. We really want never empty, otherwise it's not quite a sum type. And then my friend Sean Parent made a suggestion, instead of an empty state, how about a partially formed state? He did not go to the committee meeting, so I presented his viewpoint, and I got it slightly wrong. At that time, I thought he wanted, it's not queryable, you can only reason about it, and that wasn't quite true. You could add more things. This is just the bare minimum that you need. So he didn't mind if we could query it, but I presented it he didn't want us to be able to query it. And when I found out I misrepresented it, I felt really bad. And partially formed is still a sum type. And then other suggestions that flew by, right? Terminate on exception, right? Except the user doesn't know how to avoid that. So it's kind of rude. Limited types that are no except move constructible. Sound familiar? It's kind of draconian because it eliminates most pre-C++ 11 types. Remember, this is around 2014, 2015. And aggregates of them, right? And it's not portable, so there are some implementations of lists whose move constructors allocate nodes. So those are not no except. So you can't make it portable. And then types that aggregate, right? You have Bravo, Charlie, and Delta. There's no visual cues to know if that type is going to be storable in a variant or not. Disallow, then we came up with, hey, let's not allow throwing move constructors in the language at all. Let's change C++. Before my time, but that had been tried twice before, and it failed both times. Make it a built-in. Forget making it a library, make it a language feature. And it might be nice for other reasons, but it actually doesn't solve the fundamental problem. Have a strong assigned function to, like, you know, for function types which don't throw, and it's like, no one's going to use it. It's kind of like vector at, like very few people actually use that for things. Undefined behavior, right, which is about the same as termination, because again, users can't avoid it. Let's standardize multiple variant types. We'll make everybody happy. Except then we have to do interoperability between them. Like I said, hundreds of email messages. So the top ideas really are double buffering, partially formed state, restrict the types to no throw move constructible, or terminate undefined behavior. Again, the partially formed state, initially you can only destroy or assign to it. You can't query to see if it's in that state. And then the question is, should you be able to default construct in that state? And that turns out to be problematic. Alistair Meredith, a very young Alistair Meredith. I didn't want to change the pictures, like, because I had them from around that time. If you do that, that makes a hidden precondition on moving or copying. So I take a vector, and I reserve something that I know will grow it that would break things. So, discussing Lenexa, we invited all the interested parties. Committee meetings are busy, they didn't come. And I hate evening sessions, I strongly suggested one. Nope. So we had a small subgroup of LEWG, 7 of us, not contentious, and we solved all this. And so what the committee does is they take a bunch of polls to see what direction things should go in. So like, and they're like strongly favored or strongly against. Like, we query the empty state, that's got consensus. Default construct in the empty state, no, consensus is roughly 2 to 1, left side to right side. Had lunch, had more discussions, and then like, hey, should we have variant short int compared to the variant int short? Should we be able to sort types? I was 99%, I'm not a core I'm a library person, I was 99% sure we couldn't sort types. So next day I went to breakfast with some of the core people. I asked them not to laugh at me, so they cringed when I asked if we could sort types. Fast forward to now, we might be getting it. I mean, that's the latest poll from last week. Everything changes in this language. And again, there's lots of polls. I mean, there's lots of polls. We're still going, right? There's still lots of polls. There's still lots of polls. Like, where do you want to get this, right? Do we want a type list in utilities? No, we want like a more general facility, and eventually, like, we're hoping compile time programming gives us that. And just like, so we go to the bigger room. This was a small group. We get to the bigger room, 16 people. It goes pretty well. And it goes to the next mailing. And that seems okay, right? And now there's like kind of copy, then destroy, then move, then destroy. That's kind of a pessimization. And there's probably this argument that we should do it anyway because it gets rid of, it reduces the chance of putting this into the invalid state. There's no evidence. And really, don't make claims about optimization or pessimization without numbers. Yeah, the committee woke up again. As best as I can count them in Gmail, there were 1,080 messages. It's really hard to count in Gmail. And again, 2/3 of my messages were like, this does not contain new information. There's a few more suggestions that showed up. The group that evaluated it was too small. We need more people involved. Because that always solves problems, right? Make it so the folks at C++ now like it, because someone presented it and they didn't like what we had designed. One national body had said, don't even think about putting it into a standard before putting it into a TS. Right? Make it so you can't change the active type. Once you set it, it's like that forever. You can make an optional variant if you want to do that. Make variant move only. Like, some of the problems can possibly go away. Transactional memory was a thing at the time. Let's just use that to be able to roll back. So pre-Kona, like valid is now visible and no longer a precondition for copy or move. They had Axel do another paper, like a really simple thing. His heart wasn't in it, but that's what he did. Michael Park had a different one, and he would move on to pattern matching from this. David Sankel had a very simple one. Nobody wanted it. I mean, this is it, right? Sure, but nobody wanted it, so I don't know, nobody. I have to go look at the numbers. But then he started going for a language-based variant and pattern matching instead of visitation. So we had an evening session, right? They finally listened to me. And I didn't make the Kona meeting, but I called in. And basically the person minuting said, if I hear the same argument, I'm going to stop minuting. And the only thing that changed in that was exceptions on invalid states don't have validity as a precondition. That's the only thing that changed. Goes back to library evolution. There's 19 people. Valid becomes not valueless by exception as part of that. Some bug fixes. And then someone, Matt Calabresi, says, we should not target a TS. Let's go directly into C++ 17. And asked me that, so I said, if you can pull it off, let's do it. I'm an optimist. General feeling is we have consensus. We've talked about this forever. We know how to do it. David Sankel, I don't have the time to read this, but this is a quote from that paper on just why we're doing it. Like we spent so much time on optional, and it didn't change after being in the TS for 3 years. Let's not make the same mistake with variant. Peter Dimov didn't like it, so he started designing his own version of variant. And the final plenary, like someone said, like, we need any in here too. Like any optional and variant kind of go together. It got unanimous consent. Remember, national bodies had just, had previously said, don't you dare try this. They didn't object either. Some fixes. How do we do? I think we covered, I'm not going to go back to the slide, it's too hard, but I think we covered everything the audience came up with, and a lot more. Like one of the criticisms committee members get is like, we don't consider everything. We really try hard to consider everything we can think of. Some more fixes, constexpr, copy and move. More stuff. Barry had a minor issue. Is optional refinement of, say, variant of null pointer op T? Well, not quite, because it's not quite the same thing. There's no support for visitor, but we could add it. So here's a weird question. And because the question's up here, you know the answer, right? If floated int are trivially no except move copy constructible, can you still get an valueless by exception state? Yes, Augustine Berg figured out, yes, you can. Basically, when you try to construct the int, that throws, and that puts it in a valueless by exception state. So you still have to, even code you don't think has to deal with this, still has to care. David Sankel then goes to the language version. So Axel and I go in the room, and we give him all the questions that came up for the library variant, and then tell him things like, oh yeah, and if you have a throwing destructor, the language has to care. The library just says, don't do that. He's been talking this past week about resurrecting this, so we'll see what happens. Peter Dimov, and I won't go into exactly what he did, just did another boost variant 2 that got accepted. Either if all types have a non-throwing move constructor, then take single space, otherwise it does double buffering. That's his trade-off. Pattern matching started more around 2019. We might get it in 26. There's two kind of competing proposals. I think Michael Parks has more consensus. Well, it has consensus while Herb's does not. And it kind of looks like this currently. Like you can switch, so pattern matching is roughly you can switch on types or values. And that's what it would look like for variant. That's like working code. In 20, we added a spaceship operator. constexpr all the things in it. Like see every function inside, a member function inside variant is now constexpr. Some minor stuff with the meta functions. David Sankel wants to use monostate, again, the boost blank kind of thing, and some other. So he wants to move the header. That got approved on Saturday. So people ask me, do I like variant? Yes, I do. I think it's pretty good. If I was doing it, I'd probably want two other ones. I want one with strong performance. I don't want to like construct then move. I mean, it's so rare that an exception gets thrown anyway. We shouldn't be optimizing for that case. And I want one I can have strong reasoning about. The double buffering one, I can very strongly reason about it. I know exactly one of the two states it's going to be in. Thanks to everyone, and especially to Axel, who put that quote in there. I tried to keep it sane. And thank you.
Thank you so much, and we are ready to take some questions, please. Any questions from the room? Yeah, one over there. A person in white shirt. Thank you.
Yeah, thank you. Maybe just a comment and a little question for you to elaborate. So personally, I very like variants and discriminated unions because they allow for sort of a different form of polymorphism that we usually do in C++ through inheritance, right?
Yes.
And in many cases, even faster, because you don't need to use dynamic memory and allocate on the heap. And that looks for me like a reasonable choice when you start to implement in polymorphism. Apparently, as I saw, it requires a lot of effort, a lot of people, and a lot of emails to decide on the details. So maybe you can tell your sort of vision why we see the visitor and
sure.
and this feature only now in C++ and not like 10 or 20 years ago. Thanks.
No, it's a good question. It takes a lot of dedication to get things, especially language features, put into the standard. Right? So Michael Park started with variant, and then like he started like, okay, how can we make all this work? You know, he first tried to switch as a keyword, and that doesn't quite work. And it just takes a lot of time, and you have to get consensus of, first of all, popular consensus of all the members who are coming to the meeting, and then eventually country consensus, or they will say no to the standard. And every version of the standard has not had any dissent, and we'd like to keep that record if we can. It just takes a long time. You have to convince a lot of people why this is the right trade-off, and they have to be willing to live with it too, or they're going to just say no. It just takes time. I mean, I wish it was faster, but we may get it. We may get it in 26. Like there's a decent chance we'll get pattern matching. Thanks. Oh, and those polls I gave on pattern matching, if it doesn't make 26, those are not biased against getting it in 29. It's just those were the polls were specifically designed. Do we want this in this design for 26?
Thank you. Any more questions, anyone? One more, anyone? Looks like we are going to have a coffee break. Nevin Liber, everyone. Nevin Liber, thank you. Coffee break now, and we will continue in just under half an hour. Don't go away. Do come back. Thank you. Lovely. Thank you so much for coming back. We are maintaining the highest levels of expertise at our conference today. And with this, I'd like to introduce to you our next keynote speaker, Hana Dusíková. Now, Hana is a staff software engineer at Woven by Toyota. She is known for the compiled time regular expressions library. She also chairs SG7 study group for reflection and co-chairs the evolution working group. Wherever she goes, she represents her native Czechia. Now, fun fact about Hana is that she lives with an Italian greyhound, and as you can see, she's got a very cute roommate. And my idea now is that we show our special appreciation to Hana being here and our special appreciation to our neighbor, which is Czechia. So does anybody know the Czech word for ice cream? The pronunciation dictionary says zmrzlina. Is that anywhere near? Okay, so everyone, zmrzlina. How's that? Okay, all right. We've got another one. We've got another one. So back to the roots in Czech, according to an automatic translator, is zpět ke kořenům.
Zpět ke kořenům.
Okay, everyone.
Zpět ke kořenům.
And one more.
Zpět ke kořenům.
Okay, we are back to the roots with Hana Dusíková.
Hi. Okay, this is a really scary room, by the way. You should stand here. Okay. I have a talk. It's called My Favorite Data Structures, but it's kind of like not what you expect. I work for Woven, and I'm Hana, and let's start it. Recently, in my work, I'm hacking Clang compiler. I'm as part of fix things which always bothered me, and I have the opportunity to fix them now. Also, I like to learn how compiler works, and also can implement changes into language which I propose, which makes it much easier to propose them. So, how many of you have some experience writing interpreter or compiler? Please raise your hand. Okay, it's like 1/3, some maybe 1/2. Okay, so in Clang there is a thing called constant evaluator. Constant evaluator evaluates C++ for constant, obviously. It's module called expr constant. It interprets C++ as specify, and it's all in one file. Whole C++ for constexpr is implemented in one big file, 17,000 lines of code. And my clickers, it is independent of your CPU architecture, so it works on on symbolic execution, and it doesn't care about your CPU anything. And also implements the C++ abstract machine itself. Abstract machine is the important word because it's an abstract. There is no connection to real hardware or anything. So you need to forget about CPU architecture. You need to forget about values, memory, pointers. Are you ready? Yeah, okay. So, symbolic execution. Everything is a symbol. There is no such thing as byte, no such thing as address. So, what's a value? Value in Clang, because the Clang, as it models the symbolic execution, we can explain Clang and you will see how it works. So AP value is a thing which holds a value. AP, I asked Clang developer and they were not sure what it means because it's quite old. But after some digging, it's arbitrary precision value. It can be nothing. It can be integer with some value in it. It can be float of any precision of any type. Even the integer can be any, like 1,000 bits long, doesn't care. It can be array of other values. It can be union of values. It can be structure of values. And it can be L value, reference or pointer. So array in Clang is implemented as three things: pointer to data, size, and capacity. So you have array of items, in this case 12, and you can have it initialized with some values, in this case only zeros. But it doesn't care. It can be even like mixed values, because the interpreter is a little bit wider than the language itself, but in C++ mode, it won't allow you to put there anything else than same type. Union is just, you have some code, meaningless code, and union is two things, field and value. Field is a pointer to AST, representing the field in union which is active, if it's active, and value is another AP value containing the value, in this case integer, another integer, or it can be float, or it can be object. There is no such thing as a size of object. There are no bytes, nothing. They are just values. Structure is, in this case, we have three structures, and circle is inheriting from position. Position contains two floats, and there is also color with RGB. So such structure, sorry, it's not working. I will. So value is three things again: data pointer, and also number of bases and number of members. So in this case, we have like bases, members, 1, 3, and then we have data. In this case, are 4 values in our structure circle. 1 for base, which is structure, and first member, float radius, and color, which is another structure and another structure. And that's how you implement structure in Clang interpreter. From structure, there is like pointer to another structure, and it's like 3. So if you have like sub object, it's just sub 3 in your like main object. That's all. So what is a pointer? If you are implementing your own interpreter, how do you implement a pointer? If there is no address in memory, you have value, and you need to somehow to point at it. But how? No address. You can use AST location as identifier of the object. Sorry. So, what can be pointed by pointer first? It can be nothing. It can be null, or null pointer in modern C++. It can be initialized object of type A, or it can be initialized object of type B, or it can be array of objects. And you can move in the array of objects to not object. And you can even point past the array or even past objects, initialized or uninitialized. Doesn't matter. So if everything is just a symbol, how do you order? In hardware, some people think you can order pointers if you have linear memory. But if everything is a symbol, how do you order these two items in memory? A, B, or descending order? I don't know. Or what if there is C in middle? How do you sort them? There is no meaning in sorting addresses. That's why C++ doesn't allow you to sort to compare pointers if they are not into same main object. It can be even more into dimension and some undefined value. It doesn't make any sense to sort them. So, first, I use like term main object. Main object, and for that we need to also learn pointer provenance. So we have structure x, y, z with 3 members. As I showed you how structure looks like, we have 0th, first, and second member, because we are 0 indexing. And we have items which contains array of data and count. It's just example. So we have like 8 members and count. Is this okay with you? Like, that's how you manage things in memory? But you can do this. So you can take pointer to data 8 member, which is past the end, and pointer to count, and they will be same address or same thing. And that's wrong, because these pointers are not the same logically. Symbolically, they are totally different, unrelated. So like thinking about pointer permanence, you cannot do this like linear memory thing anymore. And you shouldn't do it at all, because in runtime, it will just lead to error if you do this. You will hurt yourself. So no, this is wrong. You need to think that array is just subobject. So we have structure of 2 items, data and count, and array is another subobject. And then we can also have like some upper object which contains just items, nothing else, and that's here. And now I can have pointer to the object, which can be somewhere on like stack, heap, whatever, doesn't matter. And I take pointer to it, and I have pointer to object. It's somewhere in program as an AST node, so I can just point at it. But how do I point at subobjects? Because there is no address. There is only pointer provenance. Imagine it as a path from top to bottom, which navigates you how to find your object. So you can do pointer to first member of the main object, which is the items, and from there you can go only down. You can go always only down. So you can go to count, or you can go to data. Data is an array. From there you can get pointer to member of the array, and from there you can go to subobject in the array. It's simple. The simple rule is you can go always down. No other direction, with one exception. For array, or arrays, you can just, this is like path plot here. You can just, yeah. Also, if you have like pointer at x, you cannot go to next pointer. You need to go from pointer on the top. So yes, you can do this. But if you have pointer at the array itself, you can just move to next object. That's only guarantee which pointer provenance gives you to go to your neighborhood. And you can do, it's happening. Okay, I think I need to use the next clicker. So yeah, then you can like nicely go to next object. Okay, so if we have model that your object is a pointer, it's some like AST thing, AST node. What's the difference between L value and R value? Is there any difference between L value and R value when you program C++? When you like code something? R value, someone said no address, but R value is always also address. Difference is R value just says, we have L value, left, right, obviously, but R value just is same type of reference or pointer which just makes, this is marked as temporary. You can steal from it. It will be soon destroyed. Maybe. You are allowed to. There is no other difference than this. So we need to talk about lifetime. We have global variables in your program. They start before you go to main, and they will end after you leave the main. There are scope-based variables in your scope. They behave as LIFO. So last in, first out. So last variable is initialized is destroyed first. Temporaries are part of your expression. Every time you create some temporary, it can have address itself, or it can be in a register. And compiler knows that, and if you try to get address, it will move it to memory. Otherwise, it can be in a register if you want. But that's hardware. Sorry, we shouldn't speak about hardware here. So temporaries are just variables with different lifetime, only for expression. And then we have heap allocations. Heap allocations are like the thing you control, and they are starting exist inside of the expressions, but they actually do not end at the expression, so they are like more like this. It's a leak, let's say, but it's up to you to control it. Also, temporaries can be lifetime extended, and you can assign them that they are now scope-based or even global. This is like lifetime model in my mind, how I see it. So, identifier of object is its location. Global variables are identified by name because you have like const variable A or const variable my global game state. I don't do that. Local variables are identified by AST node and a version. I will get back to it. Allocated values are identified by unique key. Every time you allocate during constant evaluation or in symbolic execution, you will just get some unique cookie or key identifying this is your allocation. So again, what's a pointer? Let's have like, here. Structure coordinates, x, y, and we have function, setting the variable x, y, and we have pair of values, and we take pointer of it. So AP value is three things for the pointer. Var declaration, which is just pointer to the variable itself you are pointing at, and version. Every time you call a function, you increase version. So that's how symbolic execution engine knows if you have somehow pointer to some local variable from previous execution. So it will tell you error. So it can detect UB. Because constexpr engine and abstract machine doesn't allow any UB. Everything must be detected. Not every compiler does that, but Clang is trying really well. And third thing, provenance. Provenance, yeah, we have a few versions every time I run it. And if we look into subobject.x, we need to change provenance. And it's just path to first member inside of the object, x, or y. That's how symbolic engine sees pointers. Okay, that's pointer to local variable, but also we have allocations. In this case, it's a pointer to some allocation somewhere. It's a structure. And it's a pointer to expression, so we know where this specific allocation start to being alive, and also key, which is just number. And every time you allocate, it's just different number. And if you want to go to inside, into array, you need to use provenance again. So path 0 takes you into the first subobject of the object you allocated, the array itself. And if you want to go inside, you need to extend the path to two members, 0, 0, and so on and so on. Okay. Pointer to static variable. Static global variable. There is always only one behind its name, if it's not templated, but that's just instantiation. So it's just pointer to the AST node itself and to declaration. And inside of the AST node, Clang stores the value itself. And if you have some subobject, you can use provenance too, but not in this case. So values you create, you store somewhere. Global variables inside AST nodes. Local variables in stack data structure. Allocations are in a map. Yeah. And all these are data structures you use to model execution. And then constant evaluator just walks the AST. AST is just tree-like data structure, and it goes recursively from the top to bottom, and if there is a plus expression in expression, it looks on left and right and evaluates them and gives you a result. It's really simple. I mean, the code is complicated, but it's not that hard. And everything I show you is implemented in C++, which is sometimes confusing because to implementing C++, you are using C++, and if you want to implement new feature, let's say exceptions, the best thing to model them are exceptions in the language. It's confusing. But it helped me understand how to use C++ and how the abstract machine works. You shouldn't, like, unless you do something really low level, think about what's happening in your memory on bytes, because compiler doesn't see that. Compilers see abstract C++, and it optimizes based on that. So if you're accessing past the array, it's something which cannot happen, and it means it's UB, and it can do weird things. But compiler interpret can detect these, because it has much more information, metadata about it. So, in my mind, constexpr interpreter is just another machine C++ is running on. Because C++ doesn't define anything like stack or memory. It just, everything is symbolic. Yeah, what's happening? So, in my mind, the standard library should be constant available. Do you agree that, okay, I will ask you a question. Where would you put line? What should be constexpr and what shouldn't? Just shout. Do you is it, sorry? I/O.
When a function reaches the outside world, reads from somewhere.
Yeah.
Then it cannot be constant.
Okay, from our audience, if your program reaches outside world, which is not known during compilation, then it should be constexpr, which is exactly my personal model. If you cannot observe universe, and if you cannot break your repeatable build, so by design, the feature will give you always same result, then it should be constexpr. Yeah. Good one. So, but most standard library is not. And I found it really sad. So let's do a quick test. What containers in standard are constexpr compatible? Array. Just raise your hand. Is array constexpr compatible? I'm getting 2/3. Yes, it is. So deque. Did you use deque? Only I see 3 hands, 4, 5, a little bit more, but I cannot see it back, sorry. deque is not constexpr compatible. You cannot use deque in constexpr. Flat map, which is new data structure in 26, I think. Yeah, Andreas is nodding. Flat map, new data structure in modern C++. Is it constexpr compatible? Raise your hand if you think so. Sorry, it's not. Flat set. Also, no. Forward list, which is one-way linked list. The simplest data structure, probably everyone learn as a first thing at computer science courses. Is it constexpr? Only few hands. It's not. In place vector, new data structure in 26. Is it constexpr? No. You know more details, but yeah. Yes, but with asterisk. It cannot be used for constexpr type which are not trivially constructible. We are trying to fix that, but we don't know. We have some theory how to do it, but still we are working on that. Oh, sorry. Yeah. Hive. Hive is data structure which guarantees you pointer stability. Every time you create object there, it will never move. It's really useful for game development, networking, simulation. It's not. It's going to 26, and it's not. List. No, we didn't have forward list, so it would be weird. Map. No. Yeah, Exactly. Optional. Is it now it's data structure because it has begin end, so it's container. Some people disagree, but you can use it as a container for one member or 0. It is. Set. No. It makes me sad. Basic string. It's also data structure. Yes. You know C++. I have nothing to teach you. Under that map. Nope. Under that set. No. Val array. No. I care. Yeah, I care, exactly. Val array is like, the meme, Mom, can we have symt? No, we have symt at home. So, vector. Yes. And do you know why is this like, this table looks like this? Yeah, by the way, there is a paper from me which will fix this for all the containers with exception of Hive, because when I was doing the paper, Hive wasn't in draft yet. But I should update it probably. So, let's look on some containers in details. Just array. You create array. You create something like val array for array, and inside you construct elements and elements, and you initialize them from the left to the right. And if you don't provide enough members, it will initialize them, but in unspecified state, but they will be initialized. If it's trivial type. If it's not trivial type, it's a little bit problematic. You can take pointer to begin, you can take pointer iterator to end, you can take iterator in middle, you can move iterators, you can go to end, fix security bug, you can change the values. Because you can write in, and if you change it, iterators are stable. And you can change also to this now. Array, simple. And it's destroyed from the back to the front. Okay, vector. It's 3 items. In my mind, Andre, it's pointers, not pointer and sizes, but it's depend on implementation. But so I have pointer to data, pointer to size, and pointer to capacity. So I allocate 4 members, and I will put some values there, A, B, C, D. Okay, and if I grow, I need to allocate new storage, and I need to move out previous values. But if I do this, and my type will throw exception, suddenly my my vector is broken because part is in one storage and one in another. So I cannot do that. If I can throw exceptions, then it needs to be copied. Like this. And then pointers are changed because we know it's safe now. And then we can safely destroy the objects in the storage. But not from the back to front, but from the start to the end. Vector is weird in this sense. Okay, and then I can continue. And maybe I get iterators. And what will happen if I put something into vector? It's fine. But now, I need to allocate, and my iterators are no longer pointing at something which is my vector. So your iterators are stable only when you're not modifying the vector size or capacity. So let's say, because in this sense, maybe I still have iterators, and maybe they still point at some like moved out value, but I don't know. So I need to destroy them, and suddenly they're gone. So, and then I move stuff there. I can also like take iterator, and I can delete item, and delete is just moving stuff to the end, like this, and then I just change size at the end. Or I can take range of iterators and delete 4 members in this case, and I will do only like this thing. And I will move the 4 spaces at the end, and then destroy them from the left to right, and then move size. That's a vector. And it's destroyed again from the left to right. And it's defined like this. So list, I can put thing at the end, at the back. I have two pointers to previous, to next node. Everyone knows list. I can take iterator, and even if I'm modifying the list, the iterator is stable. But use list only for really big items, because otherwise it's not efficient. I can also remove from the back or remove from the front. It's all one operation. I can even remove something from middle if I have iterator on it. And it just change the pointers and move iterator to next element. Just in simple list. In place vector, it's size and members. I'm doing the flat thing, which I shouldn't do, but I didn't have any way how to visualize it properly. So sorry. And content is just based on the size, and I can put items there. Capacity is fixed, and I cannot grow past the capacity. But there is a problem. Why in place vector is not constexpr is because all the items needs to be initialized, and if your items are not trivially default initializable, then they cannot be initialized in constexpr, and it will fail because it's an array and it must be initialized. We need to fix that. DQ. DQ is magical data structure no one uses. You have 5 members: prefix capacity, suffix capacity, and middle vector in middle of it, which points at leaves of the DQ. And leaves are always the same size. And there is some space in front, in prefix, or in the suffix. And the leaves are always the same size. That's important. So why it gives you kind of contiguous storage for leaves, and it gives you O1 adding in front and in back. So why almost no one is using explicitly DQ? I think you know your answer in your heart. ABI. Because some implementers, and I'm not going to point my fingers, MSCC, they do really small leaves. I think it's 16 bytes or 2 items. So it's basically a list with vector. So it's useless. But on libc++ and I think standard in GCC, they are 4 kilobytes. So they are page size. So it's really useful. But you need to know your platform. So these all seems really easy to implement. Why is only vector and string, and also array and optional constexpr? But mostly vector and string. Do any of you know answer? Not Guy, because he already saw this talk. And he's also sleeping in front, by the way. So, is there any answer for that? I heard because they are most used. Vector is allocating, string is also allocating. So because okay, there are so many answers. Answer is this. Because in Cologne meeting 2018, there was a last slot in library working group for review, and I bribed Marshall with chocolate to put this into standard. Because there was a lot of paper which was fighting for the last slot, and this was actually small. So we have this for 1 chocolate. It cost me €2. But I didn't write the paper. That's Louis Dion. So I just was doing the politics behind with chocolate. Okay, but C++ language and library is improving with every version. It gets better. So let's look at constexpr status. Since when you can use if, for, and while in constexpr? Which version? Just shout. Not front. You are banned. 14, yes. Variables. Since when you can use variables in constexpr? Because originally it was just constant expression, no variables. But arguments were actually variables, so Also 14. Calling lambdas. Anonymous object, like anonymous lambdas. Since when? Trivial default initialization. So you can actually put variable in your function without initializing it, and it will be somehow trivial initialized. 20. Try catch. Can you have try catch in constexpr? Raise your hand if you think so. Only a few people think, oh, you can since 20, but you cannot catch at anything because there is no throwing of exceptions. Okay, you can change active member of union since when? Not just initialize it, but also change the member of union. 14? 17? 20? You know that. Not committee member, please. 20. Inline assembly. Can you have inline assembly in constexpr? Yes, you can since 20, but it must not be evaluated. For 20, we change meaning of constexpr from must be constant evaluatable to there is maybe some part which is constexpr compatible, or maybe none. Atomic operations. Can you use atomic operations in constexpr? Yes? No? You are all wrong. 26 allows that since 2 days ago. Exception throwing. Can you throw exception in constexpr? Yes, you can since 2 days ago. Can you have initialized array members? Not yet, but maybe on next meeting. Virtual basis. Can you have virtual basis of your types in C++ in constexpr? I see like people doing like this or this. I don't know. It's just noise. No, you cannot. Can you have virtual functions in C++ in objects in constexpr? Yes. Okay. Can you use byte array as object storage? Like I have bytes and I will store object there? No, you cannot. But maybe someday we will do something about it. Can you use reinterpret cast? The cast of the OD cast, which will do everything you ask it, but you don't know what you are asking it for? No, and I hope never. So constexpr still needs some improvements, obviously. But this talk is about data structures, and I have my favorite data structure, which was actually my motivation for this talk when I started, and also for my papers in the committee to actually allow to implement it. And it's a cool one. And we have just a little bit of time, but it's enough. It's called, It has O1 insert search delete. It gives you linear growth. I know I have typo there. I didn't fix this. No rehashing. So you don't need to rehash. It grows like 3, so it's like a linear growth, so you don't need to. It can be log-free. It can be persistent. Do you want to know what is it? And also you can use it in flat storage. Sorry, I didn't know. It's 6. OK. It's called AHMT, hash array mapped tree. Try is proper pronunciation. It's all the cool words like cloud and blockchain and everything, but this one is actually cool. It was invented in 2000 and a log-free version 2011. It's new. And I think it's so simple that everyone in this room could invent it. So you have root, which is just one pointer, and you have leaf with item you are searching for, and it has some hash. It's big hash, but it's just 16-bit. Yeah, it's big one. You have level 1 of the structure, which is 16 pointers, and you use first 4 bits of the hash, 4 in this case, to navigate to level 2. And then you use E, next 4 bits, to navigate to next level. And then you use 8 and F, and that's how you find your element. Yeah, I'm fine. Thank you. And you can have obviously multiple. It's like it's a tree, so it looks like this. But also, you can have even leaves from in upper levels if there is no conflict for them. So if you know that there is no other item with same hash or some same prefix of hash, then you can put it in a higher level or even to first level, simply. But if you have multiple items with same hash, so you need to go to a hash function, what's happening? Yeah, sorry. To distinguish what's a leaf and what's level or node, you need pointer tagging. So you put information into pointer because pointer at hardware or even symbolic pointer can have some more information. So I'm using 1 bit of information to tell you or the program what's the leaf. So you can. There is 1 bit here and up there, which points what's the leaf. And obviously, you can have also more items with same hash. So you need to use better hash function. But if not, then it's a kind of hash table. But it grows linearly, but it's wasteful. There is a lot of null pointers. And I don't like them. So let's compress the nodes. Just use bitmap to give you information what each node is actually used, and everything else is virtually semantically just null. And you can do this. And suddenly it's much smaller and nicer data structure. Or you can use pointers which are atomic, and put them in front of each level, including level 1, which is on the top, and each leaf. And then just change them, and you can compare exchange them lock-free if you go from the bottom to the top, and you don't need to lock in between multiple threads. Or let's forget about the atomic pointers. You can use ref counting for each node and leaves, obviously. And you can have multiple copies of your data structure sharing nodes. So you don't need to lock also. You just will create new copy. And the copy, it just contains only the changes. And if you destroy the old one, it will still hold because it's ref counted. I have wrote, and so I have like 2 copies. Also, if you exchange pointers with offsets, you can just use them in flat storage. Like this. And then, at the end of the file, probably because flat storage is usually just file, the last node, last offset, like last value with offset, is root of your data structure. So whole data structure is just current state of your data structure. But also, you can have subview, some prefix, and you can have snapshot of previous version. So you can use this data structure in flat storage as a transaction log, maybe, or database. And it will hold all the values because you are just appending. You are not changing anything. And that's my favorite data structure. But for future, because we like C++, at least I do, and maybe Guy, there are some papers which improve C++. Exception throwing was accepted 2 days ago. Constexpr exception types, so like runtime error, logic error will be constexpr. Atomics were accepted too. Constexpr shared pointer from Paul Keir, which will make shared pointer usable in constexpr. Pointer tagging, which will allow you to store some small information, few bits into pointer, even in constexpr. Trivial unions, which maybe will allow you to have array which is not fully initialized. Constexpr containers and adapters. Every container adapter should be constexpr. Also, freestanding constexpr containers and constexpr exception types. It's a paper which will, for people working in embed or hardware development or firmwares, allow to use standard library, including containers and exceptions, but only in compile time. In runtime, they won't be there, so no allocations you don't know about, but for compile time, you can build things with constexpr. Constexpr coroutines. Constexpr stud format. constexpr stud generator. And also there is a paper from Jeff Snyder, which will allow you to allocate something in constexpr and like vector and store it in a way that it will be in runtime with almost zero overhead. Like overhead will be just like pointer randomization and nothing else. The object will be just there. And you can just read it from it and do counts or even mutable operations in some cases. Yeah, thank you. That's my favorite conceptual data structures.
Thank you so much, Hana, for this engaging talk. I think we've got time for one or two quick questions, please. Is anybody interested? Questions? I could see you all amazed.
I'm afraid that there is someone. Yes. Because it's hard to not have any question. Did you get it? Or am I on one conference? Maybe medical conference? I don't know.
Okay. It works? Okay. Hello. You said that this abstract machine of C++ is one file, but this is the rest of Clang uses the same abstract tree as this constexpr evaluator, or this is abstract tree and all of that written only for the const expression evaluation?
Okay, if I heard correctly, I have bad hearing, sorry. This is the first part of the talk, as I showed, is how Clang is evaluating C++. And because Clang is designed to be compiler, there are essentially two different parts. You do all the parsing, and then if you want to evaluate something, you need to use interpreter, because you just interpret C++. And if you compile it, you need to lower it into LLVM-IR and into assembly. And then you do. I imagine a world where you can just take libclang, link it with Chrome, and have like HTML tag, script, language, C++. Because it's just interpreted language, nothing else.
Yes, but this AST is shared between the rest of Clang and this.
Yeah, the parser is obviously shared. Like Clang is much bigger than just expr concept.
That's why I'm asking, because you said that that whole evaluation is in this file. So I was wondering what is reused from the rest of the Clang, yes, because.
I mean, there is a lot of things reusable in the rest of the Clang. There is some interface which allows you to use this machinery from outside of this file. So if there is something which can be used somewhere else, it's obviously available, not just there.
Okay, thanks.
Okay. Thank you so much. Perhaps one more. Just over there, suddenly an explosion of questions.
Hi, so I have questions about this Humpty structure. Is it like similar in spirit to this, I forgot the name, but is it similar to this thing that is used to map virtual addresses to physical addresses?
Oh, no. Like translation between virtual address and physical address is done by a processor.
But it's like, I feel like it's very similar in like spirit.
No, this is much more abstract. You have much more information about what's where, and you can go always only down. You cannot go up, and it's just abstract data structure. It's not something which is happening in the processor. Processor needs to be much more optimized and quicker. So there can be also like problems, and that lets us to like things like meltdown and spectre, because you don't have much information to do this. But constexpr C++ is safe C++.
Okay, thanks.
Yeah.
Thank you so much. I think perhaps the rest of the questions you might want to take off stage.
Okay.
Hana, we need to rearrange the stage now for our next speaker. So everybody, let's show our applause to Hana Dusíková. Thank you so much. A short break now, and we will continue very shortly with our final speech of the day. Thank you. Thank you so much once again. We are awfully punctual this year, so let us continue as advertised. It is 5:30 and it's time for our last talk of the day and another keynote speaker now, Jason Turner. Now, Jason has 2 decades of C++ experience and is a developer, trainer, and regular conference speaker. Jason created his C++ weekly YouTube series in 2016 and has released an episode every week since then. So let's have a look. Here's a high-quality screenshot of his YouTube production. Disclaimer, pixelosis has been intentional. So I give to you Jason Turner.
Thank you. Thank you. So is constexpr really zero runtime cost? And what's funny is, as I was putting these slides together, I couldn't remember what title I was going to give the talk. So then I ended up with this, the runtime cost of using constexpr. Anyhow, so yes, my name is Jason Turner. I am host of C++ Weekly. I have been publishing since March 2016, like you said. 456 straight weeks, which anyhow. Oh, of course, you can scan the QR code if you're not currently a subscriber. Like and subscribe. You know the deal. I am author, C++ best practices, C++ 23 best practices, and some puzzle books that I also mentioned in the intro thing here. And you can check out those links if you're so inclined. Developer, I've got, GitHub and all this stuff as well. Microsoft MVP since 2015. I do training, just so you know, kind of have to let you know who I am. I love doing training, and I am happy to come on site to your company. I have been to at least those countries, and I think I'm forgetting something. Yes, Canada. I forgot to put Canada on there. Or otherwise, excuse me, you can come to conference workshops. Now, this isn't just a sell for me, just for the record. All of these great conferences offer workshops, and if you have any interest in getting any kind of formalized C++ training, I do suggest that you come to one of these conferences and come to a workshop. Right, Phil? Okay, very good. So about my talks in general, avoid sitting in the back. Room's a little tight, so you can free to shuffle forward. I saw you waving in the back row. Yeah, you can. There's a seat right here if you'd like to come. He's actually moving down. Do interrupt me and ask questions. Yell things out. I will repeat it for the room. This is not a hold your questions until later kind of talk. In fact, it'll go far too fast if you do, so please don't. And this is approximately what my training days look like if you're ever interested in attending one of my classes. Although this is a very large room, I limit my classes to smaller than this. Oh. My laptop just told me I was connected to some random Wi-Fi. That's great. Just out of curiosity, is anyone who's been to one of my classes before? A few people. Who watches C++ Weekly? A few more. Who wants a free book? Okay, I have exactly one. If someone asks like a really good question or something, then I will throw it into the audience and see if I can impel it into you. Oh, sorry. This is my C++ best practices book. I brought it because it's the book that I had to bring. I didn't actually make an intelligent decision there. Okay, so then another possible title is constexpr really free? Maybe another question is, I don't really know what the title of this talk should have been. Perhaps, since I'm going last, I can take as long as I would like. It says I have 41 minutes left, but who's going to stop me? Okay, we're going to play a little game. Like a lot of you raised your hands saying that you watch C++ Weekly. As such, you're probably used to this little tool called Compiler Explorer, godbolt.org. People have heard of this. You've probably compiled an empty main or seen one compiled. Let's talk x86-64 what approximately do I expect this to compile to? All right, we'll get there in a second. XOR EAX, comma EAX, and then depends on optimization levels, one of the comments. There's another statement that needs to be put here. Ret. So something like this, right, with an optimized build. There's too many photographers in the front right now. It's making me uncomfortable. OK, so what if I do O0? What's that? Prologue, epilogue, return 0. No, we're going to get less than. We still do have to zero out EAX. Set up a stack frame, yeah, and move EAX 0, yeah. Oh, you're right, prologue and epilogue. I'm sorry. Who said that? Yeah, I apologize. Come get the book later. I corrected you, and you know, I'm sorry. Yeah, so something like this. Okay. What does this compile to? Let's do the optimized build game, I guess, maybe. Move EAX, comma 42, return, like that. All right. Now what if I do O0? Put it on the stack, maybe not, and then return. That's what I just heard. Depends on the compiler. OK, so we definitely do have to put it on the stack. Oh, look, I can paste. This is a really big stage. Where's the video cameras? Oh, are you having fun? All right. Yes. OK. So put it on the stack, maybe not was the comment. I kind of, you know what? How do I want to work this? What do you think that how am I going to load? How am I going to load 42 into EAX in O0? That's the question I'm trying to ask, perhaps. Mav EAX, comma 42, is that what you're expecting to see? Push 42. Oh, no, now we're going to get a push of 4. No, we're not going to get a. You think an O0 will load it from stack? That is the question I was going for. OK, it's not going to. So we do dutifully set up that stack variable, and then we have hard-coded 42 into EAX, return value, on line 6 of the disassembly. All right. Now, if I do Clang, this was GCC. If I do Clang in O0, do you expect something different? Are you nervous to answer? Are you awake? Does anyone need to be elbowed because they're snoring? OK, so Clang does this. It sets up like some sort of 0 first, and I'm not entirely sure why it does that. But it moves 42 into that space on the stack and then moves 42 into EAX. So they both are basically storing 42 on the stack because that's what I asked it to do on line 2 of my program. And they're both hard-coding 42 into the return value. I'm going to remove const. Do I expect anything different? This time it surely should load from stack. You're right. It is going to. Neither one of them is going to hard code the return value. I cheated, in a way. How did I cheat? Do you know the answer? I did. Why with the const did it hard code it even in O0? Because it is const is the indirect answer? Yeah, so there's like a rule basically that says constant integrals initialized with constant expressions are implicitly themselves constant expressions. I don't need the keyword constexpr there. It is a constant expression. I actually did an episode about this relatively recently. Okay, so what does this compile to in O0? Sorry, the timer is over that corner of the screen, so I'm like, yeah. In O0, what does this compile to? And maybe if we just want to focus just on line 7, or perhaps. Okay, so move 20 to AX and ret. Yes, that is what it is doing. Because I'm still cheating, right? I'm still initializing a const integral with a constant expression. It's therefore implicitly a constant expression. This becomes a compile time value. Now what does this look like? I just remove const from the ret val. I'm in O0. I'm going to run this program. What does this look like? Function call to right, so function call, the result of get value is going to put it on the stack, and then the stack variable is going to get moved to ret. This is with Clang, with O0, so function call, the result is stored on the stack. And it's, you know, if you just look at this, it's pretty easy to see how the compiler can do some of these optimizations, right? Because lines 9 and 10 look a little redundant, if you ask me, just a tiny bit. Okay, that's about right. Now, does GCC do anything different in O0? Shorter? Is that what you said? Where's talking? Oh, you're in the spotlight. Okay, shorter in what way? Less redundant of instructions in O0. That's often true with GCC, but there's another thing I'm getting at here that should probably surprise, I'm going to say, almost everyone. Yes? Why are we discussing O0? Because I'm going to make a point in just a second. First point, this is GCC with O0. Yeah, with O0, it often decides to go with runtime, but flipped around perhaps another way, GCC is incredibly greedy about evaluating constant expressions when it can. I did not put this into a constant expression. I didn't even make it const. And GCC said, I think I'm going to do that at compile time, even at O0, even in a debug build. How am I supposed to debug this? I don't know. It may as well be const eval. All right. All right, constexpr. All right, I've made the thing constexpr. I think at this point, we know what it's going to do, right? It's going to evaluate this thing at compile time. It doesn't technically have to because it's not observable behavior, but it's going to, like this. All right, so what is the point I'm trying to make? That's what you were asking? The point I'm trying to make is this particular line of disassembly right here. Someone already said this, but what does this represent approximately? Storing the variable. Stack allocation. Constexpr values are still stack variables that take up stack space, at least conceptually. This is why I'm looking at O0, right? Because in O3 or O2 or O1, we know it's going to eliminate the stack usage entirely. But at O0, we can see that this is at least theoretically taking up some stack space. So, first point. Constexpr values are still stack, automatic lifetime variables that still take up stack space, at least conceptually. So with optimizations turned on, I know one of you can just write the assembly for this program, right? It's main, move EAX, comma 20, ret, right? Good. Now you're all assembly language programmers. Go back and tell your coworkers this is what you learned at Code Dive. Actually, how many of you are with your coworkers right now? Oh, not as much as I expected, but very good. OK. But we'd probably get the exact same result even without constexpr here, right? If I turned on O3, except I'm going to have maybe the function itself omitted, right? Well, the function is constexpr. That's implicitly in line, so I'm not going to. I would get the exact same result with an optimized build, even if I removed constexpr from line 6. OK. I am not looking for you to write every line of the assembly on this one. We've officially moved past that. But the question is, what does this compile to, at least conceptually? Now, I need, so I've got this function called print on line 12. Let's start there. It expects a span of const ints. You have to be really careful when you say const ints, because it just sounds like constants. And on main, I have a constexpr auto data equals get data. Get data is just filling this array, 1024 integers starting at the value 10. And so I'm going to get what? 10 through 2033. Did I do that right? Anyhow, OK. What's the assembly going to look like on line 16? What am I actually having to do on line 16? Initialize? Can be statically stored, or it can go on the stack, is what you said. But from a C++ perspective, have I created a static variable on line 16? I have not. Excuse me? An O0. I didn't specify that. OK. So I am creating a stack variable. I am asking the compiler to copy data onto the stack right here. Clang not necessarily will. But I will tell you, this is GCC with O3. You can see that line 7. What am I doing? I am copying 1024 integers onto the local stack. And then I am passing pointers to those integers via the span wrapper to print on line 10. Does it make sense? Questions? All right. Now I have made it static. Now I'm explicitly telling the compiler, don't make me a local copy of this data. I want you to initialize this thing somewhere in the binary and then just pass pointers to it. And the generated code looks like this. And this is going to be effectively true on every compiler, because now I've explicitly told it to put the data in static storage. So at this point, it just says, give me a pointer to some static data blob that was allocated somewhere in the read-only data section of the binary, right? OK. So number 1. Potential runtime cost of constexpr, potentially expensive copies. This is something I have definitely talked about before in C++ Weekly. And I actually covered this in applied constexpr. I think the talk was called Applied Constexpr at Meeting C++ in 2017. I think it was. Anyhow, Stop using constexpr and use this instead. The point of that episode is stop using constexpr and use static constexpr. You probably mean static constexpr almost every time. And then in 3.15, I actually do a direct comparison of constexpr versus static constexpr. And then in 3.39, there's a conversation about static constexpr versus inline constexpr. You probably don't want static constexpr at namespace scope. You probably want inline constexpr because you want the linker to merge those blobs instead of loading your binary. Okay. That's not even why we're here. Why am I talking about O0? Yeah, sorry. All right. What does this compile to? This is why we're here. Do you see what I have? For the rest, if you didn't hear that, the question is what optimization level? Excuse me. And for the sake of the argument here, it doesn't matter. I have a function called use. The function called use is intentionally just forward declared. By the way, if you spend a lot of time in Compiler Explorer, this is a huge help for like seeing what your code's going to actually do. If you just forward declare functions without actually defining them, then you're going to see a lot more generated code and what the compiler's having to do here. And then on line 3, I've just got a function called add. It literally does, it does what it says on the tin. On line 6, static constexpr auto fun. What is the type of fun? So function pointer. Yeah, function pointer. And then on line 7, I call use with the function pointer, right? So the question is, what is being passed on line 7? Right there. This is a static constexpr object. It's moving offset flat colon add int comma int. Now I ask the question, is there anything missing from this assembly output? Now I'm going to see just how many of you are familiar with what level with compiling and linking and what's that? Use is void, the parameters aren't being set up. No, I'm setting up EDI, which is the pointer to the add function before calling use. It's fine. The parameters aren't being set up for the add function. Well, no, because we don't know what call is just taking a function pointer. Call is taking a function pointer. That's the point that I want to get at here. Do you know what's missing? Nobody? Hey! Did you hear him? Relocations. What is the address of a function? Is it known at compile time? I heard a confident yes. If I do like a disassembly of the linked object, then I'm going to get something more like this. These are x86 6432 things. Notice it says move 0 into EDI, but then has this thing on line 7, which is it's the relocation entry. Relocation entries. So the address of a function or really any other static data cannot be hard-coded directly into the binary. Generally speaking. We'll get into situations where it can be. This is going to be dependent on OS settings, such as like, I say at the bottom here, security settings like address randomization for where the binary is loaded, compile time link order, runtime link order. Things can vary. So the values must be runtime computed in some way, at least as an offset. You'll often see stuff in the binary that might be like RIP plus 1033 or something like that. It has to do some kind of a runtime computation for what you thought was a compile time static thing. On Linux, if it's not something that can be computed with just an offset to a register, this is a call to DL relocate object. And now I will admit, I just heard someone say that like a good technical talk talks at like 20% of your knowledge level so that when people ask questions, you can answer them. I'm talking at about 90% of my knowledge level for how relocation works. Okay, so if you ask deep questions here, I might not know the answer. But it gives you something else to play with when you get back home. But I'm going to try to measure these costs. The relocation table entries in the binary, functions that must be omitted, because often functions can just, like constexpr functions are not necessarily omitted into the binary. But if I create a pointer to one, then it has to admit it. The actual relocation cost itself, and potential table and data copy cost. We are going to assume GCC for simplicity. We're going to assume O3, and we're going to assume a strip binary. So only what is 100% necessary for execution. That's poorly worded. Who wrote these slides? Okay, this is my example test code. I've got, 7 different constexpr functions. They do what you would expect them to do, except, mod, div, whatever, subtract, bor, so bitwise or, bind for bitwise and. I needed them all to be 3 letters. I don't know. And then I have this function that is consteval on line 12. What does consteval mean? Oh, that was like 5 different answers. Wait, what? It must be evaluated at compile time is approximately what you all said. Do you say I don't know? It's also known as an immediate function if you're going to go look for it, okay? So this function is, it is. I'm doing air quotes because I don't know. I'm sure there's some weasel words in the standard that say we can't like observe whether or not it actually was or something. I don't know. Probably Nevin. I'm just going to call you out. So this thing is going to be evaluated at compile time. All right. On line 13, I have a const array of all of the functions. And then notice on line 11, this thing takes a num. So really, I'm just creating an array of all the functions, and then I'm just taking a subset, because to me, that was the easier thing to do. Now I have a way of measuring the cost. So on line 22, I can iterate. I can say, I want to build a table of 2 functions, 3 functions, 4 functions, 6 functions, whatever, up until I see what the cost of adding each extra relocation is here. Now on line 23, I know for a fact, because I'm calling this program with 0 arguments, I know for a fact that add is always going to be called. Because if I call it with 0 arguments, I'm getting argc of 1, because on Unix, my argv of 0 is always the program's name, right? Okay. So I know I'm always calling the same function, so I can remove that from the question of what are the costs here. So now I get to just measure the binary size differences in the runtime cost of the compiler and the runtime itself doing these relocations for me. I have done this as 2 different ways. I've done it this way with a non-static vals, and I have another table coming up with static vals. If I've got non-static vals, my baseline is, and this is just return add of argc, argc. Okay, so I always know which function's being called, so I've eliminated the cost of the add pretty much, but I still have an extra jump in there. Anyhow, 14,328 bytes for the actual binary, 145,118 instructions executed. I measured this with valgrind -- tool equals colgrind, okay? So if you've never used that tool, it's great for counting instructions in your code running. It is not a perfect metric of performance, but it is something that is 100% consistent because it is not sampling based. You will always get the exact same answer for the exact same code executed. All right, so if I make it a non-static table of 2 functions, the binary size goes up a fixed amount. As soon as I add in that non-static table, I find this fascinating. The binary size goes up a fixed amount. So it goes up to 14,464, but we can observe that simply adding more functions is costing me 2 to 4 cycles per function in my table. I think that's interesting. That's with a non-static table. I think slightly, let's see. So the table is always generated at compile time. It's const eval. Approximately 2 instructions to copy each function pointer onto the stack, 136-ish bytes in function relocation table. It is irrelevant if the table is explicitly constexpr or not. I measured both, exact same results. And this is, some of this is just initializing the tables. All right. Now I've made the thing static, and this is where it gets slightly more interesting. Now that it's static, I'm no longer observing the cost of copying that table. I'm now just observing the cost of actually calling the relocate function. And I can see that each extra function pointer that I want to relocate costs me exactly 13 instructions. That's neat. You're probably going, why do I care about 13 instructions? This table is still generated at compile time. It's const eval. 13 instructions to relocate each function pointer. And I did confirm that 100% of those 13 instructions is happening inside of DL relocate object. I think that's interesting. 0 copy cost happening, and the compiler is able to better compact my binary. If you didn't notice, the binary size went down a little bit. OK. So why did I even go down this road? Why do I care about 13 instructions? That's what Guy's asking. I can see it on his face.
Does anything of this apply if you compile to a bare metal executable?
I will attempt to answer that question. The question for people watching remotely was, does any of this apply if I try to compile to something bare metal? And yes, I attempt to answer that question, but I added those slides last night. Well, we'll get there, though. And I have at least an hour left to get through this talk based on my watch. All right, so I gave this talk called The Power of Compile Time Resources at CBP North in 2022. And I observed that I was seeing some bloat with very large JSON data structures compiled at compile time into tables. And Richard Smith happened to be in the audience. He commented that some of the bloat I was seeing was due to relocation tables. I have to be honest, I basically completely ignored Richard until today. I know. And then I was working on constexpr. This is my most recent experiment in scripting, embedded scripting engine for C++. It is a 100% compile time capable scripting engine. It is 100% constexpr. Its constructor is const eval. Now, when I like to talk about constexpr, I like to point out, because its constructor is const eval, it is always free to construct an object of type of the scripting engine. Because, I mean, it's const eval. 100% of that's calculated at compile time, which means it's just a mem copy, right? Whenever I want to create a new object of the engine, it's just a mem copy. Well, in episode 405, I talked about this tool called Dogbolt, the decompiler explorer. If you haven't seen that tool, it's not as refined as Godbolt, the compiler explorer. But I loaded constexpr into there, and I started looking at the disassembly from the decompiler, and I said, that's not just a mem copy. What's happening here? So I did this experiment. I have a constexpr engine that I am creating. If I don't do anything with this at all, 100% of it gets optimized away because it is const eval and it is trivially destructible and trivially copyable, so the compiler does optimize it away. But if I do O3 and I parse an empty string, I see 1.8 million instructions executed for something that's free to construct. If I parse a non-empty string, I can observe that parsing the non-empty string is only 1,000 instructions, 1,400 instructions. It's pretty efficient. And then looking into the details here, I see that, what is that? I should have put percentages. 1.6 million of 1.8 million. I have 11 minutes according to this timer. How did that happen? Are you sure? I don't think you're right. Now I'm just wasting time now. Okay, so 1.6 million, what is that, like 95% or whatever, is spent in DL relocate object. I think that's interesting because I thought that it was free to construct an object of this type. It is clearly not free. Now, to be fair, 1,600 instructions, or 1.6 million instructions, how fast is your CPU? How fast is your CPU, since you asked about bare metal? I don't know. Oh, you just asked about bare metal? All right, fine. Yeah, gigahertz probably. But it's a thing, because I thought it was free, but it's not. And 1.3 million of those instructions is in DL lookup symbol. All right. So runtime cost of constexpr. Point number 2, potentially expensive relocations. And then the question I have is, what does the building of that table actually look like? This is the actual disassembly of a portion. So this goes back to my example. This isn't constexpr, but this is the table of function pointers, right? So there's all these relocation entries inserted in here. And even if they can be like RIP plus whatever, some compile time known offset, it still can't do a mem copy, right? It has to actually assemble this thing, if you will, for lack of a better word, at runtime. So it's copying the addresses to these things into registers and then copying the registers onto the stack, and it's building up the stack of the things. All right. So the compiler knows what things need to be in the table, but the final values can't actually be known until runtime, so creating the table cannot be as simple as a mem copy like we would want it to be. So number 3, runtime cost of constexpr, static table with static pointers have to be built at runtime. I'm just assuming that most of you haven't considered this. Did you know this? Okay. If you want to play along at home, by the way, you can go to this compiler explorer link, and this is an actual instantiation of my constexpr engine, and you can look at how much it costs to instantiate an empty one of these things. You can play with it if you want to yourself. Although Compiler Explorer is notoriously bad on cell phones, so you'll probably want to just save that URL and load it later. All right, my conclusions here. constexpr does not change object lifetime. Be aware of that. Be aware of potentially expensive copies of data. This is a real point. I have, in fact, personally measured a serious performance regression because I made something constexpr but left it on the stack instead of making it static. Relocations are potentially expensive, but they should be paid only once per runtime, I think, during execution, and compile time tables with compile time pointers still have to be pieced together at runtime because of the relocated assets. So this should not stop you from using constexpr. I just thought this was an interesting exercise. Embedded and static binaries that are not relocatable can limit or eliminate the impact. I attempted to put this together. What architecture did I compile for here? Not ARM. What's that? AVR. AVR is so much more fun than ARM. Come on. All right, so this is AVR, which is a 8-bit platform with 16-bit addressing, right? Like all good processors are. So those are my functions. And my main here, as far as I can tell, it is actually basically able to hard code this into the linker, into the assembly, what the locations of this would be, because it knows the entry point into this executable, and then it's able to just load pointers into that compile time known entry points for the table. So if you're doing embedded stuff, definitely don't worry about relocation entries, all right? You can mitigate those problems. All right. So you are still not executing user code at runtime. constexpr does not affect object lifetime, but so you probably actually want static or inline. constexpr pointers have to be relocated. Don't forget that. This comes up. This came up in my first example with the compile time JSON stuff because I had like spans of things, and there's a lot of relocation entries there. Be aware of what you're asking your compiler and runtime to do. Some portion of relocations are string compare, interestingly, when it's actually looking up the name of the symbol at runtime. So hypothetically, if you have very large mangled names, that can actually slow down your relocations as well. And how easy is it to get very large symbol names in C++? All right. And if you want to play along at home, again, object dump -dr, capital C, capital M, Intel is my recommended way of getting the relocation entries inserted into the disassembly of your binary if you want to play with it yourself. All right. So now, like me, you know too much. And now I have to say, check out constexpr, my scripting engine with 0 runtime cost, because I was like, there's something happening there, and I didn't want there to be. All right, so this is the runtime cost of using constexpr. You can contact me if you've got any questions, and I don't know if you want to contact me about anything. MC is coming on stage.
Yes, I am. Jason, thank you so much for this very conversational and inspirational talk. You have been able to ask questions. If you haven't been able so far, now it's time. One over there and the second question over there, please.
All right. Oh.
One over there. Let's start with that one there. Can you still raise your hand? Make yourself visible. Thank you. Just for the mic.
You really don't need the mic, but whatever.
Okay.
Well, no, go ahead and use it now that you have it.
I don't think it's work. Oh, okay. So I think there's a difference that you have to kind of, I think that you missed here, which is that you have link time relocations and runtime relocations.
Right.
So in case of those LIAs that you saw, I think that was actually an optimization by the compiler. Because if the LIA doesn't cause a runtime relocation, that's a link time relocation.
Right.
So then the program can be like copy and write it, essentially. So when you start it again, it doesn't have to do the relocation again. It just decided that, oh, I will just do a bunch of LIAs and then copy that into your memory.
So interestingly, you're right and yes. So, okay. So your functions are going to be laid out, and let's talk specifically about function pointers. Your functions are going to be laid out in whatever order the compiler or the linker decides to put them actually in the binary, right? So you need pointers to those things. And even in the case where the compiler can optimize it, or the linker can optimize it, and remove the calls to the DL relocate object, it still has to have an offset, right? So you can eliminate the runtime relocation cost up to a point, but you still cannot eliminate the runtime building of the table of function pointers, because it still has to take current instruction pointer plus whatever offset, and load that into a runtime table based on what the instruction pointer offset happened to be.
No, but the compiler can also emit absolute address to function at sub blah 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 in a table in the data section.
I don't think it can absolute address.
Yeah, because that's a relocation. That's a runtime relocation.
Oh, okay. You're saying
it can do that, but it didn't, I think, because it wants to basically make it easier to copy and write the binary. But we can talk also offline more if you want. I
don't think on any modern operating system it can hard code a specific address. It always has to be an offset because it doesn't know what location the operating system is going to load the binary into. Oh, they cut you off.
No, I didn't answer yet. You can. That's what the relocation is for. That's called an absolute relocation, and that will emit, like in the ELF file, it will emit an absolute relocation that says, this is the offset to the function, that's what the linker knows, and then it needs to add the base address of the binary, which is randomized.
Okay,
so
but it still has to add the base address.
Yeah.
Okay, we're saying the same thing. So something has to happen at runtime. Something has to happen at runtime. Yes. Okay.
One question over there, please. That person in glasses, thank you.
Where?
Hey. Hello, Jason.
Oh. Now, why'd they give you a mic?
Don't worry. Have you tried on Windows?
No.
Because I think what you're hurting is the one thing that Microsoft got correct, which is that symbols are not relocatable or variable by default, so they don't need to be like PLT blah 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 bullshit.
But I thought Windows could still do randomized.
Yeah, but it should just be like a relative to instruction pointer rather than have like the relocation code.
Well, yes, but still like what they said. But still, if you have a table of these pointers, something has to be done at runtime to do the offsets to the function pointers.
Right.
Yes.
You can probably disable, like, you know, fpi is an option technically. It might be the default, but you can probably disable all that if you're a crazy person that really don't want to pay for it.
The only way I could get it to completely remove it was in the AVR code where I said, you know the entry point of this binary, and then it was able to hard code the rest of it. That's the only time I was able to get it to hard code the whole thing.
Okay. I think there's might be like an fnopick or whatever from like pre-relocatable.
Pre-relocatable.
Yeah, not recommended by any means, right?
Why am I still holding this? Okay. Oh, there's a question. Just yell real loud. Okay. Rip relative address. Yes. Right. So you might not get a call to relocate object, but you still have to do the rip plus something. That's what I keep coming back to. It's not like it cannot build the table of function pointers at compile time. It can't. Yes, I think I'm being like cut off. I think. No?
Not by me.
Oh, so I still have as long as well, the screen keeps changing. Yeah, so even if it doesn't do a call to an operator or to a runtime linker code, like if I had a table of function pointers that was const eval and I thought that it was making this thing at compile time, it can't.
This is you, Jason, not being cut off, on the contrary.
All right, I'm out of here. Thank you. People who just left early are going to miss the raffle.
Exactly. Don't go away yet because we've got several things to do yet. And Jason, congratulations and thank you for your wonderful talk. Somehow you made the impossible possible. You made some people very argumentative in this room, which is a great success. Jason Turner, everyone. Don't go away, we've got a prize draw in a minute, but first some thank yous. So this has been Code Dive number 11, and we've been back to the roots. If you enjoyed the conference, you can show your appreciation by grabbing a carrot on your way out. We got the largest available in this town. I'd like to thank everybody who came and who watched and who is going to watch online later on YouTube. I'd like to thank our wonderful speakers. Thank you guys for your fantastic expertise and great entertainment. I would like to thank the cinema for having us. Thank you, Tech crew for making it happen on a technical level. Yes, do it now. And there's one very, very special person that I'd like to thank. I mentioned her before. She's the youngest code diver ever. Her name is Rebecca. And why don't us join here, Rebecca? Why don't you join us? We've got a little something for you. Did you like the conference?
Yes, it was actually quite interesting and yeah, very nice.
So we've got this wonderful pair of socks if you get cold in December, and this is something you can maybe use under the Christmas tree as a gift. Congratulations. Thank you for being with us. And now, can I ask everybody to just follow my lead just very briefly? So, which is your dominant arm, right or left? Extended, just your dominant arm. Go like this. Now with the other arm, go like this. And now... Well done, everybody. My name is Rafał Motriuk. I'm a broadcaster. Thank you very much for having me 11th year straight. And now I will hand over to Ewa Okołotowicz. And she's the person who was able to make it happen for us. And she's got an official/unofficial closing of the conference. Ewa, over to you.
Thank you, Rafał. Thank you, Rafał, and actually thank you all. I knew that this edition of Code Dive is going to be a blast because as we opened registration, we were fully booked just a few days after. So thanks a lot that you followed the registration process and that you are actually here with us. Because thanks to your own energy, it all can happen. It all can be possible. But before we're going to find out who's going home with the biggest smile as a winner in the lottery, I would like to thank to my great team. Thank you, people, all volunteers, organizers, and my right hand, Laura Osińska. I would love you to join me on the stage because this magic has been created by you. All of you, come over, please. Yeah, all those people were responsible to create this magic. And thanks to them, 11th edition of Code Dive was actually possible to happen. And that we could deliver to you so many wonderful topics. And one of the most amazing speakers, father of C++, and other keynotes that were today with us. Did you like it? Seriously, I have no idea how are we going to beat that next year. But this is quite challenging. But we like challenges, don't we? Yeah? Okay, so I will put my hand here. I will ask my team to join me. It's going to be difficult, but they're going to make it. Okay, I'm going to say code, you saying dive, all right? You ready? Code dive! Woo! The 11th edition of Code Dive has just ended! Woo! Thanks, Emil, for your energy, for your presence here, actually. Without you, we wouldn't make this conference, right? But now let's find out who's going to get back home with the biggest smile. Dajcie mi losy. And let me show you the prices. Yeah, we have tickets here. Who likes Star Wars? We have a couple of fans. Who's that? I'm not asking you. Yeah, that will be a first prize. You ready for it? Magdalena? Dam da da dam da da dam. Who do we have in here? His name is Paweł. His number is Mambo, number 5. Number 5, Paweł. Do we have Paweł with us? See 3 people. Woo. Okay. Waiting for Paweł. But if he's not with us, we need to find out another person. Okay. They might be useful, right? Let's check it out. Who's going to use them? Please. Her name is Michella. It's 119. Woo! Congratulations! Great! Congratulations! Fantastic! Great! Is Paweł with us? Yeah, please join us on the stage. Yay! Congratulations to you, Paweł. Thank you. Bonsai tree might be very relaxing during long winter evenings. Her name is Joanna. I'm not sure if that's 93. 43. 43. Joanna is going to have a lovely bonsai tree at home. Joanna, 43. We're going to wait for Joanna. And this huge Mandalorian Fang fighter. They're just watching me like, what is she talking about? All right. Last ticket. 122, Olivia. Olivia, 122. Olivia. We're going to wait for Olivia and check who's going to take bonsai tree. Okay. Victor. How many Victors do we have in the room? Yeah. 171. Mateusz? Yes. What number are you? No negotiations. Any more Mateusz in this room? 140. Was close. Okay. Did you say 172, Mateusz? You lost your chance. Robert 26. My heart is broken now. Agata? 165, Agata? Yeah! Come join us. What number are you? Yes. Congratulations, yeah. And the last one. Patrick, 129. Woo! Congratulations. It's worth a picture. Congratulations. Thank you. Thank you very much. Yeah. So, thank you. And to wrap up this conference, but just here, though we're seeing each other in the Szklarnia, right, for the after party that starts 8:30. Okay, we've got some beer vouchers and a lot of motivation. Let's code our future, and I see you next year. Thank you very much. Thank you. And thank you. Dziękuję.
Nie ma to jak dobrze wystartować tydzień. To jest. Potem już z górki. Może być tylko lepiej.